So Zoom always will be there, and I'm going to share the screen by Zoom, right?
Yep. That's it. The music is a bit annoying.
Patrick, how about, all right, 1 second, no.
See what we can do here. And another thing, this we will need.
Right? This we will need, but as a share, can you download 2 files which I sent you? They're not there.
Sure. You mean the PDF?
PDF I sent you yesterday. With this night.
Yep.
Can you download them?
Yep.
I have a question. Do you have any audio in your presentation?
Oh no.
No. So any audio from this would just be Zoom conversation.
Yes.
Yes.
And also, can you open 3 websites here?
Actually, it's better if we directly put this one there. Directly in the Firefox is better.
You don't have a reader?
Oh, I have, but it's better to
Now, how to go to the next one?
how to go next step.
Yeah, how you go into the
That's a good question.
maybe this one.
I agree. Yep. Perfect.
But still, I don't like the writing here.
This works. One more thing I want to try. Just we will
And as a sharing screen, I want a workshop website now as an introduction. How to go down?
workshop website.
Yep.
1 second. Maybe
Hello, everyone, and welcome to AGI-22. This is the NARS tutorial and workshop. Our hosts will be Patrick Hammer and Peter Isaev. AGI-oriented NARS, Non-Axiomatic Reasoning System, has been attracting increasing interest from researchers and students from around the world. The workshop will start with guest speakers' presentations about projects related to NARS in the tutorial that introduces the conceptual design and the current implementations of NARS. The workshop will conclude with a general discussion that will focus on the future research.
Have you unmuted? Oh, before everything is. This is Mac window. Right. And screen sharing. Sure.
But they are also being okay. Going those mics. Both mics are recording my sound.
Oh, yes.
It's not that one.
I don't think so. I hope this works.
Because it's hard to compensate for the background.
Confirmed you are live on YouTube.
Okay, good. So that's what's on the YouTube this year, right?
Oh, yes. I think so. On the screen. Maybe we can. That. Sure.
You can see something here.
Oh, yes. This is working.
Hello, Patrick. Hello, Patrick. Can you hear me? Hello.
Shall we start?
Okay. Okay.
Okay. Hello, everyone. That's it. That's clear. I think the time to start. Hello, everyone. So my name is Peter. We're going to organize that NARS workshop today. That's a full day event, and it will have the two parts here. I just want to confirm, is everyone hear me from the Zoom? Because we have some presenters on the Zoom. Can someone respond? Like Pei, for example.
Yes, we hear you.
Pei?
Yes.
Patrick?
But-
Robert, I cannot hear you.
Test, test.
1 second. Patrick, can you come here? It's somewhere.
1 second.
Yeah, but it doesn't have to stream over there. Like everyone will see, but here.
Let's see. Can you hear me now?
I can hear you through the laptop, tiny speakers. It's a problem.
Ah, this you mean.
Yeah, it's really a problem to reach the audience.
Okay.
How do you select the speaker?
Optimum. Now, can you talk?
Yes, here I am. I'm speaking to the.
Camera does not work.
No.
You can't hear me?
Say. Okay.
Hello, 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 hello.
Only works with this speaker.
Okay.
Maybe
Could you
the-
hear?
down because of the
Let me
music.
ask.
1 second. We're trying
Yeah.
to connect the speaker.
Yep.
We talked, so they're working on the microphones to be hooked up to the optimum. We just have to choose here the projector.
Yes, we can put the speaker close to the microphone.
Right.
But I guess that's not a good idea.
Yeah, Robert, yeah, we still don't hear you.
You can't hear me?
Still trying to sort it out.
Do you hear me? Hello, hello.
It's much.
No, the thing is, you have to speaker. You have to go.
No, I already did the optimal. Optimal doesn't want to do that. Does it need a separate cable? No, else it wouldn't have detected it first. No.
That's what the point was. So the mics actually are those mics. It's not that mic.
I agree.
So those ones. That's why I wanted my system to hook up with everything. In the network it has everything.
Ah, I see. But the microphone should be done.
Mics should be fine. And the speaker. I don't think is this is. Can I try one more thing? Can I try my? And we can try, right? Also.
But it doesn't change the spec. I think that the spec runs over this.
Yeah, but that might not have the sound propagation over here because it has mainly from video.
Oh, no, it has to, else it would not select, see the speaker. It has to. I was also thinking, but since it detects the red name, it has to work. It's understanding the protocol. So it has to go through this. Right. Then maybe you can turn off this. Test. Okay,
We can hear you.
Yeah, but now we have an echo. 1 second.
Is it because this is too close?
1, 2, 3. So.
But now we don't have it in the wrong route.
Right, if I say there, so this might be up and we have error.
Yep.
Maybe we should not. Maybe we should not use that outside.
Actually, we should not use this one.
This is not going to do.
Peter,
This is
read
going to show.
the chat. Read the chat.
So this is going to zoom, right?
Can you hear us?
Yes. Yes.
Perfect.
Right. Okay, so
Great.
finally.
Oh, great. I can hear myself with 1 second delay, but that's fine.
Okay.
All right, so we're ready to start. Finally.
Right.
Sorry for us for being a bit late, running late. So I start with the introduction. So today's workshop will have 2 parts. One part is for the basically presenters from Europe because of the time zone, mainly from Patrick Hammar's team in Sweden for Robert Johansson. Then I will continue with an introduction to NARS and the design overview of the newer version of NARS, which is 3.1.3. Later, there will be Patrick will present its OpenNARS for application and also its design. And then we will finish up with Adrian, which is from Poland, who is doing some experiments with NARSing, and Dr. Pei Wang's students, PhD students, who are Tanguy and Christian Han. And at the very end, we will have the demonstration and a bit of robotics example and a bit of visual demonstrations how the NARS works. How NARS works in terms of computer vision and in terms of reasoning in the real time. For this workshop, we have a little bit different from the last one, because last one we had many projects going on and many presentations. For this one, because of the conference switched, if you remember, it has to be in Russia in the first place. So we kind of didn't know if we want the workshop in the first place. And when we kind of decided to do that, so we couldn't really arrange it to other projects and speakers. But I think we will fulfill the time accordingly. Also, wanted to know that Tony Lofthouse wanted to present his system here, but unfortunately, he was not able to do that. And so we are stick with our presentations. With all that said, I just welcome everyone to the workshop, and I just give the word to the Robert Johansson, who will probably have to present his topic about the nature and reasoning. Robert? Now you have to share this. Yeah, you have to share the screen.
I will do that.
Yep.
Let's see.
Okay, we can see it.
Oh, great.
All right, it's all yours.
Thank you so much, Peter and Patrick. So I will speak a bit about some experiments that we have done with OpenNARS for applications. And I'm based in Stockholm, where, as Peter said, Patrick also works nowadays together with me and Tony Lofthouse. So Tony, who is in UK, is also affiliated to us at Stockholm University. And my, how to say it, the way into this is that I'm curious about, you could call it psychological capabilities in NARS. So we have conducted a series of experiments that explores that, and we use for that purpose open NARS for applications that Patrick has programmed. So it's always very convenient when we run into something. It can be a new release 30 minutes later, sometimes 3 minutes later. So we have a very nice collaboration in our team, I think, where we discuss new projects and we are immediately able to revise the code accordingly. So some of the experiments I will talk about today is from the master branch of ONA, and some are more from experimental branches. So the first thing I wanted to mention is that I have been playing around a bit with this open source framework, Python framework for creating psychological experiments. And this actually works very nicely together with the Python interface to ONA. So I will make a demonstration of something called conditional discrimination. And this is something that is studied with a match to sample experiment. You can actually say that the match to sample experiment is the same thing as a training in conditional discriminations. So this kind of experiment that I will show some examples of in ONA can typically look like this, the match to sample experiment, that you present for a participant or for the NARS system, in our case, a symbol. It can be a symbol that the system has seen before or a new symbol, typically a new symbol. And when we first present it, we call that the sample. And then the task for the participant is to match that symbol either to the left or to the right, and indicate its choice. For example, I choose right. And then, since in this case this was nonsense symbols, we provide some feedback. So in this way, the system can, or the participant taking part of the experiments can learn to associate some symbols with others. And how we look at this in the NARS system typically is like this, that we have some symbols we call A1, B1, B2, B1, B2. And when the system is starting out, it doesn't know if it's gonna press left or right here. So I will show how this can look in this open source framework. So this is an experimental framework where you can design typical parts of the experiment, or like phases, and very easily design parts of the experiments that will reoccur. And since it's in Python, it's very easy to include Python code. So I have basically just put in NARS code here. So I have marked here something I call a visual as true, to be able to see what NARS do in the experiment. So I run that here now. I hope you can see this, that it says baseline, no feedback is given. So here NARS just babbles between left and right. So basically learns nothing since it doesn't get any feedback. And then it's the shifts to training, so feedback is given. So sometimes NARS is correct, sometimes incorrect, sometimes does not give an answer. And the confidence value in a set of hypotheses increases, and I will say a bit more about that. So this is during the training, and after a while, the system becomes more and more confident in when to press left and right, depending on what is the sample and what is the left and right options. And finally, in the testing, no feedback is given again. So it basically tests, and here we see that NARS is correct on most of the time here. This has also been a very pleasant experience to work with this framework. I just discovered it a few weeks ago. And it's possible to open the log file and see here during the baseline, for example, NARS was correct very few times out of 12 possible trials. And during training, the correctness increases, so to speak. Let's say that we wanted to maybe increase the training for NARS here to be even more confident. I can do something like this. I turn off the visual and increase the training maybe 9 times, and we can actually have a very short baseline. So it looks something like this then. So it just shows this blank screen while NARS is working in the background. And here we see that NARS was 100% correct after a few more instances. And this is very easy to plot. I can do something like this. Let's see. So here is since I increased the it was more beautiful before. It was supposed to look something like this. That these dashed lines, I didn't move them in the code. Anyway, as you can see in the experiment, we have a baseline here where NARS, this is the % of correct trials in a block. So by babbling, it should be something close to 50. And when we get feedback during the training, the system gets more and more confident. And then during the testing without feedback, the system was correct, but the confidence value typically doesn't increase or doesn't increase much. So what I had there on the graph was the average confidence of these hypotheses. So this is what we in behavioral psychology call an operand behavior, or when we have something of this size, as I said, we also call it conditional discrimination, since whatever happens here is dependent on a condition, the sample. So this is an example of a simple experiment that is possible to do with ONA. And it's very nice, I think, to be able to design the experiments in this framework and notice how the parameters change over time. And it's very quick, actually, to design new studies. And our submission to the main conference was about identity matching. And identity matching, you could say it's a special case of conditional discriminations. It's when you show a sample and the choice options are either the same as the sample or something else. And since this is a new symbol or new symbols, the system has to try first and maybe it's correct and learn over time to, okay, I'm going to pick the thing up there that is the same. But during training over time, it will learn which symbols that goes with which, as in the experiment I just showed. So that experiment can be called identity matching. When you train a system on a particular set of symbols and test the system on that set of symbols. But the hard thing for animals is when you then, after this training, test the system on symbols that it has never seen before. And it requires the system then to use to abstract the knowledge that it has learned from before, which in ONA or in all NARS system is realized by the 6th layer of the PACE model, where the variable introduction is done. So this is something we show in the paper that is published at the conference, how this is done in ONA. And of course, this can seem like a trivial task, but this is something that is studied quite extensively with various species from the animal kingdom. And here is a sea lion online that I won't show a video of because it destroyed last year's workshop. But I really recommend everyone to search sea lion plays snap to have a very, very good example to see this in action with an animal. And here the animal sees a palm tree as the sample and have the choice options of right turtle or left palm tree. So the hypothesis we explore here is, except for the specific hypothesis, we are also then interested in the general hypothesis, which this is our picture from the paper that we published. And you can see here, during baseline, where there is no feedback, the system just babbles. But when it gets more and more correct, the confidence value increases of both the specific hypothesis, but also for the general hypothesis. And this is actually something in behavioral psychology terms, it's called generalized operant behavior. And the key thing, so the last experiment I show is typically operant behavior. So this is generalized operant behavior when the system can do a novel behavior in a new situation that it has never seen before. But the important thing is that specific experiences can increase the confidence of the general hypothesis. So the general knowledge get increased by the specific examples, which is exactly the definition of a generalized operant behavior in behavioral psychology. So this is a real key thing, we think, that to show that an AGI system can learn in this way and develop something that is, of course, it's a minimal example, but it's still an example of something that the system can generalize to lots of other situations. So this is something also typically studied with the same method of the match to sample experiment. And another example of match to sample is something we have explored recently, which is called symmetry. So symmetry is something that is really, really hard for animals, other animals than human beings. And it typically is like, if we train with a conditional discrimination or in the match to sample task, we train someone that, in the context of A1 being the sample, I pick B1. And please remember that if this were to be done with a human being or an animal, it wouldn't be numbers, so it would be nonsense symbols. But here we use this notation with A1 and B1 to be able to communicate this as clear as possible. So let's say that we train someone in picking that symbol rather than the other symbol. Then the question is, if B1 then is the sample and A1 and A2 are the options, which one to pick? And please remember that this is, how to say it, once again, this can look very simple when we use these numbers, but when we use symbols that we have never seen before, it's not as easy as one can expect. So it basically requires the person to reverse the relationship. And this ties in, of course, in learning other relations like A1 and C1 and A2 and B2 and A2 and C2, and learn a whole network. And when you do that, we typically talk about stimulus equivalence. But the first part of the stimulus equivalence experiment is to show symmetry, that if you have learned the relationship between A1 and B1, in the context where A1 is the sample, I learned to pick B1. How can we then make the system derive that, if B1 is the sample, I probably pick A1 rather than something else? So it's a problem that you can attack, like, okay, or since this can be done with the children who are like 15 or 16 months old, like before 2 years of age. So is this something that develops over time, just naturally, or is it something that is trained? The children has extensive training history that makes this develop, or is it something else? Is this an innate capability? So this is something we explored in NARS and basically ask, how can this be learned in a NARS system? This is a recent survey on this capacity in animals, where in a review they had 30% of the animals who they included in the review could do this. So the sea lions could do it, and there's some mixed evidence with pigeons. But a lot of monkeys, for example, they train it thousands of hours without they developing this knowledge on symmetry. So this is something we have done with ONA, and I will show it here. So once again, we have multiple parts of the experiment here. So the green things are these main parts. So we have a baseline where we don't provide any feedback to the system. And actually, I have removed that from the experiment. It says 0 cycles. So here it says training A/B. So it's typically the same task as in the conditional discrimination experiment. When I see A1, I learn to pick B1 rather than B2. When A1 is the sample, I learn that, and B1 is the left, I learn to do the left thing. If A2 is the sample and B2 is to the left, I do the left. But if A2 is the sample and B2 is the right, I do the right thing. So here we do something that, and to give you some background on this, it's when Patrick designed his system, ONA, he had a strategy that I think was very respectable, that he removed everything that was not necessary. And Patrick can, of course, tell this story for himself, but my interpretation of it was that he removed everything and initially only kept the reasoning over time, the temporal implications. But when we organized our first internal workshop in Stockholm in late October, early November, and Tony Lofthouse came to us and worked with me and Patrick and our collaborators from Stockholm. We really tried to attack this problem, and I think probably it was me who showed the experiment, and I think this is something we should try with NARS, and Patrick and Tony really discussed it intensely, and after a while the conclusion started to emerge that maybe the fifth layer of the PACE model need to be put back into the ONA, which had been removed. So the NAL5 things about higher order implications and equivalence was something that Patrick re-implemented into ONA. And we also had a nice workshop when Tony came to Stockholm in February, and also Robert Winche was there, and we kept talking about these things. And I will say that the result emerged after that. So this is something that developed over spring. But in accordance with the theory is that to be able to do this symmetrical behavior, you need to have experience of the relationship both ways. It's someone who has the sound on, Surovic. Maybe you can turn off the sound.
Okay, will do.
Thank you. So if we give the system feedback both while training the A to B relationship and the B to A relationship, can we then, and I also have a part here where I really make the system experience these instances very close to each other. If A1 is the sample and B1 is to the left, and I pick left, and then very close after B1 is the sample and I choose A1. So that's the explicit symmetry training. Then we do the final symmetry test, that we train the system in a new set of symbols. When X1 is the sample and Y1 is to the left, for example, and the system learned to press left there, what will it then do when Y1 is the sample and X1 is the comparison? That's a symmetry test. And I will show that now. So it's something that you can run here in the experiment. This is, by the way, done with Patrick has a branch called the Rft branch, Rft as in relational frame theory. So this experiment is currently not working in the master.
Excuse me, Robert, the sound was stuck for 10 seconds.
Okay, do you hear me now? Let's see what happened. Can you hear me now, Patrick?
Yes.
It's working. Okay. Okay. It's fine. Okay. So once again, here's the results, and I will show it in the graph, but the important thing here is that during the testing, the system is 100% correct there. So I go back to this. And before talking about the hypothesis, this is the experiment that the system was trained in AB and then in BA with feedback. And then between here, there is a short period of explicit symmetry training where the system sees these experiences close in time after each other. And then is trained to pick Y when it sees X and so on, and then tested on the, oh, it says testing XY, it should say test YX. So should be testing YX. There we have the updated version. So this is from that particular experiment. And here is the important thing that I hope Patrick will comment on this, because this was really a major thing, I think, back in February when Robert Winchell and Tony was with us in Stockholm, and Patrick really cracked the nut on how this is to be done, that this is really about higher order relationships between contingencies. So this is one example of such higher order implication, that an experience of a conditional discrimination relation like this can be the cue for the symmetrical version of it, and the other one is just four versions of it. And this is a person, I think it's such a beautiful fact, and it's really, how to say it, an example of a higher order reasoning, or an example of when the system learns something and a quite complex relationship can be the cue for something else. And I haven't told you, Patrick, but very recently I discovered that this is something called you could talk about this as regularities, and it's very much in line with cutting edge behavioral science, that if we talk about the three-term relationship, A1 do the left and the consequent as a regularity, we can talk. This is part of this theory that one regularity can be the cue for another, and they call it meta regularities. So they explain relational frame theory processes with this thing called meta regularities. So it fits very nice with this how it's done in null5, fifth layer of Tay's model. but I think it's a very nice combination of Pei's original thought and Patrick's obsession to have the temporal reasoning at the core. So it gave rise to symmetry very nicely. And I would say this has very powerful implications. So this is one of the most famous studies in relational frame theory on the very basics of how these things develop, because since this develops so early, it's very hard to, how to say it, study it. So you basically have to find an infant where this has not developed yet and find a method that you can prove it has not developed and try to measure it. And in this study, they how to say it, tested the infant and then did the explicit symmetry training and looked what happened afterwards. So what we did then was basically a copy of that study. So this is an experience. This is once again an encoding that is only available in the Rft branch. And Patrick can talk more about that. But basically, this is if something is the sample. Maybe I have let's see, something I can show first. So basically, this is an example of you show something to the child, something that the child has never seen before. And you say to the child, this is a boohoo. And then after a while, you ask the child, where is the boohoo? And some object is to the left, and the child learns with repeated experience, I press left. Maybe you learn the same thing for the right options with something else. And this gives rise to a powerful pattern, because then the child can have, after that, only one can have a new experience, that it sees something. A dog, small dog meaning the object dog, and large dog meaning the word, the spoken word. It has this experience again, but with a new object and a new sound. And given the question, where is the dog? And choice options left and right, the system can do this, can respond with right, using this precondition. And this is done with these higher order relations. And so this is obviously extremely powerful, that you can, it's multiple things in here. The first thing is that you can train the system in a general pattern, so that it can generalize this to a lot of new situations. This is obviously something you can tell the system here anything. You can show it anything and say, this is the name for it. And then the system can, given that information, complete the task of picking something, just hearing the name of it. And as a note, Ona learns this with, how to say it, one experience of the symmetrical relationship forms a very weak hypothesis of this pattern. And for the child, of course, this is something that is repeated and repeated over weeks or months. So it's also an example of the power of the null 5 implication. And for people familiar with relational frame theory, a statement like, this is a dog, is called the C real, and I will tell what that means. And where is the dog is called the C func. So this is part of the context that makes the system, one, understand what relationship am I applying here, and two, what am I going to do about it? What function am I going to act on, so to speak? So the first part here, this is a dog, is that the contextual cue that the symbol should fall back on the symmetrical null 5 knowledge, like this thing. And the where question is the cue for the symbol for the system to do the where behavior, to point left to right. So it's a combination of the relational information and the functional information, so to speak. Given this relationship, do this. And Patrick has more examples in the Rft branch of ONA repository. Like this is a very nice example. Maybe I have it here. The previous example was, you say this is a dog and then ask, where is the dog? But maybe you say, this is a dog and ask the system, what is this? So it's the same relational information, but another functional cue. And you train the system to say the sound that it just heard, which can be realized using this information. So if you say to the system, this is a banana, this is a cat, and then show a cat to the system, you can ask, what is this? And the system will reply with cat. Or what is this when you see the banana? And the system will reply banana. And I hope I could, in a way, convince you that this is a extremely powerful pattern, which is, it seems highly related to language, and it gives rise to a lot of interesting capabilities. And I think NARS handles it very, very well. So I'm about to finish here, but I hope, since we all want to build AGI, I hope to have convinced you, or at least given some food for thought on that these steps that we have taken enable some kind of roadmap. So behavioral psychology starts with studying, for example, the operand, and moves further to a generalized operand, as in the generalized identity matching case, and then moves to the symmetry case, which also, by the way, is called the generalized operand behavior. And from there, we can go to even more powerful relational patterns, which follows very nicely from this. And Patrick and me, by the way, believes that it's a lot of power in the null 5 implication. This is not about equivalence information. We think this, at least and I think Patrick agrees. I think he agreed when we talked about it last time, that this really enables a lot of relational patterns, like abstract versions of things being larger or smaller, or opposite, or distinct, and so on from each other. So this is something we're working on at Digital Futures in Stockholm, which is a collaboration between several universities in Stockholm and institutes. and they have provided funding for Patrick's position, which we are very grateful about. And they have also funded Pei to come and visit us this fall for 3 months, September, October, November, which we are extremely grateful, both that he can that he wants to join us in Stockholm for 3 months, and that he's funded from Digital Futures for that visit, and that Temple University approved his 1-year sabbatical. But Pei will have something called Distinguished Lectures at Digital Futures, which is live in the Digital Futures hall, but it will be broadcasted via Zoom. So that is on September 8th, where Pei will talk about the basic questions about artificial general intelligence. And it's obviously going to be an extremely interesting talk. And Pei will also have a 8-week course on AGI that is also given both face-to-face and online. So if anyone here is interested in taking the course, they can email me and we can see what we can do to arrange. But this is also something that will be publicly available. So with that, I say thank you very much. And if there's any questions, I'm happy to answer them if I can, or hear any other comments from the audience, or maybe from Patrick. Thank you very much. You're muted, Patrick.
Okay, but now there's an echo. Can you please stop screen sharing? I just stopped.
Yeah, this is just me. It's not the screen.
There's some sound issue.
Oh, yeah.
Test. Thanks a lot for this very insightful presentation, which I think shows many important aspects of human intelligence, which need to be understood in the future. And I think this was a very good talk, especially with the experiments regarding identity matching, which most of the species in animal kingdom cannot do.
Now you're muted again, Patrick. The last thing we heard from you was that you said not many animals can do generalized identity matching.
Mm-hmm. Exactly. Oh.
We can't hear you.
Oh, does it work again? Ah, great. Thank you. Look, yes, not many animals can do identity matching, and it's RFT predicts it to be a key aspect of language, essentially, and so it's very fascinating also to understand what actually happened when animals went from fixed signal systems where the signals they exchange actually have some innate meaning, like encoding certain danger signals or mating signals and so on. What happened exactly to go from there to a more flexible representation where we can assign labels to stimuli in a very flexible way, where we can have names for objects and then go further and relate these names with each other in a way that we can actually change our behavior based on the information we convey using this flexible encodings. And that there's a lot to be explained, and I think the work you're doing with the identity matching and also symmetry is very groundbreaking in this aspect. But I will stop talking now because maybe in the audience there might be some questions. So thank you, and let's see.
Thanks a lot, Patrick.
Are there any questions?
Almost 2 minutes to go into different sample.
Yes, there's no question from the audience currently, but maybe I have a question. Regarding this, how to say? Let's say a system is very good in creating this meta hypothesis about contingencies, like to observe the outcome of a certain experiment and then to derive behaviors for situations the system has never experienced in the past. Would you say that this is everything needed for language? Are there additional capabilities we haven't even yet seen or understood that they will be necessary, or not sure how to say it? Do you think this will suffice, or are there additional representations we haven't even yet understood that they will play a major role?
Patrick, there's a question from online. Can I give it to you?
Oh yes. Maybe you can keep my question in the back. There's one from the audience.
Is the system assuming that it is in a static environment, i.e. not moving or changing? A question like where seems to rely on knowing where itself or objects may be in a relation. So in the example we had, the where word was just a cue. It's just a cue for the say operation, so to speak. In the current example, the system could not do anything else with a where operation, and it just learned it by, we showed the where word, and the system learned, I will only do the say operation after I've heard the where word. So it's not really relying on any, how to say it, fake things. It's rather than that NARS can only do a particular thing with a where word. I'm not sure if that was the answer to the question, or if Patrick wants to add anything.
Yes. So essentially, you're saying that there is no hard-coded way of the system should respond when the what word is mentioned, but it should actually learn that the human or the part of the task is to only say the label of the thing if the what word is actually mentioned, right? So if we show a new object the system already knows the name for, it should not simply tell us the name, but only if we ask for the name, it should tell us the name. And similarly, if we ask where is, and then mention a certain object, and then it should be able to find it. And that's a very good thing, because if we look at small children, if we show them like a new object, and we tell them this is a homolo, and then they can derive many behaviors from this, none of which they have particularly experienced before. They can now answer, what is this? Ah, it's a homolo. They can also respond to, where is the homolo? and they will point to it. And so there are many derived behaviors, none of which they have explicitly experienced for this new object. And so this seems to be a very fundamental capability, which surprisingly is exactly what the symmetry example also demands, and which only these higher developed animals like great apes, corvids are able to do to some degree. And so maybe you have more detail about which animals actually can do this. It would be interesting. So sea lion, you said?
Yes, the sea lion is really reliable on it, and they have some good experience with pigeons, but they need to be trained in a very, very particular way. But then they can demonstrate it. But the sea lion is really the only thing that I have seen in the overview papers where it's displayed in this way. But did you say corvids also, Patrick?
Oh, yes, corvids.
Yeah, given their, how to say it, smartness in other tasks, I wouldn't be surprised if they can do it too. Yeah. Mm-hmm. But to answer your question too, Patrick, is that since the full stimulus equivalence thing, as I mentioned briefly, requires it basically requires a form of transitivity, that maybe the system learns to pair A1 to B1 and A1 to C1, and not only then derive the symmetrical relationship, but a human being will also derive transitive relations. So this is what's called stimulus equivalence. So Patrick and me have been exploring also transitivity in ONA. And I have mixed feelings about transitivity. But I'm not sure in a way that it's required for, it looks on this diagram, of course, that, oh, you need to have some transitivity for equivalence, but I'm not totally convinced that it's needed for stimulus equivalence. But when it comes to higher order reasoning, like for larger than or smaller than or something like that, then to be able to do this transitive thing seems very important. So that's one answer to something else that's needed, I think.
Can you hear me?
Yes.
I think you're got me muted and screen blocked on your end from my
we can hear
atrocious
you.
beginning.
We can hear you. Can you hear us?
I can hear you. I can see you. I can't see me, but that's okay.
Mm-hmm. Okay.
the what you've been talking about looks like, and I missed the beginning of things, is the internal interface with what possibly could be an animal or something. Is there a more interactive visual kind of interface in existence? I'm not sure at that level, because I want to talk about an animal. I have to be able to describe animals, and that has a big range from octopi to bears, for instance, and those are very different anatomies and reaction types. I'm not sure if that's a question, but
yeah, I understand the question, I think, or at least I formulated a question of it. I think it's an important thing you raise here, and I think you point to, at least how I see it, the flexibility of the NARS model, in that so in this example we basically used a nonsense symbol was at the sample and some other nonsense symbol was at the right, and the system could only do 2 operations like left and right. But Patrick has done very nice work in putting that thing on a real robot. And the other paper we published at the AGI conference is about how it was able to control a robot that can go around and have a gripper. And Patrick's, I think, key insight is also to connect train network, the YOLO model, which enables visual information to be provided to NARS, like a cat is to the upper right or a dog is to the bottom left. So in a way, that's the animal that you ask about an interface. And I think the robot is a really nice interface to interact with. So the robot in a way enables both the sensors but also the actuators. But of course, this can be done also. You could have something like the Minecraft or various simulated environments and things like that.
Okay. There's one question from the audience. Maybe you can come up to the microphone. Then also the YouTube guys will hear you.
Hello. I've been reading recently a few papers. One of them suggested that humans can't do transitive relationships. I'm jumping a little bit here. Humans can't do transitive relationships if they haven't had any formal education before. So this was a set of studies in the 20s, I believe, and I can send you links, where they started asking, there's a country in the north, they have bears there, bears in the north are white. There's a town in the north, someone sees a bear there, what color is the bear? Grown adults who hadn't had any formal education couldn't answer this question. A small amount of formal education meant that kindergarten children could. So the fact that you've trained a system to learn these kind of relationships, I think is very powerful. And I think there's legs on this. It will go, you can take this further, I think. We are blinded by the fact that we talk to humans who have had formal education. That was my point.
Thank you very much for the comment, and I totally agree with you that this is a very powerful capability with a transitive thing. And I have a small comment on that. And in the experiment I showed you with the infant that was trained in this thing like this is a where is the they track the child over time, and it spontaneously developed transitivity, I think somewhere close to 22 months or something, which was a bit unexpected. I think it didn't have any explicit transitivity training.
Okay.
However, the famous sea lion that is the only, it's only one sea lion that has done this. The famous sea lion, that sea lions, it got in the study explicit transitivity training. Which I think, and I think you suggest too, that people don't do this without explicit training in it. It seems, I agree with you, it's a powerful pattern, and it seems really to be something that you need to learn from experience.
And other relationships as well.
Yes, absolutely.
Thank you.
Yeah, thank you very much.
Thank you. Yes. Any other questions? Else we will probably go on with the schedule right better. Oh, yes.
So if I have the chance to say last words, I want to say thank you to Peter and Patrick for organizing this, but also very much, if by any chance Matt and the others are listening, that organizes the AGI conference. it's obvious that they work day and night with this. So if Matt and the others can hear this, thank you very much for organizing the whole conference with all work that is involved in that.
Thank you. And then I will take over the screen sharing. So maybe we can also put this one out of the way. So essentially what Robert has already shown us is that there are certain capacities, cognitive capacities in some animals which point to the origins of how language has developed in humans. And this is a capability which needs to be understood. And generally, yes, we have now this one model which is based on a reasoning-based approach, and you will see this is a very different reasoning system, like has been tried in the 80s with expert systems, where knowledge is essentially given by a human. Here, it's really about building a system which creates hypotheses using the evidence it has available in the data, and build hypotheses which can compete with each other, and each of these hypotheses make predictions about the same outcomes, but some miss some aspects in the preconditions and so on. The point is this system is one which allows to build multiple hypotheses or models, we could almost call them, in parallel, and is able to evaluate this hypothesis. And there's a lot of psychological evidence that actually humans and some of these animals we have discussed today are able or operate with such an idea to build hypotheses and to test hypotheses. And this is something which traditionally that there has been some work in like inductive reasoning, but usually it was more like you have a certain amount of facts, and then you try to build relationships between the facts using some kind of data mining approach, which usually takes in the current knowledge base and then outputs like implication relationships between the facts involving variables. And so if you would say A is smaller than B, B is smaller than C, and A is smaller than C, that it then would hypothesize transitivity of smaller than, for instance. But what has not been achieved in the 80s is a system which can actually do this from real-time experience, from a stream of events which bombards the system in every second with thousands of events, and the system just keeps hypothesizing and building hypotheses which are able to predict successfully. And this is part of this, what we are trying to achieve here. And there's also one very famous, I wouldn't call it a buzzword, it's really more of a technical term, which is causal representations. There's a lot of, also in machine learning, it's acknowledged that this is something we want to have. We want to build systems which ideally would have a causal understanding of their environment, so that they can essentially reach outcomes by chaining these causal relationships. And yes, yes, I will try to motivate overall this reasoning approach by looking at nature, but then we will see some particular work we have done with this reasoning system. So let's dive into this. And overall, if we look at the history of AI, originally it all started with trying to understand the mind, and clearly this has turned out to be a very difficult problem, and so we have partly understandable that we have turned into problems which which we can individually solve and evaluate a model for. And to some degree, how to say, that there's a certain mismatch between building systems which can do particular tasks and building systems which try to explain intelligence as we find in nature. As I will show some particular examples which will make this point very clear, that it's still a very worthwhile endeavor to look at intelligence in nature, and even to use experiments which are carried out with animals. And there are really tasks of various complexity, and it's a very natural thing then to begin with easier tasks which are tried on animals, and then to build a system which can solve increasingly difficult tasks which have been tried with animals. And yes, of course, in the end, we want to build human level intelligence, but we have to start somewhere. And we think this is a good way to do this. And if we look at the animal kingdom, there's one opinion of ours is that reasoning has a clear purpose, or at least not the reasoning we see in traditional expert system, but the reasoning which is studied from a psychological perspective in animals, which is reasoning is really all about letting a system deal with new and changing environments. How can you actually transfer your knowledge to new cases effectively? How can you actually take parts of your experience, encoding certain relationship between entities in order to make judgments about new situations? And yes, and clearly in nature, there's also this thing, it's one thing if you can train a model to do a task with a lot of data. It's another thing if you can actually build a system which can adapt quickly in a way that it can adapt to changing circumstances in a quite data efficient or sample efficient way, so that it will actually have survival advantages over other species. And so learning speed is really key in this. And so it's very important for animal to be able to transfer its knowledge to new cases in a most effective way possible. And yes, we have one such system which can explain some of these cognitive abilities. I'm not making a total judgment here about, yes, you have to use reasoning. No, that's one thing we will see in the future, what systems we can actually build which can explain natural intelligence. But this is our particular approach to revisit the idea of reasoning. And if we look at our working definition, there was a recent AGI journal survey by Wang on defining artificial intelligence. And what we can also say is that in the field, there is no general consensus about what intelligence is even about. And so when you build an AGI system, what do you even mean? Or AI, let's leave the G out. G was really mostly only added to distinguish the research that we actually really want to look back at the original core of AI. And so, but most importantly, if you work on a system which you hope to be intelligent, you have to ask what intelligence even is, and you have to take a certain working assumption into account so that you can actually judge whether your system has intelligence or not. And we will certainly not be able to convince everyone about the working definition we have chosen, but this is our working definition, that the essence of intelligence is the ability to adapt with insufficient knowledge and resources. This means an intelligent agent, firstly, it has usually a fixed memory capacity. So at some point it has to wait, or it has to keep certain information while forgetting others. It cannot simply add more information like in a database which grows and grows and grows. Also, the knowledge the agent possesses will usually, even in animals which have evolved over the eons, they will certainly sometimes face situations evolution could not have possibly prepared them for. And so there's a key aspect how to make these animals able to adapt to new situations. And if we look at this working definition, even though not everyone will agree on this, we can, if we take this working definition, we can say at least we can point to a few systems where it's clear that they are not intelligent according to this definition. For instance, if you have systems which are pre-programmed or pre-trained or evolved, when they are not able to learn at operating them. So if a system clearly distinguishes between training and operating phase, that's not what we are looking for. We are looking for systems which keep adapting with new experience, and this never stops. It has to, ideally, it has to keep going as long as the animal or robot or whatever this will be used in is alive or operating. And yes, and there's certainly a core issue if we take the reasoning approach, which clearly, if we look at machine learning, they have understood one key thing, which is it's very important to be able to learn from data. And I would say it's a large part why reasoning has failed or is considered to have failed is that traditionally such systems were not able to learn from data. And the question then is, can we build a reasoning system which can learn effectively from data and in a real-time way, in a way that learning just continues with the information the system receives? And the answer, I think, is yes. And I will show a particular example, at least the model we are working on. But before, let's look at the ladder of intelligence, because it's also interesting how the public opinion differs between what is actually intelligent and not. Many would say, yes, the self-driving cars we have, which are being developed, are already more intelligent than insects, some would say. But after you have seen the last slide, you will be very sure that that's not the case. Usually if you buy a self-driving car, we would expect a car to drive, right? We don't want to buy a car which we have yet to train for the driving task. So for a self-driving car, ideally, it does not need to rely on inferential learning when it's operating. But insects actually can do this. And I will show you one slide away. I will show you very impressive examples of adaptation in the insect kingdom. And yes, clearly, if we go down the ladder for coffee machines, also it's clearly the case. Everyone would agree these are not intelligent. They have a pre-programmed thing. But for self-driving car, yes, we have a bit more. At least we train some of the object detection, depth estimation, and so on. Many things which we can train on data, which is very good that we can do this. But it's still no answer for building systems which continue to adapt while they're operating. Now let's look at this. Here we have a bumblebee which learns from observation of a fake bumblebee, which pushes a boar into a hole, and then honey appears in the hole. It doesn't take long for this bumblebee to carry out this task. If we do the same thing with a self-driving car, you could do this in eternity, and because it's not designed to be able to learn new behaviors when it's operating, right? But insects, even bumblebees, can do this, and they can learn quite impressive tasks, which many people would never have believed that these animals are able to do this, but they can do. And if we go further up in the hierarchy, the ladder, clearly this ladder is not one-dimensional. Everyone would agree there are many facets to intelligence, but if we roughly would use a ladder, then that's mostly how we would categorize the things into. And if we look at certain animals like corvids, that's also a good example of adaptation, because evolutionary history couldn't have prepared the ravens for for the traffic infrastructures we just have started building a few decades ago. Nevertheless, we see ravens using traffic lights, and they essentially take nuts, they throw them on the street, then they wait till a bus or car drives over and cracks them, then they wait till the cars stop and traffic light turns red. Yeah, of course, that's a question to the condition on whether the traffic light has the color because the cars just stop. Does it really matter? They are using the nuts to throw them down and using the cars as a door to correct them. And that's quite impressive, I would say. And we need to explain these capabilities and how actually, there's also a lot of work here showing how quickly these animals are able to teach their own children in carrying out this task. So it's not something it's not like a trial and error process. It's really mostly passed on from raven to raven child via learning from observation. And that's something we need to explain. And clearly, for a long time, animals were not considered to be very smart. So the field traditionally has studied mostly human level intelligence, but we think we need to study the origins because we cannot build a human level AI system right away. We need to understand this principle. How can it be that a bumblebee with 5 million neurons or so, I'm not sure, something like that is able to carry out this task? And there is also this famous parrot, African gray parrot called Alex, which was in Irene Pepperberg's lab, and she trained this parrot essentially to use human language to answer questions in human language. And what she showed in her publications is that this parrot is not only parroting, namely learning the answers to simply learning what is the response for a certain question in order to get the nut. That's even further than that. The parrot is actually able to relate the question phrase to relationships which are visually observed. Like in this case, how many green blocks are actually in the tray. It's not sufficient for the African gray parrot to count all the blocks. It's not sufficient, even though in this case it's sufficient to count all the green things. But key is the parrot is able to relate this phrase with what it's actually saying, and is even able to give a response in English. But since then, animal experiments have evolved a lot, which shows we don't need animals to speak our language in order to show that they have tremendous capacities to adapt from experience. And yes, from all this, we can draw a few methodology conclusions, yes, a few conclusions in methodology which we can adapt in our research. For instance, we want to build systems which can deal well with a certain tasks, but we also want to understand how can we do this in a sample efficient way, which approaches what we see in nature. And also we see from this observations with animals that there are actually many aspects of intelligence which we need to understand, be it the learning of useful descriptions or concepts from experience, from sensory motor experience usually. Then if we go up in Corbett's case, ravens and so on are known to be able to plan quite effectively. So they really are able to have causal knowledge about the surroundings and exploit this causal knowledge in order to get what they want to achieve. And this is a bit different than systems which simply have learned like what is the best action to take in a certain situation. It's different because the causal representation is essentially, if we look at psychology, it's back to Piaget. It's essentially representations like under certain context, a certain operation will lead to a certain consequence. And what's so special about this representation is it does not say anything about what is currently rewarded or desired. And this makes this representation so powerful, because when the goals change, it can still use them. They are not dependent on a certain utility function. They are not dependent on certain set of goals which were present when it was training a certain task. So it can actually learn representations which are goal independent. And this is a very important thing for explaining the way humans and COVID adapt quickly to new situations and also to new demands. And yes, that's also interesting, because in animals, clearly, usually they have multiple urges, like they need to get water, they need to get food, but they don't always need to get food, they don't always need to get water. It's like each urge has a level of fulfillment. And so it would be good if it uses the causal knowledge, which is related to what is currently being the goal, based on the urges of the system, based on the body needs, essentially. And so causality, I think, is still important thing. And of course, if we look even at these cases where ravens pass on their knowledge to their children by observation, or even this bumblebee, which can learn a task from observing a fake bumblebee or another of their own kind, it's clearly another thing we need to solve in AI is learning by observing other agents, or generally learning by observations. We don't always want agents to learn directly from a reward signal, but sometimes, of course, we can say if the reward is sparse, then maybe that's of course related. But this is a capability we want to be very effective. And of course, if we go further, we end up with theory of mind, but this is something we also don't have a good solution for yet, I can tell you, but it's also something which at some point will need to be understood better. And our approach, which we take here, is essentially to climb the ladder of intelligence, which we have roughly set up here, and then try to see what kind of cognitive tasks are proposed in the psychological literature, which animals are able to do them, then also try to group tasks based on the complexity we think we have, which is inherent in the task, and then essentially to try to climb it by tackling more and more complex learning problems. And there's also another thing which we can derive. In this case, for instance, if we look at adaptation with insufficient knowledge and resource, ideally we want training to never stop, to not have a clear cut between training phase and testing phase. Of course, for evaluation and performance on a task, it's good to have this separation, but of course we want to build systems which continue to adapt and which are affected by every input to a certain degree. Of course, certain input will be ignored and so on. Yes, and we can also say that here techniques which can only handle stationary environments are not open-ended, so it's also not what we are looking for. And also learning rate decay, we don't like it. And the reason is learning rate decay makes the assumption that essentially that the degree you need to change your model is dependent on the time which has already passed. This assumption sucks. It should essentially not depend on time. What it really should depend on is the evidence which is related to the hypothesis. How many samples do support the hypothesis? If it has, or counterexamples to the hypothesis. And essentially the idea is to keep the evidence for each hypothesis, and the more evidence it collects, it will naturally become more stable. You don't make this dependent on time. Yes, the other thing I already mentioned, causal representations. This is key in our system. And what's also important, because clearly if we look back before deeper reinforcement learning happened, if we go further back to simple table-based Q learning, for instance, usually we talk about states which capture all relevant aspects of the situation for the agent. And that's also something we are not after when we talk about these causal representations. We are after something which we call statements, which describe partial aspects of a situation, which can be subject and predicate in these causal representations. And of course, that's closer. It has some resemblance also with what happened recently with deep neural networks. Like if we have a latent space which is learned, which can summarize relevant information, task relevant information, then that's closer to what we want. So there's good. Clearly, there are some work also in machine learning which goes more into this direction. There's also a Bell's work on causal reasoning, which we think is relevant and also related to what we are doing. But you will see there are some differences which you might find interesting. So actually, today we have already seen a few examples which are done with, which have been successfully tested with our reasoning system. But I think I might actually make a different approach here. Instead of showing you the things we have done with the reason, I think at this stage, because I talked about causal representations and course, it's actually better if we dive into this right away and talk about the experiments later. Peter, how much time do I have? 15? Okay, that's sufficient. So we will now dive into a concrete system which features the things we have, which I described. So we are talking now about the non-axiomatic reasoning system, and it was proposed by Dr. Wang, and it operates under the working assumption of intelligence we have already discussed, and which, of course, finite processing capacity, allowing new information to flow into the system at any moment, and real-time operation. So it's not possible for this reasoning system to get stuck in a planning loop, and then you don't know when this will terminate. That's not what we are looking for. It's a real-time reasoning system, which we assume like 10 or ideally 100 of events incoming in each second, and needs to figure out how to act. And the logic this reasoning system uses is very different than what we have traditionally. You will see some resemblances, like there are certain relationships which have been used in traditional or good old-fashioned AI system or role-based systems, which we also find in this reasoning system. For instance, inheritance statement, essentially describing that one thing is a special case of another. Key difference to traditional reasoning systems is the semantics here. It's essentially cat and animal are not like a symbol which somehow has a reference to some outside object or set of objects. Or essentially what we describe as cat and animal here, in this case we use these terms, but what it really is just an invariant pattern in the stream of events the system receives. And so there are certain perceivable properties which we encode, like here cat is meowing, but what meowing really is, in this case we gave it the name meowing, but this system does not assume there's some such a thing as meowing. It's sufficient that you have a certain, like, you could even plug a self-organizing map to FFT output, and then you have like different winning neurons which you can attach to ID1, ID2, ID3, ID4. All that matters is that similar sound will generate events with the similar ID, with the same IDs. And that's how this looks like. So the semantics here is we don't have a direct correspondence between symbol and something in the outside world. These terms, as we call them, are really just invariant patterns, and which the system can relate in various ways. The ways it can relate them have some resemblance in what has been tried in the past. Some useful representations like implication relationships, which is the heart of the causal representations the system uses. For instance, if in one time point you have lightning and then a few seconds later you get thunder, it would be good if the system could build a hypothesis which says, okay, if I see lightning, then thunder will happen in a certain amount of seconds. And these representations can also be nested, which is especially important since there is essentially not such a thing as cat usually in our system. It's really just a composition of properties, like how does a cat actually look like, what sounds does it make, and so on. Multiple properties, not all of which are usually present in each moment in time. So we don't define what a cat is in this reasoning system. It's simply a pattern which occurs as a certain grouping of patterns. We will see more of this later in the hands-on part. Yes, and traditionally, usually hypotheses in a reasoning system are not even hypotheses. Usually they are called facts or knowledge. And we agree with the term of knowledge, but not with facts. In our system, there is no such thing as a fact. We don't have hypotheses or facts that are true and facts that are false. We don't have this. Instead, each hypothesis has positive and negative evidence value attached to it. And based on this, we can define like frequency value, which might remind you of probability. The difference here in the definition of frequency is that we do not take the limit here, limit of the amount of total evidence, W plus W minus. We don't take the limit here because the system can never have infinite experience. And so we don't even claim that this is a probability. And of course, if you build systems which use probabilistic inference, then you need to make sure that you collect enough samples so that this ratio will be close enough to a true ratio so that the inferences you make will actually be valid. But since we don't assume that this is a limit, we will see there are some differences in how our system operates in this case. A key in making this work, in operating with this ratio, is to not only keep track of the ratio, but also keep track of the amount of evidence that has been collected for the hypothesis. So it's actually not only capturing ratio, but also, for instance, if we have coin flips, 10 coin flips, we get 5 heads, then the system will have the same frequency like in a 100 coin flip 50 heads case, but the confidence will be different. Frequency will be same, 0.5, but confidence will be different. So this system can not only represent the ratio, like success ratio of a predictive hypothesis, it can also knows how many samples it has collected, because this is at the heart that we don't have learning rates, but the confidence is what makes the hypothesis more stable. If it has already collected a certain amount of positive and negative evidence here, then a new count addition of W plus or W minus will not change the frequency as much anymore if it has already collected. These values are already larger. It's the idea. It's quite a simple idea, actually, but not studied. I mean, not many AI systems use it, actually. And we can use this definition of evidence values or frequency and confidence to do the following. For instance, to have a system which learns predictive hypothesis from event streams. Let's say you have an event sequence ABC, and then you can hypothesize, why did C happen? Why did B happen? And essentially, if you have this event sequence, you can find positive evidence that A leads to B, and you can find positive evidence as well that A and B together leads to C, and you can find positive evidence that A leads to C. These hypotheses all have the evidential support of these samples that we have here. And yeah, so at this point, it's hard to say what is the right reason why C happened. So we simply let this hypothesis to coexist in the system. Of course, it cannot have infinite amount of unbounded amount of hypotheses. So at some point, it needs to know what to forget and what to keep. And simple thing, we keep the hypotheses which have a higher frequency and confidence, some weighting of frequency and confidence, essentially. And so that the more successful hypothesis will remain in memory. And now the interesting thing is, how do we actually make the system figure out the actual cause for an event, if there is such one in the particular example? And the key here is to collect negative evidence when a hypothesis fails. So essentially, the idea is always hypothesis predicts correctly, good, positive evidence. Hypothesis predicts incorrectly, negative evidence. And so that's essentially what we do. So if A happens and B will not happen, then hypothesis A leads to B will receive negative evidence. And at some point, if you repeat this and you have an event stream, you will end up with certain hypotheses which predict more successfully and have also more samples their evidence is based on. So it's like each hypothesis has its own data set. That's one way to look at it, or almost. And in this case, we can also say that the frequency value we have seen actually encodes the prediction success ratio of such a temporal implication, and the confidence encodes the amount of samples seen so far. And now you might ask how to get from this correlative representation to a causal one. And we have a very simple view on causality. It's simply that, let's say we have this A and then B leads to C. What about A and moving to the left leads to C? A and moving to the right leads to D. So the idea is simply to use this, like the end of the sequence on the left-hand side of the implication can be an operation. So we end up with this idea of schema, Thrasher's schema by Piaget's idea that actions lead to consequences in certain contexts. And this representation is what we understand as a causal hypothesis, but you could say it's still correlative, right? It's simply learned from a stream of events. But the difference now is these events, like moving to the left and moving to the right, the system can invoke by itself. So it can actively test the hypothesis. It can actively say, okay, I have picked up this from the past, I have tried this operation in this context, this happened. Okay, is this actually, can I reproduce this? Okay, let's try again. I want to see to happen. So I execute like left in the context of A and C. Hypothesis succeeds, positive evidence. Hypothesis fails, negative evidence. Simple like that. It's really a simple idea. And we have built one such system which implementation of this idea. So we don't only have theory and philosophy, but we have a system which we try to, at least initially, it started all with learning such predictive hypotheses effectively from data. Then we extended it to allow for B to be an operation, so that it can also learn and test hypothesis by invoking operations. And we have a system which is quite effective in learning this temporal and procedural hypothesis and to test them in parallel and to learn such hypothesis from a real-time input stream of events. And what's later work, which we have started mostly this year, is to try it on robots. Because clearly, if you want a robot to be autonomous, ideally it would be quick in picking up new temporal relationships and new ways, new behaviors that lead to certain outcomes. And so we we are very certain that this technology we have here will be a game changer for autonomous robots, and we are initiated the work in this direction. We have submitted one conference paper now, which I will talk about on Monday, where we show some robotics experiments of having this system work in action. What's also important to us is there's also often in the AGI community, there was this thing, do we need deep learning, or is deep learning the wrong approach? That's not what we see. We don't think that that deep learning is wrong or something like that. Instead, we try to utilize it in combination with our system so that we can tackle practical problems. So for instance, our reasoning system, we don't have a good solution for visual object detection, for instance. But how can we apply our reasoning in the real world if it cannot see objects? So we are very grateful that there are very effective deep learning models which can solve such challenges like perceiving objects, detecting objects, and estimating the depth from camera input, and so on. And so our approach here is essentially to use these models to generate event streams. Like if you have an object detection model, give a bounding box and class information of the seen object in every frame, and just string it into the reasoner and let it figure out temporal relationships like movement of the entities it perceives, movement of the bounding boxes, and so on. So that this is our approach, that we essentially how to say, we try to combine the best of both worlds, and I think we have a strong point that that's a very good thing to do, because it's, of course, it would be easier to just go into our own reasoning camp and say, yes, we want to solve perception as well with our methodology, but don't get far, at least at current stage. So we are very pragmatic in that sense, and we are very open to combining techniques in a way that the strengths of techniques is exploited for the particular use case. So that's our philosophy. But if we look at the reason, of course, this learning from event streams is the thing we really want to push, and the thing which really drives our research endeavor to make this really strong and robust and practical. And ideally, it would lead to a system which can extract sensory motor contingencies. This is essentially the thing I showed you. Under condition A, operation B leads to outcome C, for instance. These are sensory motor contingencies. And if it can learn this from event streams, then it can combine this, can chain them, can essentially use them to reach outcomes. So now, how is this actually done? And now we get to a diagram which looks simple at the beginning, and you might say, okay, we can always draw a block diagram, but do we actually have the details of each of these components? We have all the details. And what do we have here? It's essentially what we see here is three different reasoning paths, which we found practical to handle separately. One is for temporal inference. It's all about building these temporal implications we have just seen. One is for procedural inference, like deriving a subcore. But we will come into this. We will see this in detail. How much time, Peter? 5 minutes? Pardon? But I'm almost, maybe I will finish the temporal and the procedural part at least 5 more minutes if it's so we have the details for this. We will later go into the details of each of these blocks, what it's actually doing. For now, since there will be a dedicated session on this, for now I will simply give you an overview. So there's one reasoning loop. So let's look from input to derivations. So there are certain event providers. This can be a convolutional neural network which feeds us with bounding box events. Can be microphone, which with a self-organizing map at the end, which gives us IDs, which enters events whenever a certain sound is detected, for instance. This now goes into some priority queue, which where all the events are essentially ranked according to priority. Now the question, of course, is what is priority? How do we decide priority? We will see this in detail later. So this is central attention buffer of the system. Highly ranked, or the highest event is always selected in each inference step. So inference step is now, usually we have like 100 inference steps per second. We select an event from the priority queue, which has the highest priority. Then we select certain amount of concepts which are relevant to this event. Now the relevance is dependent based on the free inferences. This is why we have free inference buffs here in the picture. For temporal inference, which we already talked about, the key here is you pick an event which happened recently. Essentially, what we use here is a currently pragmatic approach. It's like a temporal window in the concept memory, which looks at events. So each event forms a concept. We look at concepts which have been matched by an event within a certain time window. So of course, at some point, we might want to extend this to not be limited with a temporal window. But to some degree, we didn't find this much of a limitation because it can change this hypothesis later in the subcoding step. But anyway, it's we select a concept with a related event which happened recently. So that, like, we have an A which happened, it formed a concept. Then B enters the system, and we select B from concept memory and do temporal inference. If we look at temporal inference, it's simply the cases we saw before. Like if we have selected A as an event, we have selected concept B, which corresponds to a recent event that happened, where A happened after B, say. Oh no, in this case, B happened after A, so we can find positive evidence for this hypothesis. And also, if we already have such a temporal hypothesis, what if we select event A and we select temporal implication here? Then we can use it to predict B with a certain amount of evidence, which is determined by the amount of evidence the hypothesis has already collected. And what we also can do is we can group events. Event A and event B can be formed into a sequence, which itself is just essentially an event, which the system can then again pick from the attention buffer in order to build temporal implications with structural components. Essentially, A itself can be a sequence of events. And I will later talk about Gorling, but this is just to give you the first full picture, because I've talked all about learning temporal relationships. And this is essentially this inference loop here. Event goes in, we select the highest priority event, we select related events which happened recently, and we form this temporal implication in order to derive new evidence for this hypothesis, essentially. So later we will talk about the other inference paths. I will now give the microphone to Peter. Right, or is it? Oh, what is on the scatter? Oh, okay, then it's your turn. Yeah. Exactly. I will later go into the details of how our GORs derived and what's the fuss with declarative inference. Why do we need this? What is it? When we want to build a sensory motor reasoner, why do we want this kind of reasoning in addition? It touches on what Robert Johansson has shown today. Oh, Are there any questions regarding the stock and also reasoning in nature?
Hi.
Oh.
There's one thing about this diagram that immediately springs to mind, and was occurred to me in a previous diagram, is you've got inputs, but where's the output? Where's the reaction to the events? You update internal memory, but where do you do something? And that gets back to the previous slide, where there are goals further back. I think it's forward. Anyway, where goals are introduced, but where do goals come from? And that's in turn leads to action, because any number of goals could be created.
That's a good point. It's the stance we take here. Let's say we build a robot. Their goals can be twofold. One could be, for instance, based on internal needs of the robot, say battery level. When battery level gets low, ideally we would want the robot to figure out a way how to reload the battery. So there is we take the stance that goals can be intrinsic based on the body needs. And additionally, of course, if we want to build a practical robot, there might also be some higher level goals, like reach a certain destination where a certain object can be seen. So goals can be either intrinsic based on the body of the robot, but can also be, of course, with this system we are quite flexible. We can also have higher level goals, inject higher level goals, which might be more relevant for practical purposes.
Okay.
I think there was one more question in the audience. Is there work on social cognition and more specifically theory of mind aspects in NARS? Yes, as to some degree, what we want to explain also with this system is learning from observation. And we will later see that we actually have a way for the system to represent differently its own actions and the actions of other agents. Of course, there's always this additional problem. How do you generate events with these representations from the observations of other agents? It might well be that in the case of the bumblebee, we have seen before that there is intrinsic machinery in the bumblebee which is able to detect their own kind in a way that the actions of the other individuals can be transformed or into a way that they translate their own actions. So essentially that's what we also try to do with our reasoning system, that we have a difference in representations between own actions and actions of others. Also able to generalize that, okay, if different actors or even actors with 2 legs might open the fridge differently than actors with 4 legs, just to give a particular example. But we also try to do this and to make it explicitly represent itself and other agents. But we don't, personally, I did not do much work in this direction yet, but I will be able to show later that we can do this, also with particular example. But a theory of mind extends far beyond this. It's amazing the kind of knowledge we represent about other agents and their goals, so that, for instance, if someone struggles to open a door, we will immediately infer the intention of the other agents. There's a lot to be explained in theory of mind, which, yes, we might have an answer, but we didn't do much work on it yet, because our key aspect, at least for me, between 2014 and 20, was all about making temporal implications really effective in this system. And then more recently, we have talked about, yes, let's create a reasoner more, let it create more abstract hypotheses, like relating different temporal implications via implication relationships, like the cases Robert Johansen has showed, which seem to be very relevant to higher level cognition. Also there, our work has just begun, but we think we have many answers, but there are also many things we need to work out, and also to make our implementation climb the ladder of intelligence as we would ideally want to. Any other questions? I think that's it. Your turn. Is it temporal design? Okay. Is it full screen already? I guess, I think. Oh no.
All right. So thank you, Patrick. Thank you very much for introducing the NARS and even going into improvisation, because most of the things have to be discussed in the second half, like after the lunch break. But nevertheless, we will continue. And the next topic is basically we want to discuss the logic and tutorial behind the OpenNARS for research and OpenNARS for applications. And this is the reason for that presentation, is exactly to show how the logics there and what are the principles are working behind that, and what are the principles we've been thinking about to come up with the system as a team. So, non-axiomatic reasoning system has the three parts mainly. High-level three parts is the language, which is Narcissist. It's a rich representation, internal language of the system. It's logic. In this case, there are various sets of inference rules, also some functions, and metadata about how the system has to reason. And of course, it's implementation, because implementation is one of the crucial and very important. That's a control mechanism. This particular presentation is about Narcissist and about language and the logic. And later, the next following presentation, I will talk about the newer version, newer implementation of the OpenNARS for research. And after lunch break, Patrick will continue his detailed excursion into the implementation of the OpenNARS for research, which is a C-based. Well, before we come up with a general reasoning system, we want to really understand what's an intelligence. We have to understand what's intelligent, because what's the goal we have to really pursue? What's the objective? And then we have the following questions. So is that innate behavior is intelligence, or the instinct is intelligence? Probably not really. It's just a reaction on certain conditions. Then we ask themselves, this exhaustive search, which is a brute force, any brute force algorithm, is that intelligence? Wait, well, one may think that probably if we can iterate over every possible example, every possible situation, that of course we can find the solution, the optimal and the absolute solution to any problem. And he would be right, that's true. However, in a given state and the word representation, there is exponential, even factorial number of descriptions which having resources, or which having limited resources, is impossible to iterate and search for. So that's why all the exhaustive search are only working on the limited environment, and which we cannot consider to be an intelligent, because there is no adaptation to changing in environment. Now, if we have, for example, statistical information retrieval, like all the database, I don't know, NoSQL graphs, is it really intelligent? Also, no, we don't think so, because it has a predefined system, like predefined statistical models, which only behaves on that and doesn't have a knowledge representation and a decision making. Now, we can work on like currently in the trend, like everything is AI. There is like lots of appliance, refrigerators, they all are AI. But what they do, they just do the routines. Is it intelligence? Also, we consider them no, because they're pre-programmed. Even if algorithm is extensive enough, it just have to encounter for all of the conditional cases such that follow them. It's a designer who is in the first place. It's not the system who is making the choices. It's a designer who made the choices for the system and created the control for it. So therefore, all the algorithms that follow the calculations, sorting, fixed mapping, which are designed, we not considered to be as intelligence. Second. Then what really people mean by intelligence? What different communities interpret as an intelligence? Well, to the mainstream AI, they treat intelligence as the collection of the problem-specific and domain-specific parts. So they treat intelligence as something that applies to certain domain or to a certain specific parts to solve the problems. The artificial general intelligence community actually takes intelligence as a general purpose capability that should retrieve as a whole. So intelligence, in terms of our perspective, has to consider something general purpose that can be applied to many stuffs and really cannot just be descriptions of the problem-specific domain. However, definitions of intelligence still changing, and there are still different researches in trying to pursue some objective and strategies in interpreting intelligence, and that's kind of fluid concept. Our assumption, in particular assumption of the Dr. P. Wang, is that intelligence, and that assumption is used in creating the NARS system, both the NARS logic actually. The assumption is that the intelligence is the capacity of a system to adapt to the environment and while operating within sufficient knowledge and resources. So the intelligence for us is really adaptability and how fast is the learning rate to really to make those adaptations. And key thing is that assumption of sufficient knowledge and resources, which is AICR, it means that we don't really know, and no one really knows what is coming in the future. So we have to be open for any unexpected future, for any unexpected tasks, and therefore we have to adapt and work in the real time for that. And of course, we always have the finite processing power. We have finite storage conditions and finite resources. Then we really have to think, if we are working on the AICR, so what the real components, what the framework for the reasoning system have to be. So, and then we start from the basics. We need some language, and the language has to represent the knowledge. Such a system would be a semantic representation within the system itself. And the answer for NARS here is that the Narcissist language is a very rich, extensive representation of the knowledge. Then what we have the set of rules. So how to combine the representations, how to really deal with them, and how to make derivations on a certain experience on the system. And here we use a null logic. I will cover it a little bit later. And we have that predefined number of inference rules. Also, we have the predefined number of truth functions. This can be considered as a prior to the system. That's the only that we predefine in the beginning. Everything else is basically the relation between all of this is being learned in the real time. And that's what makes NARS really special. Now, the next important component is that once we have the knowledge representation, where are we going to store it? So we have to come up with certain data structure, I would say, even place to store it. And we call it the memory. It's a main memory of the system, which we also call it experience of the system. And this is changing over time and changing in the real time. So there is no static snapshot of it. It's all evolving during the reasoning course of the system. And of course, a control mechanism is implementation, I would say, that allows for everything, for every element to function properly and allows to do fruitful reasoning and to proceed. So once we have those framework established, we totally get lots of advantages. First is the main one is a domain independence. We can apply it to many domains. It's not only for particular task. Given the limited knowledge, the system is adaptable and can learn different relations for different domains in the real time. We have the rich expressing power because the language is now can represent the knowledge in many ways in relationship. And very important, we can justify the rules and its combinations during the inference. So we can take a look after the derivation, what really caused that inference, what rules have been used. And also, it's really important in artificial intelligence, which is not the case with machine learning. We can really have the explainability in the solution. So once we have a derivation, we can explain why it was choosing. We can explain what rules have been choosing, and we explain why it was choosing in terms of importance to the system, why we chose that and not something else. And that is very important factors, given that the control mechanism is advanced enough to adapt all of the ideas present here. Of course, there are some fundamental issues here. I would not even say the issues, some conceptual understanding is a little bit different here, because under the ICAR, the system really cannot guarantee an optimal and absolute solution for a task. There is no absolute correctness or universally optimal solution anymore, because we now have a shifted concepts of the validity and rationality. Now, the rationality and validity is really the relative to available system experience. It's available to knowledge and to resources, because it's all in relation with different pieces of knowledge. We can achieve such a desired features using that understanding, as that intelligence can be general application, it can be adaptive, it can be flexible, it can be robust, and it can be traceable, which I mentioned a little bit earlier. Now, the main feature, as I said, NARS is fully based on ICAR, and that was in the design. It's in design of the logic and in design of the control. NARS accommodate both of them, logic and the control, and the logic in an original sense. It's a term logic, and that term logic is really helpful in terms of creating the efficient control mechanism for the system. So NARS feature rich expressive language, which is a Narcissist for multiple levels that covers everything from the simple inheritance, which is simple inheritance relation, to the procedural, as Patrick mentioned, to the procedural events with the execution of the operation, and really conducting the advanced planning and backward inference. So NARS has been designed as a meta level. That means that meta level of how the NARS functions, and also the object level, which is what is the knowledge of the system and how it's represented. Right. So those are main features when we're thinking about how to build the NARS. Now I'll start with the basic Narcissist language. So Narcissist is a system language for rich knowledge representation. That's an internal system for NARS. It's also readable for humans, such that reading the Narcissist, of course, it's not like in English, but reading Narcissist, we can understand what NARS is dealing about and how it reasons. So the basic Narcissist consists of terms and statements. The statement, consists of statements, and statement consists of terms. We can think that term is an atomic word, the name of the concept, like it was presented before, like cat is an atomic term, which is just a term of a statement. Now we have statement, which is a two terms, subject and predicate, for the entry-level Narcissist, and their copula in between. The copula, in this case, may be anything like inheritance. It could be similarity. It could be like equivalence. And it can be so copula is basically the connection of those. And the statement looks like subject, copula, predicate, like cat is an animal, like we discussed previously. And Narcissist language also features the truth value. The truth value can be binary or empirical. Of course, in the real-world applications and real-world implementations of NARS, the truth value is the empirical. But whenever it was started, the design process for the NARS was started, the truth value was first being binary, like true or false, and that's really attribution of the very entry-level, very first Narcissist level. Now we go into the inheritance relation, which is inheritance is a relation, which is a specialization generalization relation. Actually, Patrick mentioned about that, from one term to another, and that's a reflective, transitive, and not symmetric. So you can see it on the screen. So subject predicate, and that's the error means and inheritance, basically specialization, generalization. Like cat is an animal, cat is a special case of the animal. Now the way it is reflective is that S inherent to S is a tautology, it's always true. And this is the reflective, how the term relates to itself. The way it's transitive is that, for example, if we have knowledge of the system, cat is an animal, and again, another inheritance relation, animal is the live being, for example, so we can have a transition from cat to the live being and deduce cat is a live being. And that will be transition from one inheritance to another inheritance relation. The way it's not symmetric, because if cat is a special case of an animal, as you can see the error on the right, it doesn't really mean that animal is a special case of cat. At some point that's true, in some point it's not. And that makes the inheritance relation not symmetric. Now, inheritance relation is the very basic of NARCs, and it's present in all the NARCs levels. Any additional representation is built on inheritance relation, and that's very crucial to NARS and NARCs in the first place. So that's why I cover it here in more detail. Speaking of the entry-level NARCs and binary truth value, we can imagine that system experiences K is like set of all the beliefs, like cat is an animal, animal is a live being, for example, is it a finite set of statements. And we can call the K star, which is a transitive closure of K. That means that after we have cat as an animal, animal is live being, we can, the transitive closure will be animal is, cat is a live being, and that becomes the transitive closure of the system. Now, for the binary truth value, so the statement is true is either the statement is in the transitive closure, which is if cat is a live being, it's a true statement in terms of the very first NARCs implementation, and the other one is just if the term is inherent to itself, like if cat is a cat, it's basically tautology, it's also true. Otherwise, it's false. And you can see, so binary true or false, we really cannot apply to real world problem. That really leads us to development or expanding the ideas of that inheritance and expanding the ideas of relations. And the truth value, which is not binary, it has to do something with the evidence. Evidence is the relation of one term with another. And we can represent the evidence through extension and intension of a term. In particular, for a term here, for a term T, over here you can see in the middle, there is some set of terms which is extension of terms on the left of that. Right, there's an extension of the term T. And also for the term T, there is an intension of it, which is on the right there. So if you remember S inherent to P, here S is the extension of P, and P is intension of X. That's how it's being defined. That's theorem, of course, over here, it's easy to prove, such that for the statement to be true, that means that extension of S has to be a subset of extension of P, and vice versa, intension of P, which is follows after P, has to be subset of S. That's now we have established how we're going to relate terms in terms of their extensional and intentional intersections, and how we have to do the meaning for those relations. Now we can discuss the evidence. Take a look on the picture on the right. So there are the same subject predicate inheritance relation, and we can see that squares in green color and squares in red color. Now we can define the evidence as a positive evidence, as a negative evidence, and we can define it the following way. So the positive evidence of the system is the intersection of extensional relations of both S and P plus intentional intersection of P and S. And on the diagram, it's easily see. So suppose there are some statements or even set of concepts under that green square, and that leads to S and P simultaneously at the same time. So this is my piece of positive evidence over here, because all of them leads to both S and P. Also, another green square over here that says intension of S and intention of P also comes to some shared intersection of other terms here. It may be single terms, maybe anything. So we have the positive evidence that supports S inference P is true, representing those green statements. Green squares, and again, the green squares can be statements, can be the sequence of statements, it can be another like millions of terms here. At the same time, we define the negative evidence as such that something in the extension of S, but it's not present in extension of P. And also, if something is in the intention of P, but it's not present as an intention of S. So we can take a look at those red squares over there. And we can see that, for example, there is a term here that leads to S, but does not lead to P. So that's a piece of negative evidence. And the same happens to be if there are some in the term that P leads to the term, but S does not lead to the term. Basically, it's not an intention of the S. That's a piece, also a piece of negative statements. So we just have to add those two red squares for the negative evidence, and we have to add the green squares for the positive evidence. Having that, we can really create the total evidence understanding. So the total evidence is basically positive evidence plus the negative evidence. That's what it is. And having that, we have the relation of the inheritance statement SP in terms of its relation to inheritance and in terms of relation to its extension and intention, such that it's really meaning of that S inheritance P, it comes from the relation with the green boxes and the red boxes here. That's how we define the evidence, and that's how it helps us to define a truth value function which is not binary. Now I want to, before defining it, actually Patrick already showed that, but I will talk in a bit more details. I just want to see what the truth value means for the traditional AI. And for the traditional AI, the truth means that it measures its agreement with the reality, is meaning that how close it's to real world objective and observed facts. Of course, we can see here that it needs to be the really third party or something prior supplied to the system to judge what's the objective and what's the reality, which is not the case if the agent is self-contempt and try to independently reason about the surroundings. So the truth value according to NARS is the truth value of statement measures the evidential support, exactly like I showed you here. So support of the positive and negative evidence. It indicates how close the evidence to the system's experience captured by systems so far. So it depends on the system's experience and knowledge. The truth value of a statement can change. So it's no longer aligned against the reality, but against how much knowledge the system has. And we're going to the empirical truth value and expectation. So the truth value is basically the set of two values, two rational numbers, which is called frequency and confidence. Some ideas are borrowed from the probability here. Anyone could tell that, but the only difference that in probability we have the hypothesis of unlimited tries, which in the real world we never have it. We always have a limited concerns for the resources and limited time for trials. So frequency now defined in terms of evidence. So we have the positive evidence divided by the total evidence, and that gives us how important or how true is the statement. However, there always the confidence, and confidence here plays some of the uncertainty things. So the confidence means that the total evidence we divide by total evidence plus some constant. In our implementation, the constant is 1. And the reason for that is that measure of uncertainty, really. For example, if we just experience something like the raven is black, for example, we experience it 9 times, and the raven is some other color, we experience it 1 time. So the confidence will be here 9 divided by 10 divided by 10 plus 1, which is one thing. For example, if we experience 900 times that raven is black and only one time which raven is not black, which confidence will be much higher here. So confidence is a degree of belief for the statistics sample we can really have. And that's the uncertainty, the representation of uncertainty in the system. We also have the truth expectation, and truth expectation is necessary such that there are many situations when we have to choose between two the same statements with different truth value. That's only one case, but there are many other cases. For example, to give the importance to the sentence, and such that we need to combine the frequency and confidence together, and this gives us the truth expectations. One important thing we want to mention that 0.5 is it's total uncertainty for the system. So whenever frequency is 0.5, so we don't know if the event is the statement is true or false. That's not the case. And that's why the 0.5 actually 1/2 is appeared here in a truth expectation. Now we have to speak about how the truth value is produced. Well, truth value is always attached to the system because the system experience is the stream of statements with truth value. And in the first place, truth value gives truth value of inputs are being by default. That's a system parameter. So every input has a truth value. Of course, if we have some channel, we can override the default truth value based on whatever prioritization which happens in the channel. For example, in computer vision, if we have some, I don't know, some classification probability which is higher, it straight can go to the truth value as a frequency and vice versa. Then whenever we conduct the inference, so there are numerous inference rules. They employs the variety of truth value functions. So for each inference rules at least, we have a truth value functions that given to premises and really calculates the truth value of a derivations. And then the truth of conclusions is basically determined only by the evidence provided within the premises. So whenever we have two premises participating in inferences, the truth value is only depends on the evidence provided by those two premises. It does not really take into account truth value of entire knowledge base or entire experience of the system. So as they can see, truth value is essential to the system, and every statement except for question and goal has the truth value attached, which is degree of belief and degree of uncertainty to the certain statement. Now I want to talk about the truth functions for a second. So as I said, every inference rule has its dedicated truth function. And how do we create them? So we treated, and the truth function on the input has rational numbers, frequency, and confidences of the premises. And then we treat all of those variables, which is frequency and confidences, as Boolean operations. For combinations in premises, we decide the values for the conclusion. So we build Boolean functions used on the variables, on the variables, and then we extend the Boolean operation to the real numbers, such the T-norm or co-norm. That's actually a very common and widespread approach used over here. So if the Boolean function end, the T-norm we can do is like multiply the variables, and if it's or co-norm, so basically we can subtract 1 minus x and multiply by the not of them, negation of them. That's how we come up with the truth value functions. But truth value functions, nevertheless, are predefined and they are not learned. That's the important story. Now we can explain very few basic but very influential inference rules, and they're present in all the levels of inferences, all logical levels. But I will just cover them in the very first logical level, which is null 1, because going further, they're just more complicated to display them on the screen. So we have the three main inference rules, which is deduction, induction, abduction. There are also more, of course, but once we have additional level of logic, we just add another inference rules, which is maybe a combination of the simpler inference rules. So, for example, into the deduction, maybe many of you already know, so we can have two premises, which is the S inherent to M and M inherent to P, right? So we can create the conclusion S inherent to P with certain truth value, and that truth value based on the truth value of the two premises. That's a triangular I can show you over here. And deduction is actually the adoption of the transitivity, which comes from the very entry-level Narcissist statements. We have the example over here. If bird is an animal, so then this is the given default frequency and confidence. So then another input to the system is given that the robin is a bird, another frequency confidence. So we can arrive to the conclusion such as robin is an animal, which is sort of transitive closure we discussed earlier. And those are frequencies and confidence, which is the truth value, was computed by the truth value function for deduction. That's the how it's being computed. Similarly, for the induction, so if you have those premises as an input, M inherent to P with certain truth value, and M inherent to S with some other truth value. So over here we have the conclusion S inherent to P. S is a general case of P, and we can see over there how it's graphically represented, and we can see that example is that if Swan is a bird, again with default confidence value, the system parameters. If Swan is a swimmer, also default truth value. So then the system really deduces that bird is a swimmer, and that gives those confidence frequency 1 and confidence 0.5, because again it doesn't encounter very much details about those inferences. For the induction, we also have the induction truth functions, which is derived over here, defined over here. And again, we've been using the, it's maybe easier to understand why we do that if I could put just in terms of evidence, in terms of relational evidence for each of the premises. But we use the approach from the human behavior, common sense, and we use the approach if we want to really, how much truth we want to give to the conclusion such that it will influence the future inference factor. So that was the idea behind the truth value functions. Now we go into the abduction. It's similar to the induction, just triangularity it's called. So basically we have premises P is M, P inherent to M, and S inherent to M. Now we have the conclusion, the same S inherent to P with the truth value of abduction, which here we just switch frequency from the first premise to the second premise. And the example over here is that if the seabird is a swimmer, again, default truth value. If a gull is a swimmer, also default truth value. So the system gives us the result that gull is a seabird, and that's the confidence defined over there, frequency and confidence defined over there based on the truth function of abduction. Of course, as you have here exactly the same as previously, induction, abduction, only because you have the same input, which is default value for the truth value. Now for the revision, it's a little bit more complicated. So whenever we have two of the same statements, but they have a different truth values, what should we do? Well, I will cover in details what should we do in real implementation, but ideally we have to revise the truth value. And on the example, you see here that bird as a swimmer comes from one source and the bird as a swimmer comes from a different source. And of course, they have a different truth value and different degrees of belief. Now we have to revise that. And that's how we revise it. Bird is a swimmer, and we have the different truth value, which is computed by the revision. What it does basically, it just sums up the negative evidence and positive evidence. However, there is some problems. We have to count overlapping evidence, and I will talk about it in the next session, like in the next hour or so, because that's really a matter of the control implementation. Because there are multiple ways to implement that. Now, given that we have some inference rules, what types of inference we want the reasoning system to do? So we have the local inference. Whenever we're revising currently beliefs which are in the system, so we're really revising our experience, or we're choosing the answer given the knowledge, given the experience from the system to a question, for example. We have the forward inference, something I just described, using those inference rules like abduction, deduction, induction, we're creating the new derivations and new beliefs, and those beliefs becomes a part of the system's experience, and those also participate later in terms of defining the relation between this certain statements with other evidential support. Now we have the backward inference. That's a bit tricky. So suppose the question comes to the system and we want to come up with a statement that truly that best answers the question to with truth value as high as possible. Suppose we have that is one step. We just choose it from the knowledge from the system's experience. But what if we don't have that answer? So in this case, we have to come up. The system have to come up with a question prime, which is somehow related to the judgment, but we only have come up to that additional, I will call it sub questions. If answering by that sub questions, we can really help answer to the original question. As you can see, so backward inference is actually the chaining between the one inference step back, we come up with the sub questions, and then trying to answer that question if that sub question leads to the resolution for the question. If not, we continue the sub questioning, etc., for many things until we really reach the solution. Of course, there are many things about here in terms of implementation, which I cover a little bit later, or how far actually we can go with sub question in terms of resource allocation. What other inference is a temporal inference. So we're introducing the time to the system, and we ask the system to reason about times, which is about events. Events is a type of statements with occurrence time, and we ask the system to learn the temporal relationships based on the time interval between the events. We have the procedural inference, like Patrick already described. So we try to system to come up with the operation, and operation we need to execute such that we can reach the goal. And after reaching the goal, we have to reach some desired state of the system. So procedural learning is considered with the executing operation for the reaching certain desired state for the system. And that's the key idea, a key understanding for the planning. So if the goal arrives and we cannot really, if we don't have the operation to execute it, or we don't have the precondition for the operation to execute it, so we have to come up very similarly to the backward inference. We have to come up with sub-goal, to the sub-goal to try to achieve that sub-goal. By achieving the sub-goal, we might have some evidence necessary to achieve the main goal, which was stated to the system. I probably will go over that in the next section, how it's implemented and how we're going over that in the OpenNARS for research. Now we're going to the main components as we talked. So one have to think how to really store the data into the system, and the storage is the following: we need some type of memory or data structure. So in NARS, everything is tasks, and memory and memory and inference is basically task processing and reasoning about tasks. Task can be a question and can be a goal and can be judgment. Judgment is a piece of new knowledge. A belief, however, is the accepted knowledge, so accepted judgment, process judgment. And the belief contributes to the experience of the system. But all of that happens to the memory. Now, we have idea of concept such that memory has a conceptual relationship. As we can see, the cat is an animal previously described. The cat becomes a concept, and animal becomes a concept in this regard. And concept really has the connection between terms and tasks. And that is clustered in the memory like a graph. Very similarly, the tasks and beliefs are clustered inside the concept. So concept is a data entity. Speaking of programming, it's an object that has multiple data structures inside, which is tables, types of X, where the tasks, beliefs are stored. And also important to note here that memory cannot just be simple lazy storage. It has to be prioritized. It has to have, like, each element of the memory should have some importance. So the concepts are prioritized within the memory, and also within the concepts there are tasks and beliefs who also have importance, such that it was easy to go with the resource allocation to select the important data item necessary for the inference. Over here, there's just a very small simplified example of a network, of the memory network. If you can see the concept of bird, goal, swimmer. That's how they relate with the links, with the term links to each other. And there are truth value to them. And now imagine if that, for example, you have the thousands of concepts that are how connected the graph is, how difficult to reason with that. So we have to really come up with the idea of the deliberately pick the important items to reason about. And that's why the reasoning system, any reasoning system should have, and in fact it has more or less advanced resource allocation mechanism. In NARS, we call it attention mechanism. And the role of attention mechanism is, for example, to avoid the combinatorial explosion, because we cannot really iterate through all of the concepts in the memory to choose which one is choose which one is relevant and then start to work on that. So the resource allocation is really necessary to selecting important concepts, important items. And attention mechanism also allows to manage resources given to the system in the real time. So it's a real-time processing. That's why the attention mechanism is allows systems to stand responsive and allows the system to be operation within the system finish in the constant time, which is very important. Now, attention mechanism is also responsible for the contextual priming. For example, we select one important concept, and by selecting them, of course, we initiate the attention spread over the concepts which are connected to that, for the statements which are connected to that. And if we select the really important concept to the system, to the current derivation task, then the connected sentence statements to that will also be raised in the terms of importance. And there are high probability that later on we will select those sentences after we're done with reasoning for that particular concept. We'll try to go in more details if time allows with attention mechanisms for the second session. But for now, that's important to know that attention exists in all AGI systems, and it really controls how busy and how responsive the system is. Given that, we can define the meaning on the concept, and that's really fluid. It's meaning on the concept. If I go back over here, so meaning of the bird, for example, is really come from evidential support of its relation of how it's related. The gull, for example, here it's a swimmer, it's a swan. That relation is more important than the concept itself. It's important to note that it's always changing in the real time, for example. And the meaning of the concept for a system is actually its importance. And its importance is its priority set up by attention mechanism. So as I said, if we select, for example, the important concept during this process, during current inference step, we can trigger the raise of attention of the connected concept, and that's now changing the importance of the concept during the real time. That's what's the meaning of the concept of the system. Now, this diagram is of the architecture, general architecture for the OpenNARS. It's from the very old implementation, I believe 1.5.6, which is years ago, but it has some relevance until now. Of course, it becomes more advanced, but very general flow is still the same. So we should have some input tasks going to the system. We should have some buffer that we buffering the input task into the buffer. Then we have to pick up those. Some of the tasks again depends on the implementation, how many, and create, decompose, do some structural composition, create the concepts in the memory, put them to the memory. Of course, we have to set up the importance of the concepts. We have to set up the truth values for the tasks. After that, we probabilistically select, not probabilistically, but somewhat probabilistically, we select concept from the memory, and we feed it to the inference engine. And inference engine create the output, which is the circular here. If that output can go to the output, which is currently in our newer implementation is output channel, or it can be backfeed to the buffer, such that maybe it needs some more processing. It will be continue processing all over again. So we can see that's no closed learning here. Learning continues and continues in cycles. As I just explained, is the cycle. Of course, the control criteria, whenever we see the diagram, it has to have that, it has to operate under ICAR, because over there we always can expect the input. We don't know what comes, and we expect to process it at any moment of time. And we have to see that we have to carefully choose how we're going to store the data, because any data structure and any resources have its limits. And importantly, that, as I said, we cannot speak about efficiency if we don't define the constant time operation of the cycle in the first place. Otherwise, it becomes lousy. So while thinking about the control implementation, we have to take into consideration that constant time has to happen here. And the reason to that is because we have predefined number of inference rules, predefined number of truth functions, budget function, structural rules, that up to a certain number of them we can only invoke during the cycle. Therefore, it gives us the impression that this is the constant time operation for the for the cycle of control. Second. So over here, I want to talk about the logics. So I covered just null 1 with the inheritance relation and the truth value. There you can see there is null 2 until null 9. Current implementation is somewhat in between null 8, which is procedural learning, and null 9, which is a self-control. And with each of the levels of logic, we add some additional truth functions. We add some additional processing with each of them, such that we cover from the very atomic term of null 1 to the compound statements in null 5, through the temporal in null 7, and finally with the procedural hypothesis events and the self-control. So each of them is kind of addition over that to accommodate the changes and more advanced reasoning necessary to accomplish more advanced tasks, for example, for the compound tasks. The first order logic is from the level 1 to level 4, and basically it has the inheritance couple, as I said. It also has similarity, instance, and property. It has the compound terms in terms of sets, intersections, differences, products, images, ordinary relationship, ordinary relations, which is null 4, and sets, intersection, null 3. It has the inference rules for comparison and analogy, and it has the rules for the compound terms composition and decomposition, because in null 4 it can be 3 or 4, it can be compound terms already. Now for the higher order logic is null 5 to null 9, and it starts with treating a statement as a term. So for that we have to add additional copulas such as implication to build implications or equivalence, and those copulas are used through null 5 until null 9. We have the compound statements as a negation, conjunction, disjunction. We have the conditional inference, and we have the variables, of course. So we can see over now that NARS already become a bit complicated system. So try to not to overcomplicate it. Also, in the higher logic, we have the temporal inferences, which we treat events as the statements or tasks with the occurrence time. I'm sorry. With occurrence time. And we can learn now the temporal compositions. We can learn temporal relationship, and the tasks events can really go into arrive to the system in a sequential order or in parallel. And there we building anticipation, we making prediction, and we just see if certain event are able to be will be able to occur or not in terms of anticipations. Now for the procedural, we creating the events for the executable events for the operations, and we try to achieve the goal as to carry out the operation. And the thing is, there are two ways: either we have to carry out the operation, or we have to create the sub goal such that we can lead to the new sub goal and eventually to the final goal to be achieved by the executing some of the operations. Now, as a summary, I think we are out of time a bit. So as a summary, the NARS is fully based on assumption and subject knowledge resources. So it has a unified representational language. It has complete inferential power, really complete, is immense. It has reasoning, has learning, planning, it's problem solving, it has a decision making. And it's important that it can be integrated with the other software, and we had projects already, and it's other software and hardware well, plug and play. So we can really achieve that the different languages with the plug and play, and we can build as a complete system with the as in relation with computer vision or anything else. And we've done it in the past. Now, in terms of implementations, currently we have many implementations. Most notable here, OpenNARS for research and OpenNARS for application. We also have the OpenNARS in Python, but it's not very advanced. For OpenNARS in research, so it's a comprehensive implementation in Java, and it's used mainly for the research purposes, for where we really work on the conceptual level, not as far as for application, but you see if some conceptual understanding is correct, or we can follow it further. However, Patrick has its own implementation, which is OpenNARS for applications, implemented in the C language. It's very efficient, and that is used for the real-world applications, even for the robotics. And we will demonstrate it in the afternoon session, how it's used for the robotics. So both implementations are successful and used in other projects before, in combinations of more complex projects. And in those projects, the both implementations have been dealing with the real world problem. Now, what do you think the potential application of NARS is? Basically, NARS has never been designed for any specific applications. So it is a general purpose tool. And we really want it to be applied to the domains where reasoning under uncertainty is required, where the only assumption and sufficient knowledge resources is applicable, when the future is really unknown, where the tasks has to be explainable is a key factor, because many AI systems act as a black box with no explanation, and where the environments really require or demand knowledge representation in terms of semantic knowledge representation. I think I just be rushed for the next session. Any questions so far we have from here? So we can go to the next one, which is, I just checked it. So this is the main idea behind NARS, and those ideas are shared in all the NARS implementations, because they're very, for everything. 1 second, I have to select the, no. Where is that, Patrick? Okay. No, 1 second. The second presentation. What the?
Did we open?
No.
No? Is it this presentation?
Yes.
This one?
No. No. No.
How to exit this first screen thing?
What's
Oh, no, it didn't.
control? Okay. Why did it close?
No idea. Maybe we opened the same to this.
Once you wish to take the break, stop screen sharing. Okay. 1 second. What the? What the? How to close, Patrick, how to close the chat message in your Zoom?
Down to the bottom where you do your and then chat, hit the chat button.
Oh, okay. Okay, good. And that one?
That takes the bottom of the top of the screen. And get it out of the way.
Desktop, okay. Okay, fine. And finally, I can go to the full screen. Yeah, it's over there. Yeah, I can see it. It's good if we can use just a PDF reader, not a browser. Okay, here I'm going to explain how all the ideas just presented before are really intertwined and being implemented into the research Java version of OpenNARS. 1 second, and just to get rid of that also. No. I think I'm. It's. No, I cannot move it far. Right. So here I have that OpenRs 3.1.x because last year we delivered that version called OpenRs 3.1.1 and 3.1.2, which incorporates some newer architecture. And 3.1.3 also will be delivered soon. It has a few additions to that in terms of channel design and in terms of buffer design. And of course, some of the minor things are being improved. That's why that presentation is about all of the family of OpenRs 3.1s, because most of the strategies and most of the control and data structures and everything stays the same. So start with introduction. So we just covered language and logic, and now we're going to cover the control mechanism, which is an important implementation details. So of course I can skip that. I can skip that because I probably don't have time now. As of assumption of intelligence, I already said that this is about adoption, the capacity of the system to adapt to environments while operating in the real time under the insufficient knowledge and resources. So here we're going to focus that how are we going to really create the memory structure in terms of insufficient knowledge and resources? How are we going to really come up with the idea to, in the constant time, to really invoke all necessary inference rules, right? And how are we really going to organize everything into the control of the system such that whatever idea we presented really continue to flourish and continue to function, which is not just frozen system closed from the input. This is about the control and how to achieve that. I just covered a few minutes ago that we have multiple levels of logics, but I covered that each of them has its own narcissist, had additional narcissist rules, copulas, and truth functions. But in terms of control, some of them, like for example, from null 1 to null 4, does not require the changes in control because there's just adding on top of each other, adding new rules, adding new inference rule, or adding new truth functions. Going beyond null 4, null 5, 6, especially 7 and 8, they already require change in control. For example, null 7, which is temporal reasoning, requires some additional component in control, and null 8 is also important to note that there is some procedures for the null 6, which is a variable, for the unification of the variable with the beliefs of the system. That's also special. And of course, null 5 is still the topic we are discussing because that treats the statements as a compound statements, whole statements as a terms, opposed to just the atomic terms inside the statements. And there are many caveats here, which we're describing in terms of control, how we efficiently pre-process those compound statements. Now, types of inference just said that local inference, forward inference, backward inference, just said about how to find the answer to the question. Temporal inference, which requires special accommodation and control. Procedural inference is a way to carry out operation to achieve the goal. It's again is a special, it requires special accommodations and component in the control. Now we go to the truth value in a bit more details. So we know that truth value measures the evidential support. It's not the how true to the real world, but it's evidential support how true the statement to the system, to the experience of the system. So we have frequency, we have confidence, and we have expectations. But remember, I said that expectation is used somehow. We need to combine frequency and confidence together in the expectation. Why do we need that? For example, we need to choose the answer to the question, right? And if the answer to the question comes, there are two different statements. For example, one way is to choose from the answer which has a higher confidence. That's one way. Another thing, when we have a revision, when we have the two statements, exactly to the two statements, but they have the different truth values. We need to revise them. and assign a different truth value to the revised truth statement, right? So, but the problem here, we have to combine evidence of beliefs, and somehow we have to really deal with overlapping evidence, because we cannot really make a distinguish how much evidence each one really contributed and then subtract the overlapping evidence. We really cannot do that. So we introduced the idea here of evidential base, such that whenever the task enters the system and it enters NARS system, we assign it a serial number. Whenever task is being derived, so we create that list of serial numbers of tasks it derived from. So each derivation has a 4, 5, I know, 6, 8 serial numbers as a list to see where it derived from. Now, and how many derivations, that's a system parameter. It can be defined for different cases, but it's defined 8 now I believe. The thing is, once the two of the same statements that with different truth value are being derived using completely different statements before, that means their evidential base is different, so we can easily revise them. However, if those derivations come from the same statements, or for example, evidential base have same serial numbers in both of the statements for which we want to revise, in this way, we now have to really, we cannot really revise them, because we cannot subtract the overlapping evidence, and we have to make a choice. And to make a choice, for example, we really need there to combine those of the frequency and confidence in some simple measurement, such that we can easily and effectively create a choice. Also, the expectation is used for when we try to achieve the task. We have the achieving level. It's another metric. So an achieving level means how far we can achieve the task, or it achieved so far, and that also based on expectations of a task. Let's go straight on the control data structures. So here is the overall design of the control, which applies to all 3.1 systems. The 3.3 now features the multiple input channels, sensory channels, and has one output channels for all of them. As you can see, we have here the memory talked about already, as where the concepts are stored. This is the overall experience of the system. We have the inference engine, is where we take out elements from memory, we apply the inference rule, and we create the derivation. So the derivations can go to the output channel, or it can go to the internal experience. Those are two buffers here. There is more, actually. I'll just want to speak about only two, which is overall experience buffer. We can call it global buffer, and internal experience buffer. That's an internal buffer. So derivation comes out of the inference engine and goes to the internal buffer. Sorry, here it competes for the importance or the priority and goes to the overall buffer, and then goes back to the memory. And that is the idea of a cycle. And of course, it has to be really prioritized, really important derivation that it can survive from the internal buffer through overall buffer, compete here with input events and statement and tasks from that input channel, and then goes again to the memory. Of course, the control criteria here is the following, so that NARS has to operate on the ICAR, already talked about that, and NARS expects new task arrive any given moment. So a system should always stay responsive. All of those buffer has to spend, all of those channels has to supply the tasks to the buffer, and that buffer has to be responsive always, and it has to be ready to pre-process task and put it to the overall global buffer and to the memory. So it always has to function. And data structures, of course, we have to choose such a data structures that is bounded in size, but still can deliver us the efficiency we seek of the constant time operation. Now, let's speak about tasks a little bit. 1 second. I'll just move with that. So everything in NARS is tasks. Is a task-driven control entirely. So tasks are handled using beliefs, which is statement with truth value, and desire, which is statement with desire value. From technical standpoint, the desire value is exactly the same as the truth value. However, from the conceptual standpoint, the desires is a bit different. Desire value, it means, so we can come up with an implicit desire state, which is never explicitly present in the system, and we can create an implication from the current goal to that desire state we want. And that we have to measure the truth value of that implication from the goal to the desire state, and then and that truth value we can call the desire value. So that's desire value is basically the truth value of the implication which does not exist explicitly in the system, but it's thought of being existing implicitly. Now, tasks is always processing in the sequence of inference steps, and it's never been well, I would not say never, it's in most cases would never really be processed in full, and never been fully achieved. It's always been achieving in the cycles by certain amount given by the time slice by importance, and it always will generate some additional tasks. And NARS repeatedly selects tasks and desire as premises, apply some inference rules, and do some do some inference and provide the derivation of that. Now, the overall objective in this scenario is not to really make sure that some tasks, some particular tasks are being processed to achieving level as complete as possible, to be achieved as complete as possible, but rather to have that overall sum of achieving levels of each task. In other words, here the objective is to try to achieve as much tasks as much as possible, like the sum of their all achieving level has to be the max. So we're more trying to get all tasks available to the systems and achieve them as much as possible, all of them. And that leads us to some few other ideas. That means that tasks has to be processed in parallel, not in terms of multi-threading, but for example, one task can be processed, then it can be interrupted after n steps because the new tasks appear which are more urgent. So, and that's done sequentially, but in terms of task processing, that's actually a concurrency, because the tasks which we just stopped processing, we just put it back to the memory, we assign different importance to that. Tasks still exist in the system. It still has some importance to that, but the more important task has time to process. And thus we just switched our contacts to the more important tasks. And whenever we're done with that, if we don't have any more important tasks than whatever is there in the system we just put, we can continue working on the task we just been doing one inference step before. As you can see, of course, there is not such a process, not such a feasible algorithm, deterministic algorithm to achieve all of the tasks. Therefore, only few tasks can be processed completely because we cannot really take all the relevant knowledge into account under the time restrictions and resource restrictions. Now, there are types of tasks. It's a judgment, which is a belief. It's a question. If it comes to the system, we need to answer it. It doesn't have truth value. It's a goal. If it comes to, we need to we need to do the operations, such execute an operation to solve the goal, to state the desired system of the goal, and that's the query, similar to questions, but while question asks for the judgment with the truth value, a query asks for the desire value, goal with the desire value. So inference engine. So how much that we left? Like 15 minutes, probably. Here I want to ask that the inference engine is basically selecting tasks from the inputs, then decomposing them, then do some inference rules derivation, then accepting tasks and trigger a variety of rules and repeating that in the cycle, and then everything has to happen in the constant time operation. And why it's constant time operation? Because always we have the predefined number of rules as a predefined number of structural, budget, and temporal rules to apply to the inference. Even it can be like, large number, is still a constant number. That's why we call it a constant time operation. We go to the memory structure, which is a backdata structure. Now, the backdata structure is the structure that allows us to have the balance between exploitation and exploration. I said that there is an attention mechanism earlier, that attention really assigns the priority for each of the data item, right? And the concepts in the main memory are really prioritized based on that priority value. Well, the two main routines of the back is basically put a new concept or new item into the back. If it's already contains, we have to revise the back. If not, we have to create a new concept or new item for the back, like taskling or turning. And the other one is the take the concept or item from the back. And now how we're taking them? We're taking them probabilistically, but based on the priority of each of the items, based on the importance. Of course, if the importance is very high, so we're most likely taking that item from the bag, which is good, which is something what we want. However, there is still a chance, a slim chance, that a low priority item can be taken out from the bag, which really creates a balance between exploitation and exploration. In this case, the low priority items is basically it taken out randomly, and it's part of exploration. So main memory is the bag data structure, and then it represents entire experience of the system in forms of the concept network. And main functions of the memory is accept task, whichever we have to decompose the task and create the concepts for each of the terms for each of the tasks, and to really connect all the terms and tasks together to create that graph. And also the consider procedure, it takes out, as I described, based on priority, it takes out the concept and carry out some inference on it. Now, it's important to see the concept as a data structure itself. So it's like internal object where we have the few data structure already. So the bag for the task links. Task links is something. Task links. Probably next slide to explain what task link is. Bag of the term links. Why? Because we always need to select them, and we select them based on its importance. Also, we have the beliefs, which is the system knowledge base, system experience. We have the precondition in anticipation tables. This is for the temporal reasoning. And we have the desire table, which is, this is for the procedural learning. As you can see, the concept itself is a cluster of other concepts, statements, tasks, and terms, which are related to that. So the idea is, as we select the concept, so we don't have to look through entire memory for all of the other concepts. Already we just select the concepts and we have everything there, what leads in relation to the concepts. So all the processing and inference will be done on the items which are related to the concept and related from the task links standpoint, from the term link standpoint, and from the all others, like how much this concept is related to the beliefs of the systems, or what are its preconditions, or what the operations, for example, it has. If the goal comes, I will store all of the operation hypothesis over here to see whenever the goal comes, it will be efficiently just to query the memory as a hash table by the concept and see what operation I lead to the desired table, the desired state of the system. So this is like a self-enclosed data item that really that really part of the resource allocation idea to be embedded into the control to make the system reason more efficiently and allow to call us that reasoning happens into the constant time operations. Now I want to show the memory fragment over here, and as you can see, there are some links. So the task comes like Raven is bird, and that's a truth value there, which is 1 and 0.9, which is default. Then we have to pre-process into the memory. We have to create a concept for the task, Raven is bird, and this concept will have the beliefs inside of that. Beliefs is as I said, that's the system experience. It could be multiple of them because look, that term concept Raven is bird is being connected through different other related concepts, and therefore there may be different beliefs with the same different beliefs in terms of same content but different truth value. Also, we have to create the concept Raven, concept bird, for the task that is bird is animal. We also have to create the concept bird is animal and concept animal, right? So we have the fraction of memory which is have related concepts. Now look, we have the task links mentioned in the concepts. So task links for the Raven we just have, because it's a very simple example. Of course, we expect our memory to handle like thousands of concepts at the same time, and where we no longer can easily trace them and display them here. But for that easy example, we can trace that Raven concept Raven has a single task link from the Raven to task Raven is bird, same from the Raven is bird to task link, and same from the bird. Very similarly, bird is animal has its task link to the tasks. And now I want to say the blue ones are the term links. So Raven has a term link from conceptual raven to concept raven as bird. That's how it's being decomposed. And vice versa. Raven as bird has a term link for the concept raven. Now, they are not the single term link, but the bidirectional. And the reason to that, because go back to the concept, term links, it's also the back data structure where it's going to be prioritized by the main importance of the data item, in particular on the term link. So the priority in the concept raven for the same link can be different than the priority of the concept raven as bird, right? Like for example, here in the concept bird, we have already two term links, one to the raven as bird, one to the bird as an animal. And of course, they will have a different priority. And that therefore, the links represented that are mirrored and represented in both concepts in each direction. So this is the memory representation. Now I want to talk about, go to the main diagram and to discuss the buffer. What's the role of the buffer? So we have two buffers in the version 3.1, 3.2, and we have, I would say, 3 to 4 buffers in general in the version of 3.1.3. So you can see them. One buffer is overall experience buffer, global buffer, and another one is internal experience buffer. Now we have the Narcissist channels. Each of the Narcissist channels also in the newer design should have a buffer for the pre-processing and the pre-processing of the input tasks and the pre-prioritization of the tasks, which is one of the good idea way to do that. Also, we have one output buffer, which is very easy, just a first in, first out queue. So whenever we have a derivation, for example, it's going to be compound operation to achieve some goal. Here, the compound operation is being decomposed and then operation is being executed. Now going back to buffers. So buffer is basically current implementation is a priority queue and space restricted and time restricted priority queue. It has a duration. Duration it means that how many cycles of derivation the current item can stand in the buffer. And the reason is that it's kind of forgetting implemented in the system. The reason is because otherwise there is not much space in the buffer. It will be hard forgetting. It's very easy to throttle the system. That idea is present in the overall experience buffer, in the internal experience buffer, and of course into the channel buffer. However, the duration is different. It may be the duration is low, so less number of cycles is done in for the overall experience buffer than for the internal buffer. Now, event buffer. One rule of the one problem with temporal reasoning is that, for example, for doing regular forward inference, they have a term logic, and to do the derivations, the two premises usually, not usually, actually always have to share the term. And that limits idea of resources. So once I select the concept, I just select all the terms which associate to the concept, and I never look for the buffer what else is there, or for the system experience what's there. It's not the case with temporal reasoning. For the temporal reasoning, the two premises do not always share the terms. However, there we have to establish some time frame, some sliding window approach, for example. For example, when going through the buffer, it can be multiple events there, and we have to combine those temporal composition such that we can learn on the anticipation and predictions, and have temporal reasoning about the time. And of course, we combine based on the interval between the events. That's the role of that happens to be in the buffer in all of them. In addition to do derivations, in addition to do the task processing, the buffer also have the feature to do the event compounding. However, it's only done for the simple one, which is the predictive implication, forward implication, and the conjunction sequencing. Yes, I have probably 10 more minutes, and then we can done. Right. Later, we have one PhD students of P1 I will ask him to do the demo on the multiple channel design. Just want to say there, so the difference on the 3.1.3 is that the multiple channels have to work in the real time, and the idea is there if the input comes to the channel A, for example, which is maybe the vision channel, The idea is to prioritize. For example, if the concept is already in the memory, which is related to the input, right, related to the task, I could raise the priority of the task right in the buffer. At the same time, all other priority will be lowered in the buffer, and I will select those important ones from the buffer directly fit in the memory, and that will be fruitful for the system. Of course, there are a little bit of drawback about that approach. We also will discuss them later. Right, so that's one discussed. Now it brings us to the cycle. What we do in the cycle, we actually add results from the buffer to main memory. Then we trigger revision in the concepts. If the concepts already exist, we do the revision. If not, we create the new concepts. Now the real cycle starts with the sample concept from the memory. Then we sample the task link from the concept task link back. Also, we sample the term link from the concept term link back. That you remember. So over here, we sample the task basically and sample the term. This is a probabilistic selection based on priority here. Then we obtain the highest confidence belief, which is stored into the term from where the term link is pointing to, and then we apply the inference rules between the tasks and that high confidence beliefs from the term. Of course, we then adjust the budget for both, which is the importance for the term link and for the task link. And then we create the new importance for the derivations. And then we have to input the new derivation, which is conclusion, into the internal buffer. And that so on goes on and on. It never stops. So it never stops. It always produces derivations. It always tries to reason about derivations. And it always tries to have the time slice for the processing a single task. Then it stops processing that task because of the cycle is done. Then either if this task still has high priority, it tries to process it again. If not, it switches the context to different tasks. That's the nature of the NARS. Now, probably I will finish with a little bit insights of the resource allocations. How do we know really that what is important? How do really we select the item which is important? So, well, for that thing, we have to have certain ideas. And the resource allocation here implemented on multiple levels. First, it's logical levels, and I told you that in the term logic, we select the item is share the term. Because of the concept data structure, that's a part of resource allocation embedded into the control. We don't have to search for the. Ideally, we have to, but we can get away without it, having the control. The concept data structure. Then we have the data structure as a bag that we can really, based on the priority, we can select the item from, and then we have the entire attention mechanism in the form of budget inference, which have multiple budget functions applied in a different scenario to each data item, depending on where they come from, depending on what type of data item is that, and those budget functions are predefined, and they really define what's the importance of the items. 1 second. For the importance, we have the 3 measurements, and we call the budget value. All 3 of them are ranging from 0 to 1, as many metrics in NARS. So we have the priority, which is the short-term importance of the item. When we select the concept from the memory or task link or term link, we really look for how important it is in the short space, in the short time space. When, however, we do some inference rule and we do some pre-processing, we have to then put the same item back to the bag, back to the memory. And what do? We have to adjust the priority such that we do not want the priority to stay the same, such we do not want to only select that concept over and over again. We want other tasks participate for the resource competition. So therefore, we have the durability. Durability is the decay rate. It's like a derivative for the priority. Whenever we start process the task, we create the new derivation. We assign using budget function. We assign the priority, durability, and quality for the derivations. However, we still need to do something with the current tasks, current concepts, which are participating in the current inference cycle. So we're decreasing them by multiplying priority by durability, and exponentially that's being decayed to the quality. Quality is how importance in the item into the long term, because sometimes the item very important in the short term, we have to deal with it. But what if the item can be important into the long term? And that's the job of the quality. So such that if quality is very low, whenever the memory will be full, the low priority items will be removed from the memory, and that we do not want to happen with something like operations, for example, or something like important to the long term. Long-term events, like for the goals, for example. That's I show you how the priority is being decayed used by durability and to the power of the forgot cycles. So first we have a priority. Let's say it's default priority from the system. Now after each inference, we apply to that decay rate, and exponentially priority of the constant being decline to the extent then it's reached its quality. Well, if the memory is full enough, so I will try to remove the lowest priority items from the memory, and if that quality happens to be lower than lowest or on the rank of the lowest priority items, this item is being removed. It's determined to be not important in the long range. However, if that quality becomes higher than the lowest priority into the other elements, other concepts or tasks or term links, those items will be, of course, removed. I'm sorry, retained for the long terms. The thing is, all of those priority, durability, and quality during each inference cycle are being re-evaluated for the participating inferences, premises, I'm sorry. So we're always applying the budget functions to really compute priority, quality, and durability. Few minutes, I just say about the budget functions. So there are two ways of the budget functions to initialize the budget. It can come from a variety of things. First, it's always a default system parameter for each of them for the priority and durability, and the quality is computed by using utility function called choose to quality. Also, for the inputs, one can specify how the budget for the input events. For example, as you can see later today, so we'll have a demonstration where the priority will be basically the distance, spatial distance between the focal of attention and some other object, such that the bigger, the lower the distance, the bigger the priority. Such that the bigger the priority, the most likely the attention mechanism will pick it up and start to process it. Now there's the table of the initialization of attentions for each of data item after the reasoning. So whenever I create a new one, I have to initialize, and more or less I initialize based on what premises I had. What's importance was in the premises in the first place, was their truth value and was their importance. So as you see, NARS is really complicated now in terms of relations of each other, relations of derivation, how they related to the system knowledge and systems experience. Now, once I initialized, I have to do the inference. Every task that participates in the inference has to be adjusted. And those are basically the budget inference here, merge, activate, revise. All of those depends on the data items and used in accordance such that proportionally adjust the budget value. Now, as I said, budget functions are being implemented and predefined like a truth functions. However, budget functions is open-ended, it's open research. Still, we conducting the research on budget functions and how to really influence the better learning, better convergence on NARS based on how we really can assign the better priority, or how we can deal with either we need the short-term importance for the concept or the long-term importance for the item. That's a real research that is going on in both of the systems. Now, in the last word, I will say about forgetting, because the remaining will be the temporal and procedural learning, and those will be covered by Patrick, because we're out of time. So important thing in NARS is that forgetting. Very similar to human, although we don't want to challenge the humans or replicate the human behavior, the forgetting is necessary such that it can really lead to the sufficient memory available during the processing time. And there are multiple ways of forgetting. There is a hard forgetting in NARS, for example, when the memory is full. we cannot really accept. That's a hard forgetting. Or when memory is full, we have to remove all of the low priority items. That's a hard forgetting. However, the thought forgetting is very tricky. So one of the things is thought forgetting is when the priority exponentially decays. So over time, the priority decays, and it leads it's really reached the stage when that's very low and it's being removed if the memory is overloaded. When another thing is with evidential basis for the revision and for the choice rule, as I mentioned earlier. So currently there are 8 derivations we have to look for to really count on the overlapping evidence. But what if the derivation, there are like 16 derivations actually participated to derive the final outcome, and what if they have the overlap evidence? This we actually deliberately wanted to have a set up the system parameter of how many, what's the length of the evidential base, such that implement the forgetting the human have. We probably can we can see something in our life, but really we really can forget where it comes from. And this is what it does using the derivation using evidential base. Another one is quality. For example, when the temporal, we have the anticipation, right? And we do some temporal reasoning about that. So the positive evidence is whenever, for example, we predict event B to happen because we predicted and event B happens. But what really, how do we do the negative evidence if the, for example, event A happens, we predicting event B, but event B does not happen? How far should we wait, right? Or is there distribution we know, which of course we don't know? How far should we wait for event not to happen? And how should we capture the negative evidence? Also, if event does not come, we can have the when just the first event A comes, we right away we just can, for example, add some negative evidence in the sense that we can lower its quality, such that if the event predicted event B will never come, the quality will be decreased, and using that schema I just explained, that first event will be forgotten, and that anticipation will be removed from the system, and just save the resources for the other coming ones. I think I have to stop here because of time, and I will just welcome any questions about that. No? Was it chat? Strange. All right, then we can go to lunch, and we will probably see you at, I don't know, in half an hour. So I think we will see. The thing is, we have presenters in Europe to do the real presentation about experiments on NARS, right? And it's like 10 hours difference. Let's have 40 minutes, like, so we can have be like, I don't know, 1:30. We should be like 1:30. Anyway, let's start with 1:30, which is 35 minutes from now, right? And then we will start from you, which you will just cover temporal and procedural, and then we will go towards other projects, which is vision channel, which is new buffer design, and which is the demonstration. Okay, thank you, guys.
Yes.
I think I can unplug it now, right?
Oh, yes. I can unplug it.
Hello?
Still works.
Is anyone there in the Zoom? Yeah, like 9 people there. Okay. So this is the second. This is the second section of our workshop, and we will start with the temporal reasoning and the procedural learning of the OpenNARS for application. So Patrick will continue. We'll have a half-an-hour presentation. Thank you.
So we will now continue where we left off before. So we have this implementation, which is in C, which is mostly written for implementation, for application purposes. And as I described earlier, a key goal of this implementation was to be effective in handling temporal implication relationships, and also to handle the special case with the operation involved for procedural knowledge, so that the system can essentially use temporal implications and chain them in order to reach goals, and doing so sometimes via multiple sub-goal derivations in order to get a certain outcome achieved, because not every goal can be achieved with a single operation. Sometimes it's a chain of operation that is necessary to get a certain outcome achieved. And yes, so goal extract events, learn from event streams in real time, extract temporal relationships, and then to use them to plan ahead to reach various desired outcomes. And so if we look back at this diagram, previously I have already shown you the temporal implication relationships, which are learned in this reasoning loop here, where essentially the system gets in a new event, which will then input. This usually has high priority, so usually this then gets selected, and then it selects concepts with events which happened recently, essentially capturing events which happened recently, so that it can relate the new event with the events which happened previously, using the temporal inference, where it can either build a direct temporal implication between A and B, so find some evidence for this relationship, or it can also build a sequence using the two events, which were the selected event plus the one from the concept, to build a sequence which itself is considered to be an event, which can then also be selected, and in order to form more complex temporal implications. And so that's essentially, this was this loop. And additionally, a very important loop is procedural inference loop, because what if we already have temporal implications? What if, let's say we already have a temporal implication which says A leads to B, and then let's say A happens. So it will predict B in this inference loop here. So essentially the selection here is then to select the temporal outgoing temporal implication, so that when event A happens, it will notice, okay, there is already a temporal relationship A leads to B in memory, and send this to procedural inference in order to do this prediction and anticipate the outcome, essentially, so that when the outcome does not occur, the procedural, the temporal implication relation will receive negative evidence. That's the idea here. And another case is we want to achieve a certain goal. So there can also be goal events. Peter described the task types in OWN. I usually just call them events. So most observations are usually belief events, so they are just some pattern which is essentially currently observed, but there can also be goal events, and goal events are essentially, like Peter said, it's essentially events the system wants to happen, but did not yet happen, but it's events the system wants to realize, essentially. And so in this priority queue in the implementation, it's actually slightly more complex. We have a separate priority queue for beliefs and for cores. So to separate them so that they don't have to compete directly, because this was then difficult to get right, because if we have a priority ranking, how to make sure that the beliefs don't spam out the cores or the cores spam out the beliefs. So it made perfect sense from implementation perspective to split up the structure into two components for belief events or patterns, and then for core events or patterns the system wants to observe as soon as possible. And so this is and in this picture, essentially, dependent on how we look at this. So if we select now a core event here from the priority queue, which is of course in the separate core priority queue, then we can do different inference. We can essentially ask ourselves, or the system can ask itself, how can I realize this core? What does this mean? It essentially, the system has a lot of temporal implication relationships in its memory, and essentially it needs to pick a temporal implication relationship with operation inside, which says that under this under the context it mentions, the core will be realized. And there, of course, there are many such hypotheses. How can I achieve G under different circumstances? And only some of the circumstances will be fulfilled. So what the system actually has to answer here is, what is the implication statement? Which operation will most likely lead to the desired outcome? And that's what it does. So it's essentially looking for the temporal implications, looking for which operation most likely leads to the core. But sometimes there is not a single operation which gets you to the core in current circumstances, which is related to planning. This is when reactive behavior, more reactive one, becomes more planning behavior, when it does not have a solution to do this in a single step. So it has to plan ahead. And the idea is simply, if it doesn't have such a temporal implication relation or procedural implication relation, which circumstances are fulfilled, then derive this conditions as a subcore. And we will see how this looks like in this example. So let's say we have a kind of a causal graph with this implication relationship, that A with operation 1 leads to B, B with operation 2 leads to G, C with operation 3 leads to G. And now let's say the system wants to achieve G, and let's say A was already observed. Now, okay, let's say it selects the core G from the priority queue, and now it looks at the incoming temporal implication links to the concept G, and sees, okay, there are two links. None of them have their precondition fulfilled. There was no recent B or C event happening. So there's no current option to get G in a single decision. So what it does, it derives B and C as a subcore. Now next, it might be that it selects C first or B first, dependent on the strengths of these links. It will have different desire value for B and C. Let's say this one gets higher priority in the selected first. There's no way to achieve C. There's no incoming link. Nothing it can do. The score will be selected. It will be noticed. Nothing it can do. Next inference cycle. So usually there are like 100 per second. And let's say now it selects B. And B, it realizes, okay, there are incoming temporal implication links. In this case, it's just one. There was a recent event A as well. So, okay, in order to get B, it can now execute operation 1. This is what it does. And it expects B to happen as the hypothesis of the temporal implication link states that operation 1 leads to the outcome B under circumstance A. So it expects B to happen. Let's say it's lucky, and B indeed happens. So this temporal implication link, procedural hypothesis in this case, will receive positive evidence. It executed operation 1 after it has observed A, and B happened consequently, so this will receive positive evidence. Now, if it selects G from the priority queue, it already has an incoming link, the upper one, with a precondition that is fulfilled. So this link will win in the competition between both. This one has the higher chance to get G achieved under current circumstances. So it will execute operation 2, expecting the final outcome G to happen. Let's say it was unlucky. It wanted to achieve G, it executed operation 2 after it got B. So now it gets negative evidence for this procedural knowledge here, which says under circumstance B, operation 2 will lead to G. This is how temporal credit assignment works in the system. It's simply a matter of counting the evidence for the temporal implication links. And we also have an algorithmic way to describe this decision on subcoding process, but the example I showed you is more intuitive. So it's always about selecting the link which most likely leads to the outcome the system has selected and wants to achieve. In terms of using this system, there's maybe one thing to be said here. In terms of using the system, it's quite easy to use because all you need to feed the events are essentially, or you need to feed the system is essentially events. So some term encoding some relationship, like there's a car on the left side observed, or there is some loud sound currently heard with a certain ID from the sum or something like that. We'll just enter as events. And we can simply send them in as events. At any moment, the system is operating. And also we can always say, okay, this is what you should achieve. Like battery level is currently low. I want you, the system, which can observe the battery level state. I want you to have a full battery again. So essentially a GOR, which comes from the body of the system saying, I want a full battery. And the system will try what it can do in order to achieve a full battery. So essentially all we do is usually we enter beliefs and GORs. Beliefs, what's currently ongoing, what's currently perceived via the sensors, the patterns which are extracted from these input signals go in as events. And additionally, the GORs can come from a body, like battery level GOR, or it can also be some task specific thing, like you want a house cleaning robot with a specific task, then GORs can also encode such more complex relationships. And so essentially it has an explicit GOR representation and can derive sub-GORs in order to get its GORs achieved. So all that really matters for most purposes is to send in what's currently observed and then to demand certain events to be achieved by the system. So it's very easy to interact with the system. It will simply execute operations dependent on what's currently happening and based on what it wants to achieve actually. And additionally, we also have the ability, since there are this temporal implication links stored in the system anyway and other relationships, so we can also ask the system, for instance, how to get the light on. What would you do in this circumstance? How could you achieve turning on the light and it would give an answer according to its best knowledge, according to the evidence it has seen in the past, according to what it has seen from the stream of events it has experienced. So the interaction with the system is quite straightforward. That's this part. Peter is not yet here, so maybe I will continue a bit here. Maybe I can show some more details. So this was the overall picture. And implementation-wise, we can say, okay, the left side, the event providers, it can be different machine learning models for different processing of different modalities. It can be task-specific GORs, like I mentioned, or it can also be robotic or simulated body function-related GORs, like needs, essentially. I need water, I need food, I need battery. And yes, and from there, it's really just this priority queue, just separated between GORs and belief events, just ranked according to priority. Currently, inputs simply have a high priority set to 1, and the derivation priority. So when it selects something and it selects a related event here and derives something, then the derived result will have a derivation priority, which depends on the parent event, which was selected to derive the child event, and also on the concept priority of the second concept which was selected, or this the previous event essentially. So if we have A and then B, so we selected B and the previous concept is A. So it also depends on the priority of the concept A essentially. And also on the truth value of the derivation, meaning that patterns which are stronger, which events which stronger, which have more evidence will have a higher priority in the attention buffer, everything else being equal. So it's quite simple, this structure here. The memory structure is a bit more complicated. We see here a schema of how this is actually represented. Concepts in owner have a much simpler budgeting schema than what Peter showed with openness for research. So very simpler solution inspired by operating systems where each concept simply has a use count and a last used. Essentially, use count says how often has this piece of information been used in the past, and the last used, when was it used? The last time it was used, just a time stamp. And the idea is, when the system derives new concepts, the system needs to give them a chance to survive. This is why it cannot just be use count. It also depends on the novelty. So usefulness of a concept also is based on the novelty of the concept. How recently was it created? So it's like a grace period, a way to get around the plasticity stability dilemma, so that it gives new concepts a chance to gain some evidence and not delete them right away because the use count is low. So it's a quite pragmatic solution we use here. And also concept memory is simply ranking this according to this usefulness value, which is trade-off between last used and use count. So it's the idea to use insights from operating systems here. Yes, and else, the rest is quite straightforward. There's a difference in the selection, like I mentioned, in order to establish a temporal implication link, it needs to select an event which recently happened. This is so for temporal reasoning, that's how it selects the second or the concept for the selected event. And also for the Gore reasoning, we have seen it always needs implications which lead to the selected Gore. So some kind of incoming temporal implication which leads to the selected event, like I want light 0 to be on. So I'm only looking at the incoming temporal implication links here. So it never needs to search memory exhaustively. It has all the information local to the concept available, which makes the inference very efficient and scale up to large memory sizes. Yes, so it can essentially, this is the selection for subcores, just to look at the incoming links. And the last one is semantic inference, which has some, for instance, let's say you see a certain pattern, you see something like 2 legs and the thing has, let's say, yellow color, and then it would be good if you begin to associate, the things with 2 legs have yellow color. If all the system has seen is yellow birds so far with 2 legs and yellow color, then it will simply believe, okay, the things with 2 legs have yellow color. So it will induce this inheritance relationship that 2-legged things tend to have yellow color. And that's why it needs this inference for. And in this case, as Peter showed, there's always a common subterm relationship between. So for declarative inference, there's always a common subterm, let's look at this example. We had the example with the yellow-legged thing that is seen and it has green has yellow feathers, so it can infer that the 2-legged thing tends to be yellow, for instance, inductive inference. So there's always a common term involved in this inference. So there are different selection criteria here, which were all chosen according to very pragmatic insights. So it's just essentially free reasoning loops in this design. What else? So maybe I can know, or maybe I can answer questions first.
So, when you're trying to solve this future, do you ever wonder about the limits?
Oh, I could.
You want
Oh, mm-hmm. Oh, so you mean if it's able to apply a procedural knowledge when the instance has a certain shared property with something it has seen before? Mm-hmm. Oh yes, this it can do. It's like a form of abduction then to make this comparison, to look what are the properties, and then to hypothesize that it might be this or that. So it's a bit like in the traditional duck example. It sees something yellow with 2 legs, and essentially there might be, maybe it only sees the legs and it's occupied, and it might hypothesize that even though the feathers are currently occupied, it will have a yellow color, for instance. Mm-hmm.
So I know you can train the system. Is there another way it can just, email the real world to the
Oh. Mm-hmm. Mm-hmm. That's a good question. This also links back to the philosophy of the system. There doesn't need to be an ideal concept of a duck. For it, it's just invariances. Certain 2-legged things tend to have yellow feathers, and some of them tend to be able to fly around. And so it's essentially invariances in the system's experiences it summarizes. And of course, there could be like an auditory channel where someone says duck or raven or something like that. And then it automatically begins to form this temporal hypothesis. This label is used whenever there are black feathers on 2 legs, for instance. So it doesn't really depend on this ground truth, so to speak, but it can still associate like a label we use consistently by convention when it says something, and then it will build the temporal hypothesis. This label is used when bird or raven is used when it has 2 legs and black feathers. And so it's essentially able to correlate these events then, multimodal. Mm-hmm.
Can you freeze the system?
Oh, I'm not sure what you mean. Is it?
If we go times save the status.
That's a good question. I think it relates to prediction, right? So the system can predict hypothetical outcomes and can distinguish what it predicts from what it actually observes. And mm-hmm. Oh, yes. Mm-hmm. But what we don't have is like a way to say, no, we need to reset it to a previous state or something. It's really constantly just doing this inference loop I showed. Or it does essentially. And mm-hmm. So prediction is simply a matter of selecting an event which currently happened, and then picking a temporal implication link which says, okay, if A happened, B will happen, and deriving this prediction. And so it's just a matter of the premises which are selected. Could you please come to the microphone, because then YouTube viewers will also notice.
All right. I think it was in the previous talk that you mentioned this, that there was a window that we're looking at, right? Like to say for like temporal implications. And then if I remember correctly, you said that it's possible to like eliminate that window, right? Like to just, or at least my question, I guess, like making it more flexible so that the concept of simultaneously happening or concurrent events can be stretched from like a second in case of some events to being like, as long as it happens within the same 5-minute interval, it should be okay. Like, have you done much work, or at least like, what are your thoughts on that? Kind of like making that window a bit of a flexible thing. Thanks.
That's a good question. There are several aspects which, to some degree, of course, a sliding window is very popular in like data mining or like event stream mining approaches, and that's the simplest approach pretty much one can take. And but to some degree, we want to extend this, of course, because, for instance, certain events are predicted by the system, some are not predicted. So some are surprising according to what the system previously has learned. It can actually predict some events before they happen, and others on the other hand might not be predicted. So we're experimenting with curiosity. We have a branch of the system which which highly influences the priority of input events based on the degree of how much evidence is there that they will occur. Essentially, the system's way to measure surprise. And this turned out to be very effective. It will likely go into master after some more testing and tuning. This was one thing. But there's still, even if it notices surprising events, there's still this limitation currently with this temporal window. And of course, to some degree, it would then make sense to not use the window, but only look at the concepts with high priority. But this then also needs some kind of priority ranking. So there, or some kind of additional priority of concepts so that it doesn't have to exhaustively search for surprising events that recently happened, essentially. And so there are some implementation challenges which are there, which we need to resolve. There's also this thing, it's one thing for an event to be surprising, it's another thing to be core relevant. Will it lead to something the system desires to achieve? This is also a case where we want to attach higher priority to this, to the concept. To some degree, it already does this thanks to the subcoding. Like if it goes from here to here, it now this concept will have higher priority because it wants to achieve G, and they have been identified as ways to get G. And so to some degree, there's already a way to raise the priority temporally. And to some degree, there's also a way to overcome temporal window, but not in the formation of the links, but of course it can chain links. And because it can chain links, can essentially, temporal window is still, for our practical purposes, most times 5 to 10 seconds long. And if it now chains a few of them together, it suddenly can go to a minute scale. So it's to some degree, there's also this open question: how long need this temporal implication links, which are derived from the sensory motor input? How long do these timescales actually need to be? And there's also a lot of evidence that actually in the brain that there is a distinction between the short timescales, short temporal learning via spike time dependent plasticity, versus our quite high level representations of events, which is very poorly understood. And so what I'm covering with implication links is mostly the short time distances. And of course, then the question is, how can we form longer time dependencies and how to model them? I think there's a lot to say about the structure of knowledge, which can enable, because each nodes in this system are essentially not just atomic IDs usually, but have some structure like yellow 2 legs. There's a compound. And so there are some ways to get around some of the limitations by also taking decomposition and so on into account, which we haven't fully explored yet. So there's still a lot to do here. I hope.
I think that was really good. Just something you said in the end of there. Like, there's one thing to say that those two things are
Mm-hmm.
in terms of time and things that happen in a certain decade that consider happening at the same time, but that doesn't have to be.
Thank you. That's a great question. Are there any other questions? Sure. Sure.
This one is about, I guess I should have asked it when the relational frame and everything was being presented with the symbols. But so figuring out what subset of the rules is necessary to really reach a certain goal, right? Like, it seems that, like, what is the criteria? Do we have a clear understanding of, like, by what criteria do we judge? Do we need to add another rule? And what kind of rule do we need to add? Or do we need to subtract? You know what I mean? Like, because I think there's something to be said about there's experimentation. You can try this rule and try it against a certain test case and see if that works. But what is the guiding kind of like idea behind this? Like, how do you even figure out which ones to look at? To like add and remove, and the way that it ties, at least in my head, about with RFT is like maybe that provides you a guiding kind of like framework grounded in psychology into, and you're like, okay, well, we want that functionality, like the symmetry, for example, and you test the systems, like, do we have this? Like, no, and then you analyze. Is that the process? Like, I guess, how do you figure out what is the set of rules necessary to reach, like, when we say this, like, okay, you know what? This is a good kernel. This is a nice baseline. It does everything we want. Is it just a matter of a bunch of test cases and it's all passing? Or is there some kind of a guiding theory behind choosing what rules and how to add them?
Good question. It's to some degree, there's also to keep also the audience with me, there's also this difference between inference rules, which are innate, which are not learned, and of which only a couple exist, and we think need to exist, like temporal induction, temporal deduction. So it's a very fundamental inference rules, which essentially correspond to ways to build and utilize temporal implications and hypothesis, essentially. So this inference rules, we don't usually expand them. We haven't seen much evidence yet that NARS needs new inference rules, even though the logic was proposed in 2013. We have not encountered a single case where we found the logic to not be able to handle a specific case. So the logic is very both expressive and powerful in inference. But there's this other thing, of course, object level knowledge, like what representations can it actually build? How can it utilize the logic? And the logic is quite flexible. It does not dictate under what circumstances a certain conclusion should be derived. Yet the inference engine needs to make decision on what to pick, what inference to make in order to get a certain goal achieved. And there are some principles like, yes, we have this different kinds of knowledge representations. And then, for instance, for this temporal implication structure, we have found very effective memory structures which allow to derive subcores very effectively. So it's so in this case, so like a subset of representations the logic supports, and we found ways to make this subset of representations very powerful. But in terms of what representations we actually need, yes, there's this Piaget idea of schemas, precondition, action, consequence, or pre-causal representation almost. And then there are also other representations like Robert Johansson showed today, where there's an implication link from one sequence of events to a temporal implication, suggesting that if a certain sequence of events is perceived, you can derive a certain set of behaviors from it. And that's a representation we haven't really dealt with a lot until this year, actually. And even though the logic always supported it, but how to control the formation of this hypothesis, the evidence accumulation of this hypothesis, and the usage in the cases where it needs to use them. And generally, the approach is it should just build many competing hypotheses, but it also needs to make sure that the evidence accumulation and so on is effective enough so that the relevant and the good hypothesis will survive while the bad hypothesis will receive a lot of negative evidence and ultimately be forgotten and replaced with better ones. And so in short, yes, there are some representations which we found to be very relevant, some of which were described by Piaget a long time ago. And then there are representations which we just recently found, which seem to be related to higher level cognition. And we tried a lot, but these representations seem to be mandatory as well. And even though the logic always predicted that, always had the rules necessary to build them, it's another thing than to build the inference engine, which can actually build this hypothesis from a ever ongoing stream of events and then effectively build, maintain, and utilize them. And for temporal implications, I think we are there. Even though also for temporal implications, there are hard questions like, what if you have a hypothesis A leads to B? When will you attribute negative evidence to it? Intuitively, when A happens and B will not happen, even though the hypothesis predicted it. But how long will we wait? When do we say, yes, the outcome did not happen? Real world timing does not behave in a very, maybe for some simulations, but in real world, maybe one light switch has an energy saving lamp and it takes 1.5 seconds to turn on the light. Another says 2.3, another says 0.5, another has practically 0 delay when the switch is pressed. So essentially it needs to be tolerant to timing variations. And there are many systems in literature which try to encode the idea of a schema, like Trash's schema mechanism, which I think was proposed in 1985 or so. And the only thing which probably hampered it from being successful is that there are some difficult problems, like how to handle timing variations. And for us, it took a few years to get this aspect right. And I think we're on the right track because we have a model now which is very resistant to timing variations. And essentially, the idea is to capture the, it's still a simple solution, but essentially the idea is to, like when it perceives or when it builds a certain temporal implication from the events, each event essentially has a occurrence time marker attached to it. And essentially it knows the distance between the events and then can, for instance, average the timing. So if it already had temporal implication A leads to B with 2.5 seconds, and now it gets a new temporal implication from a new pair of events with A leads to B with 0.5 seconds, then it can actually revise the hypothesis, and the timing will be weighted based on the confidence of the hypothesis. So the hypothesis, which has more evidence accumulated already, will mostly influence the timing of the conclusion of the summarized result. So it's a way to make the timing estimation dependent on the confidences of the hypothesis, so that if there's already 100 light switches which activate in between 0 and 2 seconds, then okay, if you now have another light switch which for some reason needs 10 seconds because it's a broken lamp or half broken, then it will not adjust the timing a lot, essentially, because the new observation is just a drop in the sea of evidence. Peter, you can continue. I thought you were outside of the room. I did not say. Pardon? Is Adrian already in the Zoom room? Adrian? Oh, yes, actually.
I'm here. Yes.
Hey. It's your turn. if you're ready.
All right.
Now Adrian
If you let me share my screen.
will summarize his research regarding using the system for grid-world environments, and I will give
That's
the
right.
green red to you. Thank you.
All right. Okay, I'll have to reconnect. Let me do that quick. Okay, I'm back. All right. So this is my presentation about basically some exploratory work around training agents controlled by NARS, specifically open NARS for applications for various tasks in grid world environments. The entire focus is really on a single environment, as I'll explain. So first of all, a little bit of motivation. Why use grid worlds? Well, they are discrete 2D environments, so pretty easy to work on. It's all deterministic. With the particular framework I'm working with, they can be totally or partially observable. In this case, they are actually partially observable environments. There is a potential for generating levels procedurally. There are libraries like that provide this kind of functionality. And they support a wide variety of tasks. So there is a bunch of these already implemented in the Gridly library. And it's pretty easy to implement more of those. So Gridly is a pretty cool library that is kind of an engine for making those grid environments. It uses YAML files to describe them. And you describe both the layout, which is just characters. Each entity maps into a character. So just write a bunch of characters to construct a level. So adding new levels is very, very easy. and you describe the mechanics of the entire environment. So what kind of entities are there, and things like what sort of observations and actions the agent can receive and do. It's very efficient. It can do 70,000 frames per second on a single thread. Provides familiar OpenAI Gym API. It's a flexible environment where you can process incoming frames in various ways. You can either do computer vision with sprites or simple sprites, or process vectors that have already discrete representation of what's there. And it even provides semantic state that is very convenient, because initially you can just bypass this completely and use the JSON description, basically, or dictionary description of each state to your liking. Additionally, it provides event history, which is also useful for certain things like tracking whether some item got picked up, etc. It also has pretty good documentation, which can be hit or miss with these kind of libraries. So what do we need to connect ONA to Gridley? There are two main things. Pretty obvious. You need a translation layer that takes raw perceptual representation and produces appropriate NARS statement to be sent. So in the previous implementation, of course, I worked with semantic state. So it would take and filter all the relevant objects from that, and also using some further logic like filtering would narrow down them to the items of interest, and that then would produce statements that would be sent to ONA. Currently, I've switched to finally using proper observations, just converting from vector observations. So after ONA outputs an execution, as this is the main thing that I'm interested in here, it's all about executing operators. That, of course, need to also be defined at the very beginning. They need to be extracted from the textual output and converted into appropriate IDs that are sent to the Gym API via the very familiar step method. So the environment that I've used for this particular, mostly for this particular work, is called Drunk Dwarf. It is basically a port of the minigrid Dorrent key environment. There are some differences. I think mainly the one that it provides the rewards after picking up the key and door, while I think the minigrid one is more sparse in that it only provides the reward at the very end. Actions are moving forward and turning left, right. So this is an actual environment where the agent has certain orientation. It can face different directions. So it doesn't, you can't just move directly in all cardinal directions. You have to manage that. The vector observer for that environment provides a 7x7 grid centered on the agent with orientation tracking. So if you process that, it's always going to have, it's always going to be facing frontwards, and it's always going to be roughly centered on the agent. Rewards are +1 for all the intermediate and the final
goals. So picking up the key, opening the door, and reaching the bed. This is all plus 1. So the maximum reward you can get from a single episode is 3 points. This is pretty good environment for testing things like following hierarchical goals and curriculum learning. Additionally, I made an extended environment by adding some reduced levels that are simpler than what is shown here. What you can see here, by the way, is the first level. So in the original environment, this is the lowest difficulty level. There are higher difficulty levels, and they are, of course, larger and can feature some more objects. I think latter, like the highest 2 difficulty levels, have a bunch of other items like bookshelves, tables, etc. But in the extended one, I just added additional levels that I wanted to use for additional curriculum learning experiment. The setup for experiments is usually that I run these for 50 episodes. Each episode is capped at 100 iterations, so steps. If the agent doesn't manage to finish the level in that time, then it just gets reset, and the reward that it got is kept. So whatever it managed to achieve before that reset happens, that counts as the reward it got. Additionally, I do note whether agents complete their levels or not, and I track all the pretty much straightforward metrics that you can track from this. So the total reward, the rewards per episode, the average of that, most importantly, the completed rate. So the ratio of times the level actually did get completed. There is usually a little bit of background knowledge used, but it's mainly the goal structure, which I will show off in the next slide. There is usually a simple background statement that moving forward to something that is ahead of the agent is going to reach the object. But I don't think it actually matters that much in experiments. It wasn't super impactful, while the goal structure was actually quite useful. And in the later experiments, I started testing more hyperparameter setups. And there are 2 main hyperparameters, which is initial motor bubbling and the decision threshold. So motor bubbling rate specifies how often, if the agent doesn't have an appropriate hypotheses to use for a decision, whether to just perform an action at random. Over time, it goes down. And decision threshold determines what is the actual truth expectation on a hypothesis, that the hypothesis has to have at least its truth expectation at least this high to be considered for executing an operation. So what is the goal structure that I used? When I wrote it, my guiding principles were to make a simple structure of goals that is hierarchical and fully declarative. As you can see here, the actual goal that is used is the completed goal. I haven't actually done any experiments with got reward. This is more of a an auxiliary goal. I haven't used that one yet. It obviously gets triggered every time the reward is greater than 0. So a positive reward triggers this. The completed goal is the goal that is demanded on each iteration. And it is expressed in terms of achieving those subsequent goals. Specifically, the completed goal is door opened goal plus reaching the bed, while door opened goal is got key plus reaching the door, and got key is just reaching the key, because reaching the key picks up the key. That's another difference with the original mini-grid environment. So here we do not pick up objects. This just happens automatically when the agent enters the tile with the key. Similar with the door, when the agent has the key and tries to enter the tile with the door, then it gets opened. And as you can see, the object reached property is the kind of central property that happens when the agent reaches any object, and it's used for all these goals to stack them hierarchically, with each one being basically adding another object to be reached. Additionally, like I said, I do track rewards, and this can trigger the got reward because rewards are always positive after any of these goals is triggered. Then in practice, got reward always gets sent after got key, door opened, or completed. And it's always sent last. And that's why these dashed lines here, because it's not a direct dependence, it's more like a self-dependence. And using those goals is, like I said, impactful. Without them, the agent didn't really perform all that well. I pretty much had to use those in my experiments to really get anywhere, get any kind of promising performance with it. So what is the rough summary of the results? I had quite a lot of runs. I have close to 100 runs at this point in my Neptune dashboard. So the usual result is hovering around 25% completed rate. Depending on what sort of change I was testing in the code base, it could range from 4 to 40%. Specifically, those 40% results are from very long runs that were 300 episodes, because I wanted to see how far I can pretty much take it. Unfortunately, running it for 300 episodes would take over 5 hours. So this is something I only did twice. And 6% completed rate is the random action baseline. And again, this is all referring to that level 0, this basic level from Drunk Dwarf. There was a little bit of experimentation with the next level, which is basically like this one, but it's the corridor on the left is slightly larger. It's just slightly larger. But mostly I focused on this one because in the end, I wasn't able to solve this one, so I couldn't really move to the next one. Here you can see top 5 runs for Drunk Dwarf for this. You can see their rewards each episode and their total reward. The bottom one is linear log chart with time spent on running. As you can see, there is this one run that is over 5 hours. And as you can see, the performance here is kind of plateauing. The first 60 minutes are the most impactful, really. While later on, I do not get that much. So in the end, I stick with those 50 episodes as the gold standard for how long to run those. Additionally, I had a curriculum learning experiment too, really. And the first attempt was 50 episodes on the first level, then an export of 10 most useful concepts, and the other agent would run again for 50 episodes on the second level. And that was compared against the baseline that would run from scratch for 100 episodes on the second level. And there was some gain from that, 28 versus 21%, which is a 33% improvement. However, I did not do more runs to further clarify how well this performed. Firstly, because they, again, took very long. But second of all, I was just moving on with, I was just iterating more on representations that were used to encode incoming perceptions. And there was just no time to test this again because things were just moving around too much. And the second, more recent setup was inspired more by Patrick Hammer's experiment with Minigrid that is in the master branch of ONA. And it uses those easier levels that I introduced before. And pretty much I add this kind of preschool setup where there are four more levels that are before the first original level from that original environment. And the agent here runs continuously. So it runs for 50 episodes on that first level, 50 episodes on the next one, and so on. Unfortunately, in this case, the performance on the final level dropped to the usual range. So I think in the last one, it was 26%, so pretty usual. So there wasn't really any gain here. Now, to discuss hyperparameters a little bit more, in later experiments, I started treating motor babbling rate and decision threshold explicitly as hyperparameters. These are pretty much currently the only two relevant ones because I'm transitioning to a different way of processing observations. The default ones from the config.h file are respectively 0.2 and 0.501. Motor babbling was not very impactful, while decision threshold was actually very useful for those easier levels. Bumping it up helped considerably. Going up to 0.7, in fact, allowed to very easily 100% the easiest, almost trivial, but still not so trivial for ONA level of extended drunk dwarf, while 0.6 was a better compromise, which actually I can talk about here more. So the levels you can see here are the additional levels I made, and the final one is from the original environment. And most interesting observations I got while looking at the very first level, because it wasn't that simple to, it wasn't straightforward to get it to reasonable performance, which is really pretty much 100%, maybe like 90-something% completed, right? And increasing the decision threshold helped here. And I do get into more details about why that was probably the case. But as you can see, the idea here is to progressively make this more difficult. Unfortunately, like I mentioned, by the end of this whole sequence, the performance falls pretty much to what you would get by just training from scratch. So it's not really worth it. And increasing decision rate beyond 0.6 is not really very good. It's, I think at 0.7 and 8, it's 10% completed rate on that original level. And as I discussed with some people, this is probably because more complex plans just don't have the decision threshold, the truth expectation high enough to be used because of that. So what about those decisions? So I pasted 2 examples of decisions that the agent made, or rather its decision justifications. Some beliefs that it produced were useful, but some were not that great, as shown in that bottom example. So if you compare the top example to the bottom one, the top one is a very good, obvious belief, specifically that if delta sideways of a coffin bed is 0, and delta sideways is just the delta of it being leftward or rightward. So 0 means it's straight ahead. And if you move forwards, then you achieve complete. And that is pretty much the case in the easiest level seen here. Basically, there were 2 scenarios. If the agent turned right at the very beginning, then this was pretty much over. It would just go straight for the bed. And that was it. However, if it, for some reason, turned left, that's when the trouble would begin. And the trouble stems from that bottom example, because it is an implication of that moving forwards, when there is something ahead, and then it's some, again, delta sideways reference. It's a bit of a messy hypothesis here. But this was specifically used to just walk into a wall. And the problem is that without some hyperparameter tuning, specifically raising the decision threshold, it seems that ONA has a lot of trouble with getting rid of these problematic hypotheses, because it would just keep going, and it would run out of time. It would hit that 100 steps cap and get reset. Another hyperparameter that is not mentioned here, but it is not, it has to be changed in the config.h file, and then it needs recompilation. But there is a parameter that is supposed to regulate the rate of negative evidence affecting these. And I did increase it somewhat. I increased it 5-fold actually, but it didn't seem as impactful. It did seem a little bit impactful. But the decision threshold, as you can see, decision expectation of this bottom one is 0.63. So raising the decision threshold to 0.6 means that it's going to be, fall below that threshold a lot faster. And this is what I observed. After increasing decision threshold to 0.6, the agent here would turn left sometimes, but it would only get stuck for a few rounds, and then it would turn around. And the moment it has that bed in front of it, then it's over. It will go straight toward it. There is that interesting takeaway from this experiment. Probably the most interesting takeaway from this whole workflow that I had. Additionally, from inspecting logs, I could see that there are certain neat inferences that it could make. For example, noticing that delta sideways being zero is equivalent to the ahead property, which means that the ahead property is pretty much redundant, which is true because it is formally not very necessary. However, interestingly, removing it did drop the performance somewhat. So in the end, it seems it's best to keep it. That said, the particular representation that is produced from perceptions is in quite a lot of flux because I still haven't figured out what is really the best baseline of this. And this is really the highest complexity of working with ONA. It kind of resembles feature engineering because there is really a lot of small ways that you can tweak your input representation, and it can impact the way ONA works. One of the primary ways that can impact it is performance, because unfortunately, ONA is not very fast. That is, it can't really handle many of these events being sent per iteration, which meant I also had to figure out what to throw out as much as possible to just not make these very, very slow. Additionally, with more input, basically more input than five statements per iteration, the performance would actually go down. So not only it was slower, but it seems the system just can't really sift through higher amount of information and just doesn't make inferences as good. So in this, that's one of the biggest takeaways, and it's one of the most severe hurdles on ONA's path. Another one is plateauing performance, and I've shown that before. This is also kind of interesting. I mean, it is clear that after building some useful hypotheses, it can't really flesh out, first of all, flesh out all the true values of those so that the really good ones get used and the bad ones really get rejected. And perhaps it doesn't really build more hypotheses at a certain point and a more useful hypotheses beyond a certain point. That said, the system shows potential. I mean, it was very cheap to run, running on a single thread on a laptop. Unfortunately, without more vertical and horizontal scaling, it's kind of limited. But it was still interesting to run. It's notable that it's a very flexible software that kind of can have things thrown at it, and it will try to figure it out, basically. It doesn't require extensive thinking about what to send to it to start. Now, after you start sending things to it, unfortunately, a lot of time ends up being spent on figuring out how to send this so that it works. And part of it is about representation. Part of it is pragmatics. Like I said, optimizing for the minimum amount of statements sent for performance, and also for any particular quirks that the software can have. If there is anything else to say, well, I think that would roughly cover it. So that would be it for the main presentation. So thank you for listening. I don't know if it's worth it to run any demonstration, as of course I can't really run training, as it just takes too long. And I don't know if really the behaviors are too interesting to observe. Like I said, there is a lot of this, you could say, kind of bumbling around that you can see. So that would be it from my side.
Oh, thank you. This was a very useful work you have done. It really points out some of the issues we need to address in the near future, or also related to scaling, but also related to other issues like how to make it more effective in accumulating negative evidence for hypotheses that do not work, which sometimes really, also in other experiments, sometimes it's an issue if it fails to how to say, if it either fails to throw away bad hypotheses, or sometimes it also can happen that it doesn't find the really good ones and is stuck with half-working hypotheses. So it's still a lot of work to do. And thank you for this great summary of experiment. And there's actually a question from the audience.
This works. So I have two questions. One of them, they're related. One of them is, did you use the timestamps or time markers in the training sets in the way you trained it at all? And the second question that is related is, was the setup possible that it could memorize the map and all the moves that it needed to make, or the way that you reset it meant it could not memorize the steps?
Okay, the first question was about timestamps. Well, the way ONA works is that it has its internal clock, right? And when you send a statement, then there is a marker that you attach at the end that says this happened now. And this gets noted that this arrived at time t, and then the clock advances. So all those statements arriving after one another would arrive in sequence. So t, t+1, etc. There are some particularities about this, like it was important after each sequence of observations to send a free. So if you just send an integer, then you give ONA time to do inference, and you also move the clock forward. So sending that free after a sequence of observations helped with some silly behavior, like just mostly not doing anything. About resetting, so resetting would also be an event. It would be a reset event After that, it would also be sent 100 so that the clock moves forward a lot, so that it doesn't get confused. Like it doesn't treat the next episode as being continuous with the previous one. Now, in terms of remembering the map, well, it can't really remember the map as it doesn't really have, it wouldn't really have appropriate data structures. So first of all, right from the beginning, I used relative positioning. So there isn't any Cartesian coordinate processing in that. It doesn't use that. It receives this first person view of the environment. So things that are relatively positioned, like ahead, leftward, rightward. So it can't do something like, oh, this always is at x1, y3, right? Because it never receives something like that. This can't happen. In terms of remembering the specific sequence of steps, it doesn't seem to be the case, because it would just perfectly solve those environments if it were capable to do so. And also I can inspect. One of the advantages of working with ONA is that you can inspect the log files and see what is actually happening. All the revisions, derivations, like you've seen, the justification for performing operations. So it's a system that really has explainability kind of built in. Of course, the logs are really enormous. They have millions of lines. So really, you won't be able to trace the entire behavior of the system, because that would be a ton of work. But with a little bit of regular expressions, you can, probe the log for certain things that are interesting. So I could actually see at least part of what it was doing. And it didn't seem like it would be really, it didn't seem like it was doing any memorization already. It was, like you've seen, it was just trying to figure out that, oh, maybe if something is in front of it, it should move forward. Unfortunately, it perhaps has this kind of overgeneralization issue where it, because it produces some more generic hypothesis that works sometimes, but not always, then it uses the more direct one, and then the more generic hypothesis also gets boosted. And because of that, it like goes up in true value, then goes down, and the system is kind of stuck thrashing. I don't know if that's for sure the case, but it kind of looks like it. So there is that.
Thank you.
Thank you.
Thank you. So anything else? No?
Maybe one comment about the generalization issue. There is one mechanism in the system where it tries to essentially, when it has a general hypothesis and it knows for a specific case that it cannot apply it, then usually the specific case will like inhibit the usage of the general hypothesis. But this is also something quite new in the system, which needs to be investigated.
Well, first of all, the specific hypothesis just had higher truth expectation. The problem is when it, in that easy level, when it rotates left, then it can't use the specific one because the bed is not in front of it, but it still has the generic one that doesn't really work, but it tries to use it. And I guess the problem is that when it uses the specific one, I don't know, but maybe the generic one also gets boosted a little bit, and it kind of like goes up and down.
Interesting. Then it seems like a different case, because as you mentioned, the specific hypothesis has more truth expectation than the general one. It will be interesting to look at this. Thank you.
Thank you. I have a question for Tanguy. Tanguy, can you unmute yourself?
Okay. Fantastic.
The question, do you still have to go at 3:30? Is it still
I think it's okay. I'll try to make it in 30 minutes. 35, yeah.
no, because if Christian has to go now, and if you need to go, we can switch the order.
I can stay for a couple minutes, a couple hours. Let's Christian go first. Okay.
So you can like start at like 3:30, 3:40. It's fine with you, right?
Yeah, it's fine. It's okay.
Okay. So Christian,
Yeah.
you can start your visual presentation. Thank you.
Sure. So hello, everyone. I have a very relevant presentation today. It's a visual perception experiment with NARS, the MNIST digit recognition experiment. So looking at perception through reasoning, we should be very interested in vision in NARS, since NARS sensors are how it autonomously views the world through its various modality sensors. And we can sort of view vision as the high-level understanding of low-level sensory information. So looking at this image on the left, it's an array of pixels, but I see a cardinal on the branch because when I see a red bird with pointy feather on its head and the various features of this cardinal, I realize at a high level that I'm seeing a cardinal. The problem is that at the current stage of research, NARS vision perception requires a pre-processing module, like a convolutional neural network, to detect hard-coded object classes. And this is a problem because it limits NARS concepts such that they have to be decided by humans beforehand, instead of constructed on the fly by the system itself. And we know that when NARS has the high-level abstract concepts, it can use it in high-level logical reasoning, like deduction. So if a cardinal is a bird and a bird is an animal, then I know a cardinal is an animal. But these are using high-level concepts, which we, at this point, expect the system to already have. But what about the raw sensory data, like the pixels of this image? Can the system do logical reasoning with sensations to build these high-level concepts or object classes on its own? Because NARS can natively compute abstractions and generalizations of high-level concepts when we give it high-level concepts. So why can't it do this with sensor data? And so the research question is, can NARS make actionable predictions by natively composing high-level concepts like compounds from low-level sensation data without the need for a separate pre-processing vision module? First, we'll go over a little bit of background and then we'll go into the experiment. So in human sensation and perception, humans have over 5 sensory modalities. We know of the basic 5, vision, touch, hearing, smell, and so on. But there's actually more than that, including proprioception, which is like internal sensors of where your muscles are located in space and so on. But regardless, for every modality, there are specific neurons which detect specific physical signals from the world. So in vision, you have red and green sensory neurons, or sensory neurons that detect red and green. These are called photoreceptors. Touch, which detects things like pressure, mechanical pressure, and temperature receptors. And hearing, which detects various pitches of noises, so high pitch and low pitch. And what's interesting is that in animals and in humans, these sensory neurons connect to the brain in a special way that preserves their spatial layout. And this is called a topographic mapping. And this is pretty easy to imagine or visualize in the vision modality, just because images are very spatial in nature. But this topographic mapping actually occurs for most, if not all, sensory modalities. And that includes things like touch. So if you see this picture on the left, this is a somatotopic or touch map. And basically what it means is that neurons which are nearby in physical space will be nearby in the sensory map. So the head neurons are connected to the shoulder neurons, which are connected to the arm neurons, or nearby in a topographic map. And the same thing with hearing. Lower frequencies are closer to neurons which detect lower frequencies are closer to neurons which detect similar frequencies, whereas on the other end of the spectrum, you have neurons detecting like high frequencies. And so sensory neurons can be activated strongly or weakly or not at all, depending on the stimulus. And this forms a unique 2D stimulus pattern on the topographic map. And so these patterns of sensation that the system is receiving all the time, this is the system's inputs, or in our case, the brain's inputs. So the brain is using topographic or spatial maps to understand the spatial layout of its sensations. And if NARS is analogous to the brain, then the question is, can we modify NARS to accept sensory topographic maps as well, and then test NARS performance? And that's essentially what this experiment is all about. So about the test itself, the MNIST digit recognition test is a famous test for computer vision, goes back a couple of decades. And the idea is that the computer system will succeed at the test by correctly identifying the digit that is shown in the image. So here on the right, this is an example from the MNIST data set of digit 3. And the data set consists of thousands of labeled images of handwritten digits between 0 and 9. And these images are 28 pixels by 28 pixels. This is 784 pixels, total pixels per image. And each pixel is represented by an intensity value in the range 0 to 255, where 0 is completely black and 255 is completely white. And then in between are your grayscale values. And this is a pretty decent test for NARS perception because we can treat each image like a topographic map, a visual topographic map or retinotopic map of 784 low-level sensory photoreceptor activations, from which NARS could ideally infer the high-level object class, which would be the digits label. And so to use an image in NARS, we could treat each of these pixels in the image as a specific instance of a vision sensor, like each pixel would represent like a single photoreceptor. And then each instance of a sensor inherits a certain property, which is whatever that sensor detects. So it might detect intensity values or brightness values, redness, like in humans, greenness, blueness, but it can even detect any other feature, things like vertical edges or edge orientation, like edges that are at 30 degrees or 60 degrees or various orientations of edges, or really any feature that you desire. But here we just use the brightness property to indicate the individual pixel's brightness or intensity. And then what we do is we encode each sensor's activation as an atomic Narcisse event, where the frequency is the intensity of the sensation. So a pixel with no activation would have 0 frequency, and a pixel that it's at full activation would have a frequency of 1. And then we encode the confidence as just a unit amount of evidence. So like one piece of evidence, essentially. And an example of this, you can see in this image, we have a bright pixel over here, and it's encoded as this event where the arrow is pointing. So this pixel at location 14.6 in the image is bright, and let's say it has 0.95 intensity, 0.95, that's a normalized intensity. And so the change to the NARS architecture that you have to make is to store the events in a 2D buffer or spatial buffer that retains the spatial layout of the sensory events. And this allows the system to group the various sensations or sensor events by location. And then also store a reference to every event in a bag, standard NARS bag, using the event's truth expectation as its priority so that events can be randomly selected with a certain probability. So the way it works is, first, NARS probabilistically selects one of these events from the bag, and then it uses this as a pivot event. And then, since spatially nearby events are more likely to be related to each other than spatially distant events, so this event here at the top of the 3 is quite unrelated to these activations here at the bottom, NARS can group the events using a spatial window around the pivot. And in psychology, this is actually an established theory or model of attention. This is called the spotlight or zoom lens model of attention. And there's further reading on this. And so in NARS, multiple events that are selected in the window are then combined into a single compound event using the conjunction or composition. So if the window selected 2 events, it would create a compound like this, where the 2 atomic events are combined using conjunction. And this statement is actually, this is a higher order statement, but it's actually equivalent to the first order intentional intersection of the events. And so that's what this is down here. And so if you look on this image here to the right, this is an example of having the spotlight of attention on the topographic map. This is a 5x5 attention window. And so a window like this would compose up to 25 events into a single compound. So in this experiment, we were interested in 2 different tests: memorization, which is, can NARS remember images that it's already seen and recall them in the future, and also recognition. And this is, can NARS label new images that it's never seen before, based on, say, some training set of images. And so the setup was to divide the very traditional setup, where each experimental trial is divided into the training phase and the testing phase. So first, the system is shown labeled images, and this is in the training phase. So it's shown an image and then told a label for the image, and it can temporally associate them. And then the knowledge is tested in the testing phase. So in the training phase, NARS is allowed to just observe the training image for some set number of cycles, and then input with a label, which is another event, which informs NARS which digit that it's currently looking at. And so for an example of a label would be, you're looking at the digit 5, or this digit 5 is seen. And then during this phase, NARS temporally associates visual features with the digit label event using temporal induction. So if NARS might make a statement like, if this pixel is bright at this specific location, if this photoreceptor is activated, essentially, then I'm looking at the digit 5. And then whenever NARS sees that event again, it can predict what it's looking at. So it will predict that I'm seeing digit 5 whenever it sees that this specific pixel is activated. And then in the testing phase, NARS is given seed goals to execute a specific operation for a digit if that digit is seen. So for example, the goal might be, if you're seeing the digit 5, then press the digit 5 button. And goals are input into the system for all 10 digits. And so therefore, when NARS predicts certain events, like I'm seeing these visual features, so I'm predicting I'm seeing the digit 5, NARS can then use deduction to derive evidence for the operation goal, like to press the digit 5 button, which will then cause it to execute that operation if it exceeds the decision-making threshold. And so the success criteria is whether NARS predicts the correct digit or not, executes the correct operation or not. And so NARS gets 1 chance to answer for every image in the test set, and it answers by executing an operation. And then depending on what operation it executes, the answer is recorded as correct or incorrect. And there's also a timeout, because NARS is not guaranteed to give an output. It can give an output or it cannot if no operations exceed the decision-making threshold. And so there is a timeout of 3,000 working cycles in this experiment, where if the system does not recognize any image features or the labels, then it might not execute any operation at all. And at a certain point, we have to cut the system off and say, okay, you're not going to get this digit. You got this one wrong. So the basic idea is that NARS will scan the image continuously and compose visual features into compounds. Then NARS continuously makes predictions of the image class based on the compound features that it's seeing. And if enough evidence for various predictions accumulates in that memory, then NARS will use them in goal inference. And so the hypothesis is that NARS will predict certain digits correctly with high confidence. And by grouping multiple events, the compound event will be specific enough to predict the digit class, but generic enough to recognize variations on that digit. So images that NARS has never seen before. This is compared to like a single pixel, which would be far too generic, because many different types of images, many types of digits might activate one pixel. But also NARS can't just store the entire image in its memory. That's far too specific, and it's very unlikely that another image of that exact same layout will be seen again. So it needs to do something sort of in the middle. And here's a video of the experiment. And so the image on the left is the image that's being presented to NARS. And the image on the right is what NARS is currently paying attention to and at the current working cycle. And so you'll notice that it sort of jumps around and compounds, composes features from different parts of the image. And so this is the training phase. It's given 125 working cycles per image, and it's shown 300 training images. And so here at this point, it's essentially composing visual features into compounds and then temporally associating them with the labels. Here, the label is being given because this is the training phase. Then in the testing phase, NARS does the same thing. It composes the various visual features, but at the same time, it's continuously making predictions based on the implication statements in its memory. And so here you can see that actually, in many cases, NARS is predicting the correct label for the digit. So here the system was looking at this digit 3, and it viewed various features, and then it predicted that I'm seeing the digit 3. And if you watch this video, you'll see certain situations where the system sort of gets tricked into predicting the wrong digit because the windows that it's looking at, these small windows it's looking at, are sort of ambiguous. So like a 3 might sort of look like an 8, depending on the small window it's looking at. And so here's the overall results for the 4 tests that were run. There was a memorization of digits 0 and 1, memorization of digits between 0 and 9, classification of novel images for binary digits, and also classification of digits between 0 and 9. And so what you'll notice is that NARS performed both the binary and the digit memorization perfectly with 100% accuracy. And it could classify new images of binary digits or the digits 0 and 1 about 98% of the time correctly. But the most impressive was the hardest test, which was the digit classification, which is identifying digits of 0 to 9 that it has never seen before. And in a single trial out of 100 images, NARS was correctly able to classify 50% or 50 of the images, approximately. And this is much better than the random chance we would expect if NARS was, well, NARS is not actually guaranteed to output any operation, but if it was, we would expect random chance to give an accuracy of about 10% if NARS was randomly guessing. So this is pretty statistically significant. NARS is classifying almost 50% of these images correctly. And it's doing this simply using composition, induction, and deduction rules. So just simple inference rules with no pre-processing involved. And there's also the personality parameters for the various tests. Here in the most impressive test, the decay rate for events and goals confidence was 0.95. The evidential horizon was very standard, k equals 1. And the decision-making threshold was fairly moderate at 0.65. And so analyzing these results, we can see that the spatial grouping of visual features for compositional inference actually allowed NARS to predict correctly the class of novel images. And interestingly, the system achieved higher accuracies when modified to use static sized attention windows rather than allowing the window to randomly change in size randomly. But this also limits the system in that it can only look through specific size windows of the image as opposed to more adaptive size windows. And so in the future, the attention window should change according to some factors. The system also performed better when given access to select disjunction of events. This is like a form of max pooling, which provides robustness to small local translations of digits in the image. So if you have this 4x4 feature map, it might be these features might be too specifically located for NARS to recognize it. So you can actually use disjunction to sort of fuzzy the image up such that like features, if the features are slightly translated to the left or to the right or down or up, when you pool them using disjunction or operator, NARS is more likely to recognize them. And just looking at the limitations of this and possibly future directions, one problem was that the system couldn't choose its own attention window. It was randomly sized or in fixed size. And so it would especially be useful if NARS could use its own top-down predictions to better analyze the stimulus. So like if NARS sees the color red, it might predict that it's going to see a cardinal, and so it will additionally look for beak features to confirm. Also, NARS only had a pixel intensity map. Humans have neurons in visual cortex V1, which detects specific edge orientations like vertical orientation of edges or horizontal, and the various degrees in between across the entire visual field. And you could also represent these as an activation map. Related question to this is, do these edge orientations, for example, need to be detected with a pre-processing algorithm, or can NARS do this natively? So could NARS, for example, detect vertical edges using Boolean operators? This is a question. And the explicit kind of spatial window used here might be sort of a naive approach versus maybe a more implicit and parallel spatial composition, which you could achieve with neural networks. But still, these results pretty much show that the promise of spatial grouping and evidence-based reasoning, it works for sensory understanding. And here NARS was trained and tested in passive image classification tasks, but future tests could take place in a more active context by testing NARS in a real-time interactive environment. These are my references. And that's all. Thank you. And I'm glad to take any questions or discuss.
Thank you. This was very promising work, and especially,
thanks.
How to say? Clearly, we humans have like a focal point or phobia, and there's a lot to be explained how actually human vision works. And I think what you're doing is much closer to this than let's say when we have a convolutional neural network. Nevertheless, clearly for applications, we need networks which can detect useful objects from natural images. Do you think that we could potentially utilize features like a YOLO model has learned and use them as a guidance so that it doesn't have to compose random spatial conjunctions, but can actually have a attention bias to certain features which the YOLO model, for instance, has learned in ImageNet? I wonder what your opinion is.
I had the exact same question. Like whether the individual neurons from the very beginning to the very end and all the hidden layers in between could be analogously used by NARS and let the neural network perform the spatial composition in parallel. And I wonder if that could be achieved with deep learning, and also if that could be achieved like internally in NARS, according to some using the composition rules and some sort of like network type data structure, so that the compositions can be sort of composed in parallel, and then the system can more effectively use its attention to select out of this network.
Interesting. Are there any questions from the audience? Let's check the chat. Oh no, no questions, I think.
Okay.
Then it's,
well, in that case, thank you very much.
Thank you. Thank you. Then it's Doris talk, I think.
Okay, thank you. Let me share my screen.
Yes.
Yeah, can I see it?
It works.
Okay, thank you so much. And hello everyone. My presentation is about multi-channel functionality for open NARS and enhanced buffer. To start, let's talk about channel. What is channel? Let's just think a channel is the result of information. For our human beings, for example, we have a video channel, which is our eyes, we have audio channel, which is our ears, and we can taste and we can smell. These different channels. Different channels have different information, and we fuse different informations to get the experience of the world. So at first, I want to give you a big picture. Previously, we fused different information information from different results in a successive manner. Or in another word, we do it manually. For example, we see an apple and we hear an apple. This is from two channels. First, this is the vision channel, and this is the audio channel, right? But excuse me. But previously, we do not have such mechanisms to fuse them in naturally. So we have to do it manually. For example, just to create some compounds to tell us that we seeing an apple and hearing an apple happens simultaneously. But currently, we introduced this new design to want to make it in a parallel fashion. So two main purposes. The first is to make it natural, right? This is not for any additional functionalities, but it is it is more convenient. Previously, it may take some time to design things we want to fuse these different channels manually. So we have to design some algorithms to do so. But currently, we just need to create different channels independently, and they will fuse naturally. So, and this will give us, more space for creating more interesting experiments. And to do so, we have introduced this enhanced buffer. Why is enhanced buffer? Since previously, the buffer is just a container of information influx for filtering useful ones. And currently, we separated some processes from the main memory and add them to the buffer. But this will not change this functionality. So we will just see this is an enhanced one, not a brand new one. And in the following discussions, I think I will introduce many examples, including variant channels, since that is very intuitive. But that does not mean that this channel, this new design, is built for variant specifically. Okay, we hope that this channel refers to any information results. Okay, to start, remember what I have talked about channels, and we want to fuse information from different results. But previously, we do it manually. Currently, we do not want to do so. How these different informations are combined? Let's just have an example. The answer is from categories. Categories is philosophical terminology. Here, I think we can just simply understand it as an entrance of information. But this information is pre-processed with some a priori knowledge. For example, our familiar space category, like this case, we see a wheel and we know this wheel belongs to a bicycle, right? Why? Since this wheel is a part of this bicycle based on the 3D real world Euclidean space category, right? Another example is this time category. For example, this alarm light. It is red, and now after a few seconds, it will become blue, and this pattern will continue. This space and the time relationship build what we want to find naturally. But how about we want to, describe something brand new? For example, this image is generated by AI. So we may think, okay, it is of a desert oasis, but something is different. So this image might be unfamiliar, but we try to describe this image, this unfamiliar one, with some known stuff. For example, we see this might be cactus, a house, and a dog, a person, or something else. You may discover more recognized entities and use a combination of them to describe this image. So that means if we want to describe something brand new, we usually do it while combining something known. This combination might be infinite. The bad news, this is it. But as any intelligent system, NARS is also bounded by computational resources. We need to do this infinite combination, but that is not realistic. Therefore, we want to come up with a design by ICAR, by this assumption, so NARS can do enumeration, but still fulfill the responsibility of a buffer. That means filtering something useful. Therefore, the main concept of this new design is that exhaustive enumeration in a local scope in each buffer. Make sure this local information is consistent with a global status. Since a buffer is small and limited, this will not take a long and a relatively small and fixed amount of time. And then by communicating these buffers with the main memory, we are able to give this heuristic for filtering. Okay, this is a guiding concept of this new design. Let's take a look of the concrete design. The design of the buffer, we have 3 kinds of buffers. I think this has been introduced previously in today's presentation. First, this is an event buffer. Second, internal buffer. Third is the overall buffer. Here, just a short reminder to let you know what's the responsibilities of different buffers. So the event buffer, it is for the outside information. For example, just like this radon channel again, with a wheel, and we know, except for the wheel, absolutely, we also see the background road, right, and the grassland, but we did not pay attention to that. Therefore, for event buffer, it absorbs outside information and try to find what's worthy attention. Secondly, it's an internal buffer. Internal buffer is also used for filtering, but it works on what I thought. For example, I have different feelings, but currently I am curious, and this is filtered from my feelings. The next one is the overall buffer. Overall buffer is a hub of internal buffer and event buffer. So this is for what I thought and the outside information. For example, previously I have just see a well, and previously I have just thought I am curious, and here I make a combination of them. I make a combination of them from different semantic spaces, right? This will be talked about later. As mentioned, buffers precise by time and space. I think they are the underlying logic for making combinations automatically. However, time is very it's just straightforward, just to follow the time order. But the spatial relationship is a little bit different here. It is not necessarily a 3D Euclidean spatial relationship. So when talking about space relationship, we may think about the positions of different objects, but that only happens in our real world. For example, in this overall buffer, it contains what I have just thought about and what I have just thought, right? These are from different domains, but they are combined at the same place. Therefore, we see this spatial relationship has a more general meaning. Is not just the Euclidean space. Therefore, we can generally think each buffer has 2 main components. Think even this spatial relationship is a little bit different, but it's also about time and space. Time slots and the prediction table. For time slots, its name might be a little bit misleading, but it is actually for the space category. And for this prediction table, it is for the time category. And I will talk about the design in detail, so don't worry. First, I will talk about the green part, time slots. It has 3 types of time slots. First, previous time slot. Secondly, present time slot. Thirdly, future time slot. That means that this is a present time, and this is the history, and this is my expectation of the future. For example, if I say, it is cloudy, and I may expect it's going to rain, so I may put raining in the future slot. For each slot, it has 3 areas. First, operation area. Secondly, event area. Thirdly, anticipation area. But here is just a reminder that not all time slots have all the components. For example, for event buffers, their time slot does not include the operation area. Here is just one case study. So I will not talk about the detail, talk about the detail things. I don't have enough time, but this is just to let you know that this presentation is about the general design. For more details, I think yeah, it may take some time to understand. Then for the events area, I mean this part, events area as a name says, it's a area for observations, events. The events area is a priority queue with a relative small storage. Since this is where we want to do the exhaustive enumeration. If it is too large, we're not able to do so. The priority value is calculated by the event choose value, budget, complexity, etc. Different metrics for an event. And note that this is different from the priority. It's budget, right? For you understand NARS. But in one word, it is a priority queue. The priority is based on three things. First, we want this judgment or event to be certain. It is true or it is not true. That means we do not want something in the middle. It is 50% true or 50% false. That is not what we want. We want something extreme. And we want something stable as well. That means when we're talking about the truth value, it will not subject to change in a long period of time. Secondly, it is important. That means this is consistent with the system's current thinking. For example, if there is a breaking entertainment news while I am working, probably I will not pay attention to that. Since even if it's breaking, but this is not important to what I am doing, right? But if I am free, I may, I may spend some time to take a look. After introducing the events area, I think it is enough. It is time to introduce the operations area. Operations area contains all operations supposed to carried out. That means their effects are already manifested. For example, in one slot, we can see the events area and the operation area. The events area always happens after this operation area. Here is an example. Suppose there is an operation called draw something in the operation area. And that means we need to draw something on canvas. For example, let's just draw some clouds. And after that, the canvas or the environment has been changed. Therefore, the information gathering will detect this cloud and put it in the events area. Okay, and after introducing, here we introduce the time slots and independent time slot. And it's two areas, but anticipation area will be introduced further, so not here. After here, you might be, some of you guys may have such a question that thinks events buffer as something process the outside information. It may process something never in the memory before, something brand new. If it's not in the memory, what is its truth value or what is its budget or something else? In this case, the truth value and these metrics are given a priority. For example, in a vision channel, the white circle represents the field of view, and the green circle is the middle of the field of view. And we have detected several different objects, and the probability of each object detected given by the neural network could be the frequency. The closer it is to the center of the field, the higher its priority, something like this. So that means we need to define how this input information evaluated by the system. But I think this is still much more convenient than the previous design. Okay, after introducing time slots, it's time to introduce the next part. This part, prediction table. Prediction table is also a priority queue, just like the events area, including only temporal implications. Predictions are used to make expectations in the future, just like the the previous example. If it is cloudy, and I may expect it's going to rain in the future. Since it is a priority queue and the space is limited, different predictions, will compete. But here we do not want to the one with the highest priority. We just want to keep the top M is the side of this prediction table. That means they are active predictions according to the context, a short term of history. After introducing these two parts, and let me introduce the buffer cycle. We have introduced the cycle of NARS. But at here, when they say, I think it is worth it to introduce the cycle of each buffer, since while doing the cycle of each NARS, it's inevitable to process something in the buffer. So let's just call it a buffer cycle. Before a buffer cycle is started, first, the oldest slot will be dropped and a new one will be created. The remaining one, you're getting older. That means, a step for the time slots. After that, there will be new information inputted in the current or present events area. They're atomic. So they need 4 steps for further processing to get the final answer. There's 4 steps. The first is the compound generation. Second is called local evaluation and memory-based evaluation and the prediction generation. After that, one selected event will be forwarded to the next level for each buffer. It looks like for each buffer, we have input a couple of things, but by this processing, in the end, there will be only one, maybe not from them, one selected one and forwarded to the next level. Let's just talk about the first step, compound generation. Compound generation, as the name says, but it has 2 parts. First is the concurrent compound generation. Second is the temporal compound generation. This needs to be done in a successive manner. For example, we need to figure out what we need to pay attention to at the current time, and we are able to think the relation of what I have paid attention to and the previous things I had paid attention to. Concurrent compounds are simply all combinations. For example, if we have n atomic events, and we will have 2 to n or a combination. And these n atomic events, think this is a priority queue, the sorted, and so does this one. It is also a priority queue and sorted. And after that, we do not want all of them, since that's too much. We just want to pick top m events. M may be larger than n, since we may need some softer margin for that. We'll talk about it later. And secondly, we need to generate temporal compounds. When considering the generation of temporal compounds, we still consider using exhaustion. For example, here we have 5 concurrent compounds, and we have 3 previous time slots. And previously, they all have the in previous time slots, they all had the the thing we paid attention to. Suppose for this is X, and for the second one is Y, for the third is Z, and we want to generate temporal compounds. For example, we have XA, XABC, XCD, XAC, and XD. This is just for X. And we will also do the same thing for Y and Z. Therefore, if we have M concurrent compounds selected and K previous slots, we will have K times M temporal compounds. Of course, we have M concurrent compounds, right? But you may be curious why we need to keep this compounds in 2 tracks. The first is concurrent, the second is temporal. Should them be mixed? I agree with that, but this might have, this may be a little bit risky. For example, to the example of the alarm light, it is shining red, blue, and red and blue. To describe this pattern, for our human beings, we may describe it as, okay, it may be red after blue or blue after red, something like this. Just the 2 nodes of this pattern, it is enough. But if we do not keep these 2 things in 2 tracks, for example, when we talking about, when we come to the second time slot, we get the pattern blue after red. And when come to the third time step, and it thinks I need to generate a temporal compound, continue the second time step. The pattern will become red after blue after red, which is unnecessary. But if we keep these things in 2 tracks, there is a possibility for us to generate something like red after blue, only considering the second and the third time step, just like dynamic programming. This is the first step, compound generation. Then the second step, local evaluation. And here, there are 4 things we need to do. First, when we focus on the whole, components get less attention. just that focusing on a bicycle, we may forget about its details. What's the color of the saddle? What's the size of the wheel? We may forget them. Therefore, when a compound and a component coexist, for example, we have AB as a compound and A both selected in both of these two tracks, the component, I mean this one, will be penalized. And that's the reason why we want to take M, which is larger than N, things as softer margin. Things here, there must be something necessary to be filtered out. Next, we will check the prediction table, this one, to check whether the preconditions of some predictions are satisfied. If it is satisfied, we will just put the result in a corresponding time slot in the anticipation area. Next, we will check the anticipation of the present time slot, whether the anticipation is satisfied. If it is achieved, it will be revised with the present event. This is uncommon, but it might be very useful when my anticipation is extremely strong. Another example is that this is a sunny day. I strongly believe in that, but I see water is dripping outside of my window, and okay, in some case I may think it is going to rain, but it is not true. So I doubt about it, since my belief, my expectation is really strong, and I don't think it is a thing of the rainy day. If anticipation is not satisfied, it will simply be dropped. It does not happen, but this may penalize the prediction who generates this expectation, since that prediction is not accurate. The last thing is for unexpected observations. Since we hope we can expect something, since if it is expected, okay, that is non-common, right? But if it's unexpected, I don't expect it's that thing, but that happens. That make me curious. So in this case, these unexpected observations may worth a higher priority. So they will have a bonus priority. Then we go to the third step, the memory-based evaluation. Previously, we have introduced the time slots and the prediction table, but all these information are local. In the third step, this is a chance for us to query the memory for the global information, whether these important information are really important, like the previous example of breaking entertainment news. If such information is in the memory, so we will think, okay, I'm thinking about it, so it will get some bonus, otherwise it will get some penalty. After this step, all these two tracks, the priority will not change. Therefore, it is time for us to get the highest temporal compound and the highest concurrent compound. Aside, we just need one of them, but as the issue for the inheritance of the previous event's history, we created two copies. First is for the concurrent one, the second is for temporal one. So we have two of them. But in the next step for prediction generation, at first we need to we need to let the system know what is the one worth the attention based on the history. So only one of these two things can be forwarded to the next level. So first, we pick the highest one, which is called the highest compound, and and this is one that we need to forward to the next level. That's okay. Here, this is the thing I need to focus on currently. And the next thing is that what makes it apparent? So what's the reason to make it apparent? What makes me to pay attention to that? We need this reason. So we make some predictions based on the previous highest compound. For example, if we say A is the highest compound at the present time slot, what makes it what makes it the most apparent one? It is X, we don't know, but we just create such a prediction. It is Y, we don't know, we just create another prediction. Different predictions also have different truth values and budgets. They will compete in the prediction table. And that is the buffer cycle. In the end, I decide the highest one will be forwarded to the next level. As a reminder for event buffers, the highest compound will be forwarded to the overall buffer, internal buffer also be forwarded to the overall buffer. But the overall buffer, the selected one will be forwarded to the memory. And here are some special notes for Narcissist channel and output channel things. Although these are named with channel, but they have different interpretation. First is Narcissist channel. It has two interpretations. First is that it is just a communication channel between Narcissists, just like you and me would speak English to communicate, right? In this way, in this interpretation, the Narcissist channel is just a channel that is not too special, different from other channels. So it has no priority status, but it has a different interpretation. That is, when we're talking about Narcissist channel, we also mean that it is also an admin tool for us. In this way, the Narcissist is not from another NARS, a non-Oximatic reasoning system, but from us. So we want NARS to respond to our instructions directly. So in this way, this Narcissist channel will have a higher priority. The next one is output channel. It also has two meanings. The first is that when we think the output channel, that is a output window for NARS to present what is just got, what is just inferred, or as a data log recorder, something like this. Another interpretation for the output channel is a working mode in which the input channel executes an operation. For example, we have a camera, but it can zoom and it can move. That means these operations, NARS can tell the channel to carry out this operation, but this does not mean that this channel is only used for output, since it is still a camera. It is still able to get the video influx and forward that influx to the non-Oximatic reasoning system. And since we still have some time, and I think I'm able to talk about this appendix. A short experiment for this new buffer design on computer vision. This experiment is still ongoing, so I will talk about the limits. Let me talk about the configuration at first. We have NARS, non-Oximatic reasoning system, connects to two channels. First is a video channel, camera, but it is a fixed camera since this is still an ongoing experiment. It is not able to move and is not able to zoom. It faces a screen, plays different images. All these images are manually selected under the same inside our house. Why I pick this same is that, okay, this is the same consists of a variety types of objects. It may contain books, desks, chairs, televisions, and even toilets and persons, something like and plants, something like this. That means it is an abundant one. It is a little bit hard to define. And another channel, I just designed it, but currently it is not very useful since I have just used one theme of pictures for this experiment. So for this channel, as a reminder of the theme of the pictures, it is invariant. It will not change. Here I just show some examples. We will see the detected one in the next few slides. Images are pre-processed by RetinaNet, an objection detection neural network. This is different from what Christian just did. He did it in a pixel-wise manner, but this is in object level. For example, different objects are detected. There's televisions, the desks, this person, this bottle, and this plant, something like this. And the priority and the choose the budget and the choose value are introduced like the previous slide. Here it means that for each image, we will get a couple of nurses describing what we have seen. And based on the arrangement of these objects, we may know what is nurse may know what is called a thing that is inside the house. Here is another note that is, since here we deal with different images, and these images are episodic. That means we do not want to discover the temporal relationship of two different images. Thanks. To be honest, this temporal relationship is just totally random. So when we just take the IID assumption and forget the temporal relationship of different images currently. Therefore, for this ongoing experiment, we do not need to think about this one. That means we do not think the second channel, that is that the overall channel, the position of the overall channel is not very important. And for the first one, it has different images and it has different objects detected. So I think we just need to see what's the attention of the video channel. That means by reading these images, by reading 90 of these images, what's NARS attention on the remaining 10 images? The result will be something like this. For this one, NARS attention is on this child. For this one, still on this child. Even this book is very close to the center. For this one, still this child. Okay, this is couch, this is not chair. So that's the reason why NARS do not want to focus on it. And for this one, it's also focused on this child. It looks like NARS prefers, NARS thinks if this configuration has a child and it is largely called the same inside of the host. And here are just 4 examples, and I think we still have 3 minutes. So I think I'm able to share more experiments. There we go. It may take some time. Sorry. Okay, here we go. First image, just like this. Think this child is a focus. Second, this child again. Next, this child again. This child is not a focus, it might be too far. This one, focus the child. This one is a refrigerator. I think there are no other objects detected in this image. Next, this television. There are no chairs at here. Next, couch and sink. There are the only 2 objects detected here, and no chair. For this one, it is chair, even if it's too far from here. And all these other things are not commonly appeared in the pictures under this thing. Okay, and I think it is about my presentation. In the future, I plan to, currently the camera is fixed. It is not what I want. So I plan to add more operation like zoom and move. Secondly, if we still want to deal with episodic images like the machine learning and deep learning people, then there are plans to introduce more scenes and more channels. But if we want to processing videos, there is a need to detect changes in the video due to non-camera movement. For example, if we use a camera to watch the television, it plays a football game, and 2 players moved from one place to another, we want to detect it. Otherwise, it is hard to describe what is happening. And okay, that's all about my presentation. Do you have any questions? If I'm able to answer.
Let me check the chat if there is nothing in the chat.
Okay.
So, okay, thanks, Tanguy. So this was the actual new enhancement on the version 3.1.3, which I presented. That's the different, which makes it different from the version 3.1.1 and 3.1.2. This is the design of the buffer and the channel and how the buffer are incorporated into the channels, input channels. I think so we are done with the presentation for this workshop, and the only left is the hands-on demonstrations. So that's what we will start, right? So we will start with the smaller examples and then going toward the robotics, probably video, because we didn't bring the robots with us, and we'll show that how robotics is working.
Yes. So at first, I just want to give a quick overview. Let's see where actually. 1 second, I need to stop screen sharing. Where's the window? It's closed. 1 second. Oh, yes. So maybe in the meanwhile, yes, I just want to give a brief overview of some of the things we have tried experimentally. Which might be relevant to summarize overall the capabilities. Like we have seen in the early day-to-day capability for high-level formation of a concept of identity, like to learn to pick a sample which has a shared characteristic property with the sample in the middle, but it can actually build and utilize such hypotheses. What we did not yet see is also it's also quite effective for integrating background knowledge and working with background knowledge, even when the background knowledge is not perfect or not always reliable. For instance, we have a few examples in the code base which show like relational reasoning and basic planning. Like let's say we have different doors on different objects with different properties and materials they are made of. And let's say we also know there's some kind of light that we can use which generates heat, and heat causes materials to melt, which is all quite high level knowledge. So we also have some experiments where we also show that we can utilize some of this I was muted. Oh no, it should be fine because it's like, oh, okay. Was I muted before? Oh, okay. Oh, good. No one complained in the chat, so it should be good. So we have several examples also which show that the system is also able to get some of the strengths of what expert systems also are typically known for, like to utilize high-level knowledge. Like if we already have a lot of high-level knowledge, why not utilize it to solve a task? And we think that a lot of potential in applying the system is also a combination. Like if you have a certain background knowledge, why not give it to the system, and other aspects of the task might be subject to learning, essentially. So as to combine the strengths of both worlds. But what we have nevertheless also done is a comparison with reinforcement learning, since that's a very, of course, an interesting question. If we can learn these sensory motor contingencies which allow the system to reach goals, how does this actually compare? Can we test the system on classical reinforcement learning tasks and draw some comparison? The answer is yes, that's also possible. There are comparisons both on theoretical and practical level. If we look at theoretical level, there are some high-level features which distinguishes our approach from reinforcement learning. For instance, typically the reinforcement learning solutions solve temporal credit assignment for reward outcome, while NARS can essentially temporally relate all events which come in the stream of events, and which also means has potential for learning from observation, because it doesn't necessarily need a reward in order to associate events temporally with each other. Another thing. Okay. Another thing is as I mentioned in my earlier talks, is we don't use a learning rate decay. Instead, the confidence of a hypothesis naturally stabilizes the frequency value of the hypothesis. What's also good, because we have causal representations, it's actually easy for the system to change behavior.
Pei, could you please mute yourself because there's an echo? Thank you. Please continue. We don't seem to hear you on this side.
We're having a little bit of sound issue. Give us just 1 second. Something changed.
Okay.
It was on Scarlet 6i6. I do. Oh, I do. Can you try again?
Can you hear me?
Yes, perfect.
Okay. Is there any slides where there was no sound? Because else I can repeat. The last two? Okay. The last two. So essentially, just very briefly, so today we showed some high-level learning abilities which allow the system to create and utilize quite high-level hypotheses, like choosing a sample when it has a correct characteristic property with the which it shares with the middle one. So this is something which Robert Johansson showed in the early morning. But sometimes it can also be the case that declarative knowledge is not learned, but sometimes it can also be that we have some human given background knowledge already. And we also have some examples in the repository where we can show that the system can actually effectively use high-level knowledge in order to solve problems. Like in this case, when it has like information about different object types, what they are made of, and like the lighter can generate heat and so on, can essentially in this particular task learn to unscrew a screw by melting a toothbrush and shaping it into a screwdriver form, essentially, just to give a particular improvisation example, problem-solving scenario, which can benefit from knowing about the materials objects are made of, about that heat can melt certain materials and so on. So this is also something we can show, essentially, to not only have learning, but also a way to utilize high-level knowledge quite effectively, which is sometimes quite useful. But we also have comparisons with reinforcement learning. So a key strength is that we can learn in the absence of a reward. We can, because the system can correlate events with each other. It's not only learning about what leads to reward, but also is able to learn from observation, so to speak. And other aspect here I already mentioned. And a very strong aspect is that it learns causal representations, which allow it to adapt to changing objectives or changing goals, essentially. So it's usually quite quick in adapting its behavior when goals change, because of the causal representations it's building, which do not depend on the currently active goals. Another thing which Adrian touched on is when he tried like different exploration rates, usually it did not make much difference. And a point is, and one aspect of this is that this is one hyperparameter which is actually not really a hyperparameter because it's adjusted by the system. When it has a high confidence of how to get the goal achieved, then it reduces the chance of motor bubbling. So it essentially reduces exploration rate or trying of random actions when it becomes more confident of how to achieve the outcome. And So it's usually not too dependent on the initial value as long as it's high enough, because it will be decayed by the system anyway for specific outcomes it already knows how to achieve. Previously, we did some experiments where we tried compared owner with Q-learning on several tasks like Pong and Space Invaders and some grid vault experiments more recently, as Adrian has also shown. But what's already quite interesting is compared to a vanilla Q-learning table-based Q-learner, which is a good baseline when we don't learn from pixel data directly, but already have some feature used for feature representations, which we can feed in as events. Then it still makes sense to use Q-learning as a baseline. Of course, ideally in the future, we also want our system to learn from pixels, ideally, but it's still an unsolved problem of how to do this. We have experiments where we actually pass gradients back to like a convnet, which is attached to the system by having a differentiable formulation of the reasoner by using differentiable programming tools. But this is still early work. So at this stage, I can only show you comparisons with Q-learning, with normal Q-learning. And what we can, the results are not too surprising, mostly in environments like Pong. There's hardly any difference between using owner or Q-learning. Difference, however, is when we have a Pong version with stop operation, where essentially it's not non-Markovian, because it does not only depend on the next observation, also depends on previous actions which have been invoked. Like whether it moved to the left or to the right before it invoked the stop operator. And so it's essentially in this Pong version, if it doesn't call the stop operation, it would keep going into the direction of the action it took a few steps earlier. So it's not just dependent. Any question? A master is always owner. And Q-learner is the branch where we replace the agent with Q-learner, and both receive exactly the same information. And yes, and what's interesting is in the Pong variant, which is non-Markovian, clearly it's not that Q-learning did not work at all, but it, of course, since it builds on the assumption of Markovian environment, it did not find policy as good as many runs of owner. But sometimes it also happened for owner that it built hypotheses which only related events which happened in the previous frame. So in this case, it also learned behaviors which are not optimal, which are actually similar to the one the Q-learner has learned. So that's something we can show that owner most of the time, or is not dependent on Markov assumption. State and action. And an additional interesting result was in our grid vault experiment, because we have some first initial results which show that curriculum learning is actually way more effective with causal representations, because essentially if the next task depends on behaviors and knowledge which were built in previous experiment or in simpler tasks, like let's say at the beginning it just has to learn how to fetch the key. Then next step we make it more difficult. It has to fetch the key and open the door. Next step we make it more difficult. It should fetch the key, open the door, and then get to a target state. That makes a huge difference if it can carry the knowledge it has learned from a simpler task, like how to not get stuck in the war is already a useful information, how to navigate without getting stuck. If it can use this and apply this to the next task, even though the goal is different, that's already very useful transfer of causal knowledge, so to speak. And this is where we can show that we're better than Q-learning as well. But this was not surprising, but it's a direction which we need to investigate. But of course, there's also other responsibilities we have, like something special happened when they moved from Q-learning with a table-based representation to a deep Q-learner, which can approximate the Q table and actually pass gradients up back to the ConvNet or convolutional layer, which are part of the agent. That's something great which happened, and it would be good to investigate more whether we can profit from the same idea. And that's something we need to investigate in the future, because clearly in the deep learning community, they will not take us very serious if we need special feature representations as input, even though biologically it's not implausible that evolution has evolved some of the relevant features in our visual system that make us survive. Maybe our vision system is more flexible than that of a dragonfly, for instance, but there might still be some innate evolved aspects but to some degree, clearly we also want to make this more flexible and ideally also to learn from pixel data at some point. So this is still ongoing work, but what we can already show is that causal representations are in many ways superior than simply learning what action to take in a certain state, namely the one which with maximum expected reward. And that's how to say that our representation has certain benefits, but we need to find a way to make it do similar things like deep Q learning, for instance, if we want to compete in the machine learning community this regard. But clearly what's also interesting is learning rate in some domains. Like here I have Space Invaders. In all the examples, pretty much I needed to do some grid search for the Q learner in order to reach reasonable learning speed. While in Honor, I did not do any parameter tuning for any domain here. So I guess learning speed is also something where we hope that we can show good advantage. Exactly. And I can also probably I can show one illustration of how this transfer of knowledge actually looks like in one of the better runs here. There are also some bad runs of Honor where it's not doing better than the Q learner, but on average we can see the curriculum learning setup. That the thing with curriculum learning is always, to some degree, to be effective, you need to assume that the agent has learned relevant aspects in the previous task before it actually makes sense to move to the next. It's a bit like in score. If the children don't perform well at the tests, then they should take the class again, ideally, because else they will not be able to do well in the next course. And here it's similar with curriculum learning. There's a high variance in how good the runs perform, because if the ones which are lucky and where it picks up the right hypothesis early, they will give it a large boost in progressing to the next level, essentially. Yes, this is something I can actually show. So this is the example I mentioned where it first has to learn to get to a target location, then it has to learn to pick up a key and open a door, then it has to learn to pick up a key, open a door, and get to a target location, combining essentially what it has learned in the previous experiments levels. So here it's essentially trying to get there, but it's stuck in the war. So it hasn't yet learned how to get to how to get not stuck. It's can take a bit because it's essentially babbling operations. It has no idea how to get it, but now it was lucky. And now it's already moving around the device and not getting stuck. It was lucky to pick up the key. It was a good run, essentially, just to show you how this can look like. And it opened the door also through motor babbling. And then it already combines this knowledge to pick up a key, go to the door, open the door, and then to go to the target location. And here, essentially, we just make the lever a bit bigger.
Is in babbling, is the
There are some branches where we make the babbling dependent on like curiosity, like to make it use moves which correspond to actions which it has almost no idea what the consequences will be in a certain context. But it's still early. So far, the default strategy is simply a form of epsilon greedy, to sometimes try a random action. And that's something clearly we want to improve because we have ways to measure like novelty of new events. We have ways to measure whether a certain action was already taken a lot in a certain context. We have all this evidence accumulation features, but for this exploration, we didn't make use much of it yet. But for exploitation, it's very effective in essentially using the hypothesis, which most likely led to the outcome that we wanted to achieve. We also have variations of discrete world. What's happening? Variations of discrete world environment. Like in this case, where's the screen so large? Oh, so large. Like here, this is like a simple environment where essentially it has to collect, maybe the choice of colors was not ideal. It should collect the green objects while avoiding the war, essentially. This is also something that usually doesn't take long for it to learn. Now it will just collect green objects. To some degree, that's simpler than what we saw before, because before it needed to collect a key and then go to the door, open the door, and then get to a target. So this is simpler. This is something we did before we moved to more complex grid worlds. But it's still a good example because it shows how fast it can actually learn to navigate, not get stuck, and learn to collect the green objects. When there is less green objects around, it's clearer that it's not just moving randomly. Oh, yes. We also have some classical examples here, like the Bang example I mentioned. This is actually Bang with stop operation. This is why it was vibrating at the beginning, because it just used left and right. But now it has learned the non-Markovian policy, so to speak. Also have things like cardboard, ASCII cardboard. No guarantee that it will work. This one is sometimes difficult for it, but usually it wants it. Let's see. Sometimes it's swinging it up, but it's not balancing it yet. Oh no, it got it. It's like also some more classical examples in reinforcement learning can also do. Oh yes. And what else is there? We could. Oh, yes, I think that's this for now. There's one more thing I want to show, which is also interesting from people who want to interact with the reasoner and see if it can derive useful knowledge if you give it like high-level knowledge. And we have actually also some interfaces for a natural language channel, a simple natural language semantic parser, which just extract subject, verb, object from a sentence and some prepositions and so, and builds essentially direct Narcissist relationships and fits it into the reasoner. We can show some of this. Additionally, we also have a way to interface with ConceptNet, which was also interesting because ConceptNet is a bit different than SAG. It doesn't really demand knowledge not to have contradictions. NARS also doesn't demand this. If some knowledge contradicts, it will not lead to it being able to derive arbitrary conclusions. So it's this is a quite practical knowledge base which we found quite good to use in combination with NARS. And we made it so that NARS can actually query ConceptNet for information. Can actually show this in examples like this. For instance, we have here we tried some intuitive reasoning, like if the sphere is round, and then I asked the system, is a ball round? Doesn't know it. The only input it got is the sphere is round, but it will ask ConceptNet, and the ConceptNet will say, yes, balls are round. And then I can ask, is the sphere a ball? And it will have the hypothesis that that's the case. Then I can tell it more things like a box can sustain a ball, like here in this picture. Then I can also ask if the box can sustain the sphere, and it will essentially deduce that that's the case. This is a related example, geographic containment, like if we say Paris is a city, Paris is part of France, we could ask, is France part of Europe? That didn't appear here, but ConceptNet says it tells us, yes, France is part of Europe. And then if we ask Paris is part of Europe, it's essentially just a case of transitivity of part of relation, and it will say yes. And you can also ask more abstract questions. A city is part of Europe, and it will also induce this because it has examples like Paris, which is a city, and from which it has derived or got the information that it's actually, or derived that it's actually part of Europe. So oh, yes, exactly. It just takes the information from ConceptNet and directly translates it into Narcissist. What's also happening is when it already has information about a certain relationship, it will revise it with the, so it does not need to fully believe ConceptNet if it already has a lot of evidence for certain knowledge to be first, for instance, then it, even if it gets this positive case from ConceptNet, will essentially, how to say, revise and still believe that's maybe not the case, or vice versa. Maybe it has the belief that that's not the case, but only with very low evidence. And then ConceptNet says, I have evidence that this is actually the case. And so it can actually revise also information from potentially different knowledge sources, which don't need to be consistent with each other. This is a very, very different, major difference to something like SAG, which the solution they had was essentially to group the knowledge into micro theories which apply in certain contexts. And we don't need this in us. We don't need this design time imposing of certain micro theories which need to be consistent. Yes, I can actually also if we execute like this example here. Maybe let's make the text a bit larger again. We can essentially try this. This is a script which translates English input to Narcissist. Simple English sentences at least. It's not very sophisticated at current stage. This is now, there's another channel which we attach, which is concept net Narcissist, which allows it to query information. And then we pipe this into the shell. And maybe for the hands-on part, maybe I will start from the beginning actually. Let's go into a new directory. So to get the system running, we need to execute this line, git clone openness for applications. Then we can cd into it. Then we can simply execute build.sh. We can execute it this way, or we can also execute it this way. Doesn't matter. It will complain about SSE because I have a Mac processor which doesn't have it, vectorized instructions, but it simply compiles it without SSE when it's not present. And now it should run all the tests successfully. Now we can do the thing. We can do English to Narcissist, concept net concept net Narcissist, NAR shell. And then we can also add some coloring, make the output a bit prettier. And so if we, for instance, look at the representations in this example, if we, for instance, say, the sphere is round, then it will essentially translate it to inheritance statement like this. Sphere has property round. And also if we do something a bar.
Just for a moment, I want to let you know that there's a band that's going to start a sound check at 5 o'clock. So we're allowed to be in here for a bit longer, but it could get loud.
Okay. That's fun. What did it complain here? Branch that doesn't. Maybe they changed something in concept that sometimes happens if they, because this one uses the online version, and if this one can try again, but looks like they changed something. They do this sometimes. Yes, it crashes. It's not honest fault. That's they make changes to the ConceptNet API whenever they release a new version. But we can do the same without ConceptNet for now. We simply delete the thing in English. But I used two tabs. So we had the sphere is round. Or is round. This it says here. There are also a lot of derivations derived about this. If we don't want them, we can say volume is 0, then it will not print them in the next input. So now we can ask sphere is a bar. it says yes, phi is a bar. And we say a box can sustain a bar. Yes, this is what I have also here. Then it will use such a relational encoding, box bar sustain. And now I can ask, it will have derived with a certain confidence that the box might sustain this field, for instance. So one can essentially just go through this example like here. Of course, we can also say things like Garfield is a cat, for instance. Cats are animals. Garfield is an animal. Garfield is eating mice in the garden. Then it will say Garfield eats a mouse and Garfield is in the garden, essentially. So it can also do some basic grammar learning. Oh yes, it will essentially carry out 100 inference steps when we enter 100. Maybe it's more interesting with volume back to 100. So we'll see all the derivations it made. A bar is something which is round and can sustain a box, for instance. Being round and being able to sustain a box has become its own category, essentially. A bar is similar to a sphere. Whatever is in the garden, it's a mouse. The mouse is eaten by something in the garden. So not always easy to interpret the outputs, but the hypothesis owner builds in comparison to openness are quite simple. So it's usually most of them are quite easy to understand after some reading of the relevant Narcissist. But also, I think the English channel helps a bit to understand the Narcissist encoding, because one can write simple sentences and then see how does it actually represent the knowledge. And yes, this is something it can do currently. Another thing which might be relevant is the Python interface. There is a script called nar.py in the MISC folder. And let's see how much time we have left. 12 minutes, I guess. In the Python folder, there is a script. If we call the Python interpreter, we can simply say import nar, and it will import the reasoner. And now I can use the API, which is quite simple. I can do things like add input. Then it will say, okay, this is the task, it has input. The term is cat is an animal. The truth is frequency 1, confidence, default. There are no derivations at current stage, no answers returned, no executions. There was no reason because there was no execution. And then there's also the raw text of what the reasoner gave it. And this supports all the reasoner functionality. For instance, we can do question answering here. What is an animal, for instance? This it will, where is it? Essentially, if maybe we can do this a bit better, that we don't need to read all the output. We are only interested in the answers. Answers equal now at input answer. Okay, answers it's called. So we can simply say at input, what is an animal, and return the answers of the system. If we now use this variable we have used, let's see, maybe it didn't like that I made a mistake at the beginning, because I had a syntax error or something. But now at input, cat is an animal we had. And then we did something like just return it for now. Now at input, what is an animal? And then we can say also if we don't want to that it prints the reason output, we can also say print is false as additional argument, but it's quite useful also for the robot application to see what is actually input, what is actually derived, what is actually executed. So now we could do things like what are the actual keys here. So the answers, executions, reason, and so on. So let's just use the answers again. Here it says you can also use answer 0. It says there's an answer with term cat is an animal and with this truth value. And of course the truth can also be queried, like what is the, if we are interested, what is the confidence of the answer? We would say this answer 0, truth, confidence. Essentially, so it's a quite simple interface, which simply passes the output, the shell gives to the Python script. So it simply spawns it as a sub-process and then passes the output. Yes, so we can use it for question answering, but also operations. Like if we say in the context of A, operation left will lead to B. Let's say that's already something we delete, or we can also train it. We can also do a similar thing. We train it for X and execution of red leads to Y. Oh, I used the, oh, where is it? I made a mistake here. X, red, and Y. So we can now also do again the question answering. We could ask it how to achieve Y. Or we could ask it even with context under context of X, what would you do in order to achieve Y, for instance? It would say, under this circumstance, I would do this in order to get Y. So it can also be used to introspect what would it actually do in a certain context. And of course, in the actual context, that's also what it would do. So if we have, for instance, X, then we want Y. We want the system to reach Y. We'll execute the operation. Even though it has just seen a single example, but that's the best it got. It's there. This one is essentially a sequential conjunction. It means that I know in the slides I have simply written it this way. I have written it like something like that. I have used notation like that. But essentially here is an implicit sequential implication between both events. So after X, the the right will lead to y being observed, essentially. Exactly, so it's like a temporal succession. That's one thing, and I think we have 5 minutes left. There's maybe one thing which you might find interesting, but maybe the robot example I will. That there's a video on YouTube in case you want to see it. You can watch it later if you want. How's it called? I think I got the video here. Yes, we have more recent robotics work, which might be also interesting to you, where we have bought a robot which has like multiple sensors. Maybe this is better. Maybe just to give you some idea, but I will also show in the conference. So we have used this robot, and we have used a machine learning model for object detection on board. We are also using localization and mapping so that it can build a map of the environment, and NARS essentially constantly receives events about the bounding boxes, meaning what is currently seen by the camera, and also receives location information as estimated by the SLAM algorithm. And then it can, for instance, notice, okay, this spotted plant is I always see it when I'm at a certain location. And so this is enough for it, even though the vision channel knows nothing about localization or vice versa. Simply by receiving the events from both modalities, it can then remember where is the spotted plant located. Simply by correlating, again, temporally, okay, whenever I get this location output, I see the spotted plant. And this is something which we make also use of in this experiment, which I will show then that it can actually, yes, maybe I can. So it can, for instance, remember the location, but I can actually have uploaded this video, I think, which shows some of the capabilities of this combined solution. So what we show here is the thing I just mentioned, like correlating events from map channel and vision channels, so as to be able to go back to a remembered object's location. And then there is also more work where we have, because this robot has a manipulator arm, we also show that it can then use this with some pre-knowledge of how to pick something, can actually carry out some task like searching for a bottle, and then combined with the first thing, retrieve it to some location we wanted to retrieve it to, which it then recalls from memory. I have seen it I have seen this object at a certain location according to the temporal correlation which was made in the past, and then it's going there and essentially putting back the bottle. Maybe I can quickly show this capabilities, because I think I will not have time at the conference to show this video. I will only show the details of how you will see more details there than. But here you will at least see what it's actually doing. So this is now a case where it simply goes back to a location of an object which it already has correlated in the past. This is just to show that it can actually utilize this previous learned or input correlation in order to revisit a certain location. So also since it's using a robot operating system for this and using this map, it means it can also use the navigation stack of ROS. So it can also avoid obstacles on the way. Like in this case, I asked it to go to the location where it saw the bottle the last time, essentially. And of course, if it doesn't know yet where the bottle is, then this is what it will do. It will simply drive around and usually we also have some experiment where we show that it can quickly learn object avoidance, which is actually similar like in the grid world environment, where it notices, okay, if it doesn't move to the left or right, it will not see anything new. It will essentially get stuck. And this is also something which we have an experiment with a robot which learns object avoidance. But if it already knows how to avoid it, then it will just, in this case, move to try not to crash into it. And if it's lucky and finds the bottle on the way, then in this case, it has some background knowledge which tells it should pick it. This is also real-time contour, so we don't use motion planning. It's actually looking at the visual input. Is this actually aligned with the grabber? And so if I would, for instance, move the bottle, in this case, it would adapt to it because it would notice it's not spatially aligned. So we don't use motion planning, but the idea of real-time feedback, essentially. Ideally, we would also like to use this real-time feedback in order for it to improve its grabbing procedures for different operations. But this is something we have not yet demonstrated. Oh, I moved too fast. Gripping is a bit slow. It also has a servo sensor here. So it actually notices when it has successfully grabbed it. If it does not, then it will essentially stop the operation and drive backwards and see if it can fix the grabbing. Yes, and in this case, it doesn't yet know where the human is, so just driving around and is searching for a human to retrieve the bottle to. And next, this is just now a view from the robot's perspective, from the camera, how this looks like from the robot. There are also interesting things. Like here we saw, it actually detected itself as a cell phone. This can sometimes happen that it, because we simply used the YOLO model, which was trained on ImageNet. And and we have all of it running on the robot, the reasoner, the YOLO model, and also the SLAM algorithm, and the rest of ROS. It's also running on the robot. Currently, it's using a Jetson Nano with 4 GB of RAM for the entire solution. And this is now the case where everything is combined. So here I'm essentially sitting. This was really hard to do with the video creation tool, because in this case, I wanted to have the view of myself on the camera as seen from the robot, and also it was a bit tricky to get rid. But here, essentially, it sees me sitting in front of it. So it should essentially, when it finds the bottle, it should know where I am and should be able to directly move back to me and give me the bottle, essentially. So here, what I'm doing here is, whoops. This is actually question answering here. So in this case, I simply asked it what it sees on the left side. I guess this is not very visible. But it says essentially person has property being on the left. So it actually was for me to see if it actually identifies me as a person. And so that it can actually remember me, because then I will ask it to return the bottle to the person. So it's just to check whether it has actually seen me. And then I just send it on the mission. I tell it should bring the bottle to me. But it didn't yet see the bottle. It's moving around. Now it sees the bottle. It's trying to grab it. Here we also see some of the error correction. It's not perfect. We did not spend much time on the manipulation, which itself in robotics is a very difficult thing to get right, especially if you wanted to do it in a way that it doesn't know the object's dimensions beforehand. And so it's quite rudimentary, but nevertheless, with this real-time feedback, most of the time it's able to carry out this task. Oh, yes. That the only we have some way to export knowledge to the file, like to export the 1000 most useful concepts, for instance, and which can then be fed into a new instance. This capability we have, but here we did not yet utilize it. Also in openness. But the doors are a bit different, but we have essentially the same idea to export memory. Now it's giving me the bottle. There's some completed the mission, so to speak. I will go into the details of this in the conference presentation. That we also have, of course, we have not run this a single time, but at least 10 times, which is not too much, but it was a bit, the robot battery life is really annoying because it only lasts for like half an hour or so. So I had to load it between the runs. But there are still some issues like mechanical issues. Its manipulation is difficult in robotics if you don't give it the dimension beforehand. So mechanical issues still sometimes are an issue, but can also happen in this particular task because the manipulator it's not how to say it's the servo sensors are not very accurate and so on. So usually if it's tipping over the bottle, it will usually not be able to pick it up, even when it's able to see it. But this is something we want to see whether we can use also the real-time feedback to make it adjust its grabbing procedure in a way that it will essentially then learn how to pick up the bottle which has tipped over ideally. And this is something which we will try next, but are still work in progress. Oh yes. Are there any questions? I think we're over time anyway, right? Then I think we can conclude the session. You're welcome. What is here? Okay. No questions from YouTube. Okay. Then I think the next part of the conference is tomorrow at 9 a.m. right? Yes. I will lift it some. No, but actually, I think there is. I think. Let me check. Actually.